Okay, all right. Are we all good in the back? I see you, Aaron. Where's Zach? Looking for my eyes. Okay, are we ready to go? Thank you. All right. How's it going? I was planning to ask for more energy, but I think we're good. So, my name is Ceremonies, and I am formerly part of the McGill Rocket team, and I'm a fervent disciple of Launch Canada, where I'm outreach lead and master of ceremonies for the conference. So, unfortunately, you'll see my face a lot this weekend. I want to congratulate all of you for making it from across the country to the beautiful city of Timmins to launch some Canadian rockets. And today we have teams from almost every province in Canada. I see we have people from BC. I think that's a 3,800 kilometer journey, so thank you. We have people from even Tennessee, California, and that's a lot of gas. So thank you for making it all the way to our very own Canadian rocket launch competition. Thank you very much. So on that note, allow me to officially welcome you to Launch Canada 2024. You know, I say it every year, but there's nothing more Canadian than talking aerospace in an arena in the boreal forest with a polar bear on the stage. Launch Canada last year had its first edition in Timmins and on Metagami First Nations land. And we've been lucky enough to be welcomed again to the same location this year. Thank you. Thank you very much. That is very adequate. Launch Canada wishes to properly lead this collaboration with the City of Timmins and the Metagami First Nations with the utmost respect and vision for the past and for the future. Essentially, almost every day this year, even Joel sitting a little bit late, we've been working towards making this place something we would like to sustainably call home for the decades to come. So thank you very much. And so allow me to make the following land acknowledgement. I would like to respectfully acknowledge that this week we will be gathering on the traditional lands of Metagami First Nation within Treaty 9 territory. We extend our heartfelt gratitude to the community and the people of Metagami First Nation for allowing us to come together and host the 2024 Launch Canada competition within your traditional territory. Thank you for your generosity and hospitality. Thank you for welcoming us on your land, and thank you for showing us the ropes of your heritage while we build the future of Canadian aerospace together. Thank you very much. Talking about the future of Canadian aerospace, I would like to welcome up here a very young and good-looking fella. One of the only reasons we are here today. Please give a warm welcome to Launch Canada's president, Adam Trumpor.
All right, thank you everybody, and welcome first of all to the third ever Launch Canada Rocket Competition. So this is only the third year of the event, but it's incredible the way we have grown in just a short amount of time. You're all absolutely a testament to that, and I know I've said this before, but I will say it again. This growth is really thanks to all of you, the students. It's your passion for rocketry and your constant eagerness to challenge yourselves and learn by taking on some of the most advanced aerospace projects possible, and creating these opportunities for you to do this is what drives all of us. So thank you for making this what it is and creating this community that we now see represented here today. Thank you all. So when we held our second event last year, several volunteers and students all said that what being together really felt like, more than anything, was a reunion. Not just competitors and volunteers, but a community coming back together to reconnect with each other and do some seriously cool things together. This year, it feels for me like that idea of community has taken on an even greater meaning, because this is our first year returning to Timmins and to the traditional territory of the Matagami First Nation. And from the very beginning of our time here, in so many ways, these communities have made us feel so welcomed and so supported, and I really cannot overstate that. There are a lot of ways that that's manifested itself in the last 2 years here, but I want to share one more immediate story. So, trying to put together an event like this always has its hiccups along the way, not unlike building a rocket. And a couple weeks before the event, we learned that the shipping container mission control center from last year was no longer at the site. So we were left scrambling, trying to find a new platform for our launch control tower. So we started reaching out to everybody we could see who sold shipping containers or delivered them to the area. And there was one local company right here in Timmins, Jokans, who immediately reached out and said, "We love what you're doing here. We want to donate one of our shipping containers for you to use for this event." So they did that, and they dropped it off at the site. It was amazing seeing how they came through for us. Well, then just the other day, when we were hauling our really big trailer of stuff up to Timmins, we had a bit of a trailer disaster partway here, and the hitch got damaged. When the fellow from Jokans heard that this had happened, he immediately got in touch and said, "What can we do to help? Don't worry about your trailer. We'll be your trailer for the week, and we're happy to send our welder out to check things out and see if he can repair it." So this was just one of those examples of the community going above and beyond, and we literally wouldn't be able to do anything like this without that kind of support. And we've seen it in every interaction, from things like that to random conversations with local members of the community at Tim Hortons. This just keeps happening, and I'm sure there will be so many more stories over the course of the next week of these amazing supportive contacts with the locals, and I hope everybody makes sure to thank the community here for everything that they're doing to support us. So on behalf of all of us at Launch Canada, thank you to our incredible host communities for welcoming us and literally making everything that we're doing possible. But I also do want to talk a little bit about why we're doing this and why this all matters, because I do get questions all the time that from people who will look at something like this and say, "That's cool. Why a rocket competition?" And admittedly, we're doing something that's pretty unique here, so it doesn't always make sense to people why this big deal about rockets. And I could point out a lot of reasons why this is all important. I could talk about how important the things that we have in space are to our everyday lives, how they allow us to communicate, to navigate, to monitor and respond to disasters, to learn not only about the university, but our planet, our environment, our climate. And you'll hear talks this weekend that will touch on many of these things. But I'm going to focus on something that's a little bit more fundamental, because this is rocket science. And we all know that rocket science is extremely complex, extremely difficult. It's kind of right up there with brain surgery. But what I really think this week is all about, what Launch Canada and everything that we do is all about, is showing people that we can actually do it. You're going to see students from across Canada, and even from right here in Timmins and Matagami, taking on challenging problems, and you're going to see them succeed. No pressure or anything, but this is absolutely going to happen. There is something tremendously empowering about discovering that you can take on really hard things and be successful at it, with some hard work, care, and attention to detail. And something as seemingly complex as rocket science is not actually out of reach for any of us here. So in his famous speech challenging the United States to put a man on the moon, President Kennedy emphasized that this was something they choose to do, not because it's easy, but because it's hard. But I'm going to suggest that sometimes the reason for doing something isn't because it's easy or because it's hard. Sometimes we choose to do it instead because it's important. And if something is important, it doesn't matter how hard or how easy it is. It's important, and that's all the reason you need. And not unlike building rockets, it turns out that putting on an event like this is hard. It's actually incredibly hard. But we're all here because we think that it's important. We think you're important. Your skills and the things that you will go on to accomplish are important. They're important to this industry. They're important to Canada. And we have a lot of amazing supporters, sponsors, and volunteers here making this all possible who I'm pretty sure are going to agree with that. So I want to acknowledge a few of our sponsors for this year's event because they do enable all of this, and you'll be seeing many of them around today. You will also see their logos and names listed on our banners around the event. So if you see any members of those companies here, do be sure to thank them. At our highest level, which we call escape velocity, I want to acknowledge Pratt and Whitney Canada, who are our lead corporate sponsor this year. They have returned for a second year this year because I know they love everything that you're doing and they want to help you to have more of these opportunities. So huge thanks to Pratt and Whitney Canada. Also at the same level, I want to acknowledge our friend Mark Pathy, who has become an amazing friend of Launch Canada and has been providing us with amazing support starting this year. I also want to acknowledge Soft and Way, who have been supporting us with many of the special educational projects that we do for our students. So huge thanks to our top 3 sponsors. At the second stage, I also want to acknowledge one of our longest serving sponsors, MDA Space. They've joined us from year 1 of this event, and they've kept coming back and been supporting us more and more every year. We are really truly grateful for everything that they do to not just be a leading space company in Canada, but to help make sure that you all have these kinds of opportunities. So huge thanks to MDA Space. So just going through a number of our other sponsors for this year, I want to acknowledge Daishan and EOS. I want to thank the Royal Canadian Air Force, who are celebrating their 100th anniversary this year, and you'll probably find some goodies from them in your swag bags. So huge thanks to the RCAF. It's especially cool having them involved with this event on this important year for them. I also want to acknowledge Randing Research, Telegistics, Stein Industries, Nordspace, Flonex, Murata, Shunk, and local mining company Newmont Gold. So this year we also have a few special sponsors who are supporting us with some of the prizes that you're all going to be competing for. And back again for our 3rd year, we've got our motor makers extraordinaire, Cesaroni Technology, who are supporting the grand prize for the basic launch category with a Pro 98 reload. We also have our friends from the Canadian Space Society who are once again sponsoring our payload challenge. Of course, it's not just about the rocket, it's about what you can do with the rocket, and so we always love to see students thinking about those applications, and thanks to the Canadian Space Society for helping us to incentivize you all to do that. And finally, on the sponsor front, we also have three very special in-kind sponsors that I would like to acknowledge. Communicating on a remote site has its challenges, and ICOM have supported us since last year with the radio gear that allows us to do this. They have been absolute heroes, so huge thanks to ICOM. You will be the beneficiaries of their support for the rest of this week. I already mentioned Jokans, the provider of our shipping container, so once again, huge thanks to them for everything that they've done. And finally, I want to acknowledge Astos Solutions, who've been providing us with rocket trajectory analysis software so that we can make sure we know where the rockets are going to go and keep our airspace clear. So huge thanks to Astos. Now, I know these speeches do very quickly start sounding like an Academy Awards talk, so I'll try to wrap this up really fast, but before I do, I also have to thank all of the team of volunteers who work so hard throughout the year to make all of this possible. You're the reason why we're able to do this and why I can get through this without having a complete nervous breakdown. So huge thanks to our volunteers. You'll see them represented in light blue shirts. Volunteers, want to stand up? And you'll also see some very special volunteers, our staff members who take on leading roles to help run this event and make this whole show happen. You'll see them around in dark blue stylish polos, kind of like this one. So staff, please stand up. You're all amazing. We also have a few longtime volunteers who unfortunately weren't able to make it this year, and as a community, you know, you do feel the absence of your friends and family members. So I also want to acknowledge David Bueller, Karina Sapelnikova, and Mark Hassenflug, who you've seen around the last 2 years, who unfortunately weren't able to be here this year, but I know that they're thinking of all of us here today, and we're certainly thinking of them and looking forward to seeing them the next time they're going to be able to. So huge thanks to those three. So this really is an incredible community that we've all built here, and you guys are all doing some pretty incredible things, but what you're doing here isn't just important for what it is, it's also important because of what it shows. These projects that you're all working on do show people that things that they might never have known were possible actually are. This is why we're here. We've already seen that inspiration motivate you all to bigger and bigger things. And I'm thrilled that we can be here to share some of that excitement and inspiration with each other and with the community who are so graciously hosting us. So thank you to our hosts for welcoming us into your community, and we hope that you all feel welcome in ours as we dive into a really exciting week. So let's all have fun, work hard, and let's launch the North. All right, and now, rather than just standing here to acknowledge our biggest supporters, I'd like to invite a couple of them onto the stage. Chief Jennifer Constant from the Matagami First Nation. Please allow us to thank you again for your amazing support, and come right up. So, we kind of set a precedent unintentionally earlier this week with slightly oversized gifts for our amazing host, Chief Constant. And we're not going to stop now. So, Chief Constant, thank you so much.
Thank you.
Got a couple other little tokens for you as well. So we have our official mission patch for 2024, and the Launch Canada patch, as well as a t-shirt. So thank you so much.
Thank you.
Not to put you on the spot or anything.
Well, I was kind of expecting, I didn't expect the gifts. So a bit of a little story behind this. What's customary when you go to greet someone is to give them tobacco, and Cyril had messaged Brandy to ask for reference of what should be provided. So she sent him a picture of a tobacco tie. And so when I showed up, I've got this massive tobacco tie. They're usually, you know, a little tiny thing. So I got this massive thing, and it just made me burst out laughing. He's like, I had a picture, but I couldn't put it to scale, so I didn't know. So now that I'm gonna get worried once they get to be the garbage bag size. So thank you so much, though. I appreciate this gesture and the respect that's being provided to Matagami First Nation. And not only that, but the excitement that we as a First Nation have to be hosting this type of an event in our territory. One of the things that maybe is not common knowledge to the general society is that Indigenous people, and more specifically Ojibwe people, which is the territory that you are in right now, they have long studied the sky. We have legends and many stories about the stars and different alignments and all of that. So this is something that we think is really in line with our First Nation and our traditional values. And it's an exciting time, not just for Timmins and for Launch Canada, but it's an exciting time for our community because we have the opportunity now to hopefully ignite that kind of inspiration amongst our people in our territory, as well as our youth, so that I'm hopeful that we position ourselves in the north to be the hub for aeronautical research, design, any of the stuff that comes with that. So it's an exciting time. So I just want to say thank you from the bottom of our hearts for this partnership. I kind of got ahead of myself, so I'm gonna just kind of back up a little bit. What's customary in our territory is to do a greeting and to acknowledge all of you and to say welcome, so I'll do that. Makwashkishko Nindishnakas, Nindogi Makwe, Matagami Aki Nidojba, Boju and Dinwe Maganidag. And I'm trying to brush up on my French, so I use every opportunity. So bonjour à tout le monde ici. Je m'appelle Jennifer Constant. Bienvenue chez le territoire traditionnel de Matagami. And again, my name is Chief Jennifer Constant from Matagami First Nation, and I wholeheartedly welcome you to our territory for this exciting week of activities. So, miigwech and miigwech again.
Okay, and next I would like to call up the councillor from the city of Timmins. We don't have the tobacco for you, unfortunately. We already used it all. But you still get the patches and the t-shirt.
Thank you so much.
Thank you so much for your support.
Good morning, bienvenue, miigwech. On behalf of Mayor Boileau and the City of Timmins, I'd like to welcome all of you to our community. We consider it such a privilege to have this gathering of 300 to 400 brilliant young people, or mostly young people. I'm sure there's some older people in the house. But I'd like just to follow up on some of the words of Adam and Chief Constant about what an inspiration this really is and an opportunity, and how important this work that is being done. As Adam mentioned, it's not easy work, but there's not a lot of things in life that are easy. Easy isn't always good, and easy isn't always right. It's just easy, and that's why everyone does it. But this is important work about communication, about navigation, about studying our environment, and I know that our community wants to be a part of this. Just as Chief Constant mentioned, it's an opportunity to perhaps become a hub for aeronautical engineering and study, and that is so important to our community, and we want to host a great week for all of you and show you what our communities can offer with our balloon base in Timmins, with our advancing technology, with our really tremendous mining communities. This could be an opportunity where we see you every year. And I'm really struck by the fact that growing up, I'd often hear, this isn't rocket science. Well, today I can actually say, this is rocket science. And I'm really proud to be a part of this, and I hope that everyone has a blast this week. I couldn't help myself, but welcome to our city. Enjoy yourselves, and thank you so much for attending and bringing your collaboration and your brilliance to our community. Thank you very much.
Okay, beautiful. Still prompts me for my password. It's me, don't worry. Thank you. Thank you to our wonderful host. Coming here really starts to feel like home, and from the all-you-can-eat ribs at Montana's to the all-you-can-eat blueberries in Metagami, I always feel both happy and well-fed around here, so thank you for having us. And talking about well-fed, it takes a whole lot to run this Launch Canada machine, and a big part of that are our sponsors, like Adam mentioned. And right now, we have one of our largest sponsors on stage and in the audience. So if we could have Jessica come upstage with us, with the City of Timmins. So I'd like to welcome Adam to the stage, Jessica and the City Councillor, and allow me a small celebration. Cue the music.
Let's go, girls.
Soon we're going to start line dancing up here. So, all right, now we have a full day of activities ahead, starting with our yearly Launch Canada conference, which you're already attending. And so I would like to welcome to the stage our conference director, Zachary Harrison, who's always running somewhere, and he's running here.
Good morning, everybody. First of all, who's here for their first time? Put your hand up. Wow, a lot of first timers. Well, welcome. Who's here for the second or third time from previous years? All right, welcome back. Okay, so I'm going to do a little rundown of the conference schedule for y'all. So here we are at the opening ceremonies, running a little late, but that's okay. Right after this, we're going to have an info session for all of the drone operators. So that'll be right here, right after the opening ceremonies. And then we'll start our conference program for the day. So we've got a great lineup of guest speakers and some of the teams here coming up to give technical presentations. Really looking forward to hearing from all of you. And at the end of the day, we've got a very special presentation that we'll be playing from a special guest. Some of you might have figured out who it is. It should be really cool. And then the day will finish. We'll continue with our judging and safety inspections, which will be happening downstairs near the main entrance. We've got rocket motor builds happening tonight at Northern College. The mini launch event is a little bit weather contingent right now, so if it's raining, we might have to postpone that for the day, but we've got some other outreach activities going on here in the arena. And I think that's about it. So then Sunday, a lot more team presentations. We'll have a second showing of our special presentation for anybody that can't catch it today. And then we'll end our day with a keynote presentation from MDA. And finally, we'll have an info session for range safety. Right after that, we'll have a group picture with everybody here, and we'll tear down the arena. And everything has to be out by the end of the day because the arena is going into maintenance starting the next week. So yeah, that's it for the conference schedule. I hope you all enjoyed the program we've got for you this weekend. Thank you. Last thing I want to mention is we've got a food truck outside. So our good supporter Dixie is here to feed you all. So please go get your lunch or breakfast or what have you down there. And finally, I'm going to hand it off to Shane for discussion about safety inspection and everything. Thank you, everybody.
Hey, everybody. Let's see if we can speed us up a little bit. I don't have a lot to say. For those of you that are new, we've all done virtual safety inspections with everybody. Now we're going to do it for real. So when you're ready, and I don't want anyone to rush, you've all heard this from me before, I don't like seeing people rush, but when your rocket is ready for final safety, you bring it down to the room at the bottom of the stairs, no energetics, no motor, don't button it up, we're going to pull it apart and check all your connections. So I want your rocket basically ready to fly, minus the motor and the ejection charges, and no shear pins. Bring it down, we'll go through, we'll give you either things to rectify before you can fly, or we're going to give you the all go. If you get the go ahead, all you have to do is go through the final inspection on site, which is basically a weigh-in. If I give you anything that you need to address, you'll have to address that and then go through the safety again. If you get that addressed really quickly, I'll be happy to look at it again here. Otherwise, we'll just look at it on site. If your project is a hybrid, see Peter. He'll come around and do your inspections in place. Everyone else, solids, bring it down to the room downstairs and we'll do that. And that's all I've got. And the liquids, yeah, that's all Peter. Hybrids and liquids are Peter. And he's gesturing this, which the 2 stages can come down to me, that's fine. They're solids. That's all I've got. So we'll just bring the judges up next. So that's Robert and Mitchell.
See, this time it's not me. So. There you go.
Good morning, everyone, and welcome to our head judge's address. My name is Robert Bernard, and I, along with Mitchell Cesaroni, are both the head judges for this year's competition. The main role for all judges, including us head judges, is to select which teams place first, second, and third in this competition's basic, advanced, and technology development and payload challenge categories. Who wins the Launch Canada main trophy, as well as a few other fun and silly awards. As head judges, we additionally try to make improvements to the judging process for Launch Canada, act as arbitrators for any issues that arise amongst the judges, and we also act as a point of contact for questions student teams may have. As Launch Canada continues to evolve, so too has its judging. When this competition was first held in 2022, as one of its head judges, I can assure you major lessons were learned. Expecting our judging team to review every single project, it was simply impractical. The level of items scored had to be drastically reduced, and we simply needed way more judges. This prompted our association to immediately document and audit at the time what worked and what didn't work. Fast forward to months before 2023's competition, one of the first things we tried to do was increase the number of head judges. This led to more ideas, refinement to our scoring sheets, and implementation of a buddy system where only 2 judges ever scored the same team. Ironically, despite these efforts, we still ended up with only 2 head judges present in person last year. Roughly the same number of judges have been recruited, but the projects had easily doubled. Despite odds like these, all judges we have had over the past 2 years, some update going on, over the past 2 years have done a phenomenal job helping this competition run smoothly, and for that deserve a large round of applause. Now, if you haven't guessed already, I was the head judge that didn't show up last year. It was for a good reason, though. However, being off-site allowed me the opportunity to again audit our work. It led to actually the discovery and correction of a clerical error, and most importantly, served as a subtle reminder that even us head judges are not infallible. This finally brings me to highlight the process changes for this year. The buddy system I spoke of will be used again. The scoring sheets have been refined even more. We've gone as far as to even schedule when judges actually meet and evaluate each team over both the conference days. In terms of scoring, some of the most significant changes are the team documentation submitted is worth 50% or more of your total points for this competition for all the 3 main categories. And we did this to reduce the number of technical questions asked and evaluated by judges during the competition itself over the week. There's been a reduction of the scored line items to 52 or less for all the competition categories and payload challenges. The flight score for both the basic and advanced categories is now calculated using 4 steps, and I'm going to quickly go through them. 1, we obtain your estimated altitude from the teams prior to your launch. 2, we obtain your achieved altitude from your flight computers. 3, noting what type of propulsion that you have, whether it's commercial off-the-shelf or student research and developed. And 4, and this is important, using your estimated achieved altitudes, the flight score is now calculated based on a linear formula if it's commercial off-the-shelf, or it's a simple and less severe polynomial formula if it's student researched and developed. And we did this to recognize the higher difficulty associated for teams that are developing their own propulsion systems. Next, the scoring of ground support equipment has been added. So if you made your own GSE, you can and will get scored for that. We've added line items to evaluate your basic build quality, the manufacturing, integration, and assembly. And last but not least, and this is important because Mitchell and I need a bit more time to, as well as the whole team. There will be no scoring judging of your launches or demonstration on the last final launch day, because we will be using that for deliberations. So aside from the aforementioned scoring changes, this also marks the first time all Launch Canada judges have access to internal documentation to guide them in their duties, building further upon the framework needed to help this competition be successful for many and many years to come. And I almost forgot to mention the best part. We have assembled the largest contingency of judges we have ever had, a total of 16. This competition would not be possible without the dedication of our judges. So with that, I would like my fellow head judge, Mitchell Passarelli, to now introduce our team and provide closing remarks.
Okay, I'll be fairly brief here. I just want to introduce our judging team for this year. So if I could have all the judges kind of stand up and come to the side here. That way I can introduce you all one by one. Yeah, come in front, that's actually better. Don't stand behind things. Okay, so in, I guess, alphabetical order, we'll do this the easy way. First we have Ahmed Raslan, who is an ex-McGill propulsion member and a current master's researcher in combustion at McGill. We have Gabriel Dubé, who is a Polytechnique's former director and a master's researcher in propulsion as well. We have Arsha Zarin, who was a propulsion test engineer at, or intern at RFA in Germany, and is also an ex-propulsion team member. You're gonna hear that phrase a lot as we go through this. I don't know why you guys like judging so much. Next up, we have Joel Jean-Philippe, who is McGill's former team captain and a PhD candidate in combustion. Joel's been, as you can see from the dark polo, has been a Launch Canada member for quite a while now, and he is indispensable in our efforts. Next, we have Sebastian Frick, who is a project manager at Cell Aerospace, working on gas turbine test cell development. He's actually worked on some stuff in, he recently came back from a trip in Singapore, setting up some new test cells for, I think it was Siemens? It was for Pratt. Okay, there you go. I should know this. Beside him, we have Niall Bannigan, who was Western's former rocketry team lead and is a current master's graduate in materials and mechanical engineering. Then we have Zachariah Mears, who is a former Waterloo rocketry team member and a current master's researcher in metal additive manufacturing. Next up is Dr. Puriya Madani, who joins us from the Ontario Institute for Technology and is a researcher in adversarial machine learning, if you want to know what that means. I was just talking to him. Next we have Noah Gaffrin, who is a former Queen's Rocketry team member and or their former chief technical officer and a current master's researcher in composite materials. We have Robert Gus Gissing, who is a lecturer at Conestoga College, and I would refer to him as a jack of all trades. He's also worked on a bunch of stuff with Adam, if you want to know a little bit about Adam's deep, dark past. And last but not least, we have one of our payload judges, sorry, give me a second here. Dante Corsi, who joins us from MDA where he works as a payload systems engineer. So he's going to be one of our payload judges coming around and talking to each of the teams entered or who have an entry in the payload challenge. That said, there are a couple judges that I don't see here, and I'll just mention them for sake of having them on record. Michelle Wander, who's probably somewhere at the launch site or trying to get back here as we speak, who is a CSA systems engineer and skydiver. He jumps out of airplanes for fun. I don't know what's wrong with him. That's maybe why he's not here right now. And Madalena Patron, who is not only McGill's ex-team captain, but is also one of our logistics coordinators here for Launch Canada. So if I could get a round of applause for our judging team this year. Now for some very brief logistics for judging. In case you don't know, there is a judging schedule. We'll try and make that communicated to the team somehow, but you should have received an email, I believe last Wednesday, or this Wednesday, communicating when your team is supposed to come. When it is your time slot, please come to the judging table. We're just across from the checking counter. Introduce yourselves, and your judges will introduce themselves to you as well. and they'll come with you back to your team's booth so that we can inspect your rocket and then do the questions there. When it comes after the conference days, when we move into the launch days, the judges will shift into an observer mode, and we're going to kind of follow you around, shadow your teams to see how you guys operate in the field, and taking into account that performance, because obviously watching the rocket go up and down, we don't really have to see, oh, look, it went up, did its job. So that scoring is fairly automated. We're more interested in seeing how the teams operate themselves. For reference, the judging interviews are 1 hour, and the payload judging will occur separately because we only have, unfortunately, 2 judges for the payload challenge this year, so we're going to have them come to the teams individually on their own time to discuss the payload challenge. If you have any questions, I'll be at the judging booth if I'm not busy judging a team, so feel free to come by and ask any questions. Thank you.
Okay, so we're really busy at Launch Canada this year. There's a lot happening. I had planned some final words now, but I realized that there's a whole other section to competition that I should mention. That is outreach, because I am the outreach lead. So if you allow me, we have a few activities that are going to be planned for this weekend and this week. We have the Rocket Passport. So if you see young students walking around with a little passport in their hands, these are students from Metagami or Timmins that are excited to learn about rocketry. So each team here should have prepared a small activity to introduce them to the field and have fun with them. And don't forget to stamp their passport, because we have a little gift for them at the end. At the end of the day, we also have a mini launch event, so they'll be painting rockets, or you can even paint some tube rockets that we have on the outreach booth. And at the end, if weather permits, at 3:30, we're slipping on time, but let's say around 4, we'll be launching rockets on the baseball field. And one big thing that we're doing this year is the Rocket in a Box program. Essentially what that is that Launch Canada has decided to provide a rocketry experience from A to Z or Z, depending on where you're from, of how to launch a rocket. So we've gone and done some workshops at Science Timmins and in Metagami First Nation to essentially teach students how to build rockets and launch them. So you're going to see them throughout the launch week, and they're actually going to come to your booth in dedicated times, and it's on the schedule. It should be in your volunteer handbook. So if you see them, please welcome them, do a little bit of mentorship, because you were there at some point. And finally, a big other new thing that we're having this year is we're doing certification flights. So Launch Canada, we have your big and majestic rockets, but we also have certification flights to allow Canadians and people from all over to get their certification to launch rockets on their own. So we have 23 university teams, but 40 certification flights. So I think that's like a record in all ways, so I'm not going to say which record, but it's a bunch. And organizing all that is our LCO, Christopher Hobbs, that I'll invite on stage to talk about it.
Hello everyone, I'll be quick. So with your big rockets, you'll be inspected downstairs for solids, and then the final inspection will be at the tent just in front of the LCO, in front of the CCAN. Once it passes final, you'll get clearance to go out to the launch site to put it on the rail. You'll be going out with the RSO. RSO will help you or inspect and help you get it on the rail, and then we will send you off. With the personal projects, you're not going to be inspected downstairs, but you will be inspected at the tent in front of CCAN. Once you are inspected there, the same with the Big Bird. RSO is going to go to the launch rail, help you set it up, and then we'll send you off. Priority will be to the university projects. So if you are on the rail and ready to go and a university project shows up, if you're ready, and by that I mean ready, we'll send you off and then send the university project out to the rail. But if you're not quite ready, then we'll pause the individual certification to give precedent to the university projects. That's basically it. Frank is RSO with Tripoli, Shane, and your car. So if you are certifying Tripoli or car, just make sure that you have the right RSO. Oh, you're both. Okay, so then If you're doing a car certification, then make sure it's Shane. If it's Tripoli, it can be Frank or Shane. So that's it.
Chris is very nice, but he can get very scary. So listen to his advice. Thank you. And now to conclude this ceremony, we have one more thing. And you notice that there's a bunch of beautiful trophies on the stages. Like I said, even a polar bear and a certificate and a Canadian flag. But for those that have come in previous years, and I know there's a bunch of you, there's one big thing missing on stage. And so we have this ceremony that we do every year, and I would like to do it again and welcome the Launch Canada winning team of 2023 from UBC Rocket. I would like to welcome the captain, Victoria, on stage. And you can even place your tag on it. So there you go. Congratulations again to our 2023 winners. This could be you. All right, so organizing an event like this requires tremendous work, dozens of people behind the scenes, and thousands of volunteer hours. And I say it every year. It feels like a yearly family reunion, and it is because it is. And that's a big part of why personally I am here today. I love it here. And so if you don't mind, please one more round of applause for our volunteers and our staff. Thank you. Thank you. Thank you for your devotion to this true grassroots movement of student rocketry. And so now, let's head for a small break before we start with our invited speakers for the day, and let's go launch some rockets. Thank you very much. So for drone operators, please come here for a 15-minute, 10-minute little presentation. Thank you. Let me maybe ask Adam, yeah. Drone operator? I think underneath makes sense. Yeah. So is Alex here for the drone? Okay, very cool. Congratulations again. It's coming. The presentation for drone. Thank you.
So everybody here for the drone operations, could you guys take a seat up front here? Just there shouldn't be too many of us. Okay, no worries.
More of the, this is really being like this grassroots movement. So in other areas of aerospace, usually it's like, hey, we're done yet. Oh, let's do it. We're gonna, develop this theory, go launch this thing. They have never completely adopted it. But some have been inspired by what they've been seeing going on around the world and deciding that, why can't we do this here? And so they've been taking it upon themselves to do it. So we're not just seeing like these cool activities with students, we're actually seeing the genesis of an entirely new industry right now.
Okay, so welcome to the Launch Canada drone operations. I'm Alec. I've been the one that's been setting all this up, making sure we're in order for this. So if we go to the next slide, I can't see what slide we're on, so this is where it's gonna be fun. You guys gotta tell me. It should say attendance form. Attendance? Attendance? Okay, we can skip past that because we just did that. So we're here, so the reason why I've got you here today is for safety. We care because we don't want any collisions, we don't want any fires, we don't want any injuries. A drone can easily take your eye out. A little one, a big one, it doesn't matter. It will hurt you. So from a safety perspective, that's why I have you guys here, that's why this matters a lot. Moving forward to the next slide. Oh, thank you. So if you guys don't know, we are flying Class F aerospace. We are in an atypical airspace. It's pretty locked down for the most part, but it's important that you guys understand where you're flying, and because if you don't, well, you shouldn't be flying. Most of you guys do not have an advanced license. Most of you are flying micro drones. So we are able to work around the rules here, and it just requires permission to fly, and as long as you guys are flying within the rules that I set out here, it shouldn't be an issue. I also have this presentation basically summarized into a picture that I want to basically airdrop to anybody, so if you guys have questions, you can easily go on your phone and look at it. Next slide. So if you guys don't know, there are consequences if you don't follow the rules here. So there are point deductions that are possible. And last thing we want at the end of the day is next year, have no drones flying beyond the live stream. We want you guys to fly, we want you guys to record, we want you getting your footage that you guys want for your rockets. And then if it gets severe enough, obviously we can contact Transport Canada to go through with fines and further situations, I guess. I'd rather not though, because that's where it gets a lot more severe. Next slide. So first of all, I want to start off, everybody's drone, I want them to mark it bright yellow. It is a requirement. So I have a micro drone here, this is my personal one. These drones are really hard to see once you're up in the air. If you're a spectator on the ground, once you're past about 100 feet, it can be hard to pull this out. I have good eyes, I can only fly this in line of sight to 200 feet. So I have tape, I have scissors, come find me, come tape it up. Kaylin. Negligible. It's negligible. The safety is more imperative in this case. I'm pretty sure the drones fly less than 250 enough that a little bit of tape won't hurt. But I'm looking for mostly tape on the top, on the sides, and on the bottom. Obviously, that's not always possible. So like this live stream drone, I have a lot of tape on the top, on the sides, but I have cooling fins on the bottom here. I'm not taping that. So I have tape. You guys come find me at the live stream tent. I have tape, I have scissors. Take some time, tape it up a little bit. I'm looking for visibility at the end of the day. Next slide. So flight rules here are going to be pretty simple. Next slide. They're trying, it's not working. So pretty simply speaking, if you don't know for a micro drone, we're going to keep it simple. All micro drones, you are not actually permitted to fly over people. Fun fact, you go on the Transport Canada website, they're rated to fly near people, not over people. You need a parachute to fly over people. So pretty simply speaking, do not fly over people, do not fly over the launch pads. Keep 30 feet, it's not hard to do. And stay the heck away from the spectator area. Because as soon as you're flying within the spectator area, within 100 feet, it's an advertised event issue, and there's a huge liability associated with that. So flying around, just keep your distance. And then secondly, the following slide will have information on launch pad areas roughly, where to take off from. Take off from those wherever possible. Obviously, if you're out on recovery down the road 5 kilometers, take off safely, make sure there's nobody that's going to get hit. But for the most part, if you're able to, take off from the pads. In case anybody else is flying, it'll be easier to identify. And then third of all, stay under 400 feet and fly within your capabilities. So transmission range for the drones I know that are flying here shouldn't be an issue. You should be able to fly up to 15K on your transmission range. However, your battery life will limit you to 2 to 3. And then beyond that, make sure you can return home. You have enough battery life. And you have your return to home preset to about 50 feet. That'll clear your trees in most cases. Next slide. So this is included in the little picture I'll send you too. This is the areas. So you'll see we have a very similar setup to last year. The live stream will be taking place from both the solids pads as well as the advanced pads. Those two, there's a waypoint at the second set of pads that I'll be running from. The exception, it's going to be a little different if you're flying from the test area down there, because you are both at a different elevation and there's less people that you're going to have to be dealing with. So as long as you stay below your 400 feet above ground level AGL, there shouldn't be any issues here. So there'll be pads marked out. Go find it before you go. Your launch is ready. Somebody will probably be there, and if not, it's just stay around your pad when you're launching it and you're flying. That way, if somebody else goes to launch your drone, you can communicate and make sure that it's in order. Last thing we need is a collision and then starting a fire and then everybody's evacuating. I don't need that. Next slide. So pretty simply speaking, if you don't do this already, you should be. Quick pre-flight checklist. Make sure you're fit for duty. No drugs or alcohol 12 hours. Standard Transport Canada rule. And you feel good to operate. Don't want you vomiting halfway through and then passing out. That would be a problem. Make sure your battery levels are good. The weather is suitable, so weather, it's just, the drones are pretty good for weather capabilities for the winds, so I'm not really concerned with that, since if we can fly rockets, we can fly drones. But no rain. All of your drones are consumer grade. They are not waterproof. They will incur damage if you have rain. It will rot your motherboard, and besides that, you could have GPS issues and just lose your drone. Check the equipment structurally, aeronautically. Do a quick check over. Do you have a fin that's broken? Do you have a fin that's cracked? And then hazards. Make sure you're 30 feet away from things. So there's a tree. Avoid the tree. Pretty straightforward. You can fly beyond line of sight with a micro drone here. It's not an issue. Just stay under 400 feet. Next slide. So pretty simply speaking, for emergency procedures, most of it is just return to home. If you lose signal, your return to home should automatically initiate, and that'll bring you within your signal. There's an aircraft sighting, bring it back. There's a fire, bring it back. Excessive winds, bring it back, or if you're forced to, land somewhere where you can recover it, ideally. There's rain, obviously, return to home. Next slide. Next slide. And then there's a flyaway, so this is more directed towards our larger drones, but we have like flight incident reporting, but ideally if anything happens, I made a form for you to fill out and we'll address it accordingly. If you have a sudden loss of power, just land away from people. Don't knock somebody in the head, that will be bad. Yeah. Do you guys have any questions at this time? We want to encourage flying the drones not just for taking your videos, but also for recovery. I know last year was very helpful to search the treetops for rockets and parachutes. So we want that to happen again, but we want to make sure we're doing it in the most safe and responsible way possible. At the end of the day, use your best judgment. Common sense should prevail. And yeah, have fun. Yes? The question was, do we have to request permission to take off? No, you shouldn't have to. You go to your launch pad, check the area, see if anybody else is flying their drone. If anybody is, just talk to them briefly, ask them what they're doing, what their flight plan is. Go over, launch it, go do your flight plan. Just communicate with the other drone operators. That's at the end of the day what you need to do. So make sure you have like 5-10 feet of separation, and you shouldn't have a collision. Yeah. If you have any other questions, I'll be here all week. I'll be available. Just ask me. I'm more than happy to help. And if you have problems with your own drone and you still want footage, look around at everybody else here. They should be able to, I'm sure somebody will be willing to put their drone up and record for you. Live stream will be, besides taking, obviously, live stream videos from much higher up, I'll have my secondary drone, and I'll have a team of flying in for pictures close up for launches. Yeah. I need to talk with you separately, but anybody that's name wasn't rung off earlier, I want to talk to you here about what's happening too. Hello. We got a lot of people. I do not like that. So if you're flying under 250 grams, go over here. If you're not, you go over here. Okay. So this is the easiest way.
Okay, so we are 15 minutes late, but we will continue with the rest of the schedule. So essentially what we're going to do, we're just going to slide a little bit the day. We're going to keep the same schedule, the same order of things and the same length of things, but we're just going to shift it by 15 minutes. So we have our first presentation coming up at 10 a.m., which is right now. So if people want to come in for the start of the conference and the start of the presentations, our first presentation is from Star and Nimbus. So I recommend you also invite your teams to come attend your presentation. That's okay, good. So I'll start with a short introduction then. I'll give 1 more minute. Okay, so I'll start with a short presentation of the team. Star has currently flown and successfully recovered 3 rockets. At the first launch Canada, they were one of the few teams at the very first edition in 22. They launched Ringo 1, which won the payload prize and reached 10,671 feet. Ringo 2 launched at 2023 LC, which won the 2nd place in basic and won payload again, reaching 9,841 feet. They then launched Ringo 2B at 2024 Spaceport, which won 3rd place in 10K COTS out of 68 teams and awarded 6 overall, while reaching 9,964 feet. That's really, really good. That's amazing. The payload project has been an iterative 5-year project working to closely mimic the goals of NASA's Dragonfly mission to Titan set to launch. What? That's awesome. In 2028. So the title of the presentation is Grid Fin Design for Subsonic Roll Control. And I'll have the presenter here come in a minute, which is Christian Venter. He is working on a mathematics degree with a specialization in computing science, which is essential, which in a sense, is just a cool sounding applied math degree. His role in the team is the vice president and a payload member. He designs the electrical and software systems used in our payloads. He is also responsible for heading the research and development of their autonomous control payload and the sensor algorithms they use for payload orientation. So I'd like to welcome Christian to the stage. Thank you very much.
Alrighty. Hi, Star. Is it saying it's connected? The mouse? I am now. Oh? Ah, sick. Okay, go to the start again, please. Alrighty. So, thanks for the introduction. So we're doing grid fin design for subsonic flight. So let's start with the why and the who of grid fins. That good? Good? Okay, sick. So why and who of grid fins? So for the people familiar with grid fins already, this photo will be pretty familiar to you. So this is the SpaceX Super Heavy booster, and you are seeing the photo up there of, you could see 3 of its grid fins in black right there, and this is their next generation flight vehicle. So here is a full stack of that vehicle. So let me just go on the slideshow of mine. So if I go next here, it's really small to see, but you can see those grid fins on that rocket right there, pointed to by that red arrow. So many people believe that SpaceX was the first one to actually design and implement grid fins, but as we know with everything in this industry, the defense industry did it first, and they did it better. So right there, you have the mother of all bombs with some grid fins on it as well. So that was kind of the initial start of grid fins, and then SpaceX took over. All right. Let's head to the why. So grid fins are pretty self-explanatory in the sense that when they aren't trying to impart any control, they have extremely low drag. So this is a top-down view of a grid fin. You can see that there's not a lot of surface area that's going perpendicular to the wind, so you have a lot of roll authority with minimal drag at this point. The next thing is, grid fins are quite easy to control. They only require one input, so that one input being a connection to anywhere on the grid fin, and then you are able to rotate the grid fin, and it works pretty easy. And then, the one really important thing for the space industry here is it being compact. So right there is a render of our payload, which will be winning payload this year again, 3-peat. So right there you can see the grid fin design system on there. So it has to be pretty compact to be able to actually fit into a 3U CubeSat design. Alrighty, so you would have noticed with the SpaceX grid fins that they were a square pattern. So, this mouse. So, on the left there is the square pattern. So, the SpaceX uses the square pattern, and we decided we would take a look at the square pattern, but also that hexagon pattern, because we thought there might be a chance that something else works better. And since SpaceX is mostly in the supersonic regime, we kind of decided to try something else and see if in the subsonic regime it's a bit different. So we did our tests, and surprisingly enough, like how supersonics and subsonics go, basically the opposite is true in subsonics. So where square works great in supersonics, the hexagon actually works great in subsonics. So that is the grid fin design that we will be using. And why is that the case? Honestly, where is it? We got no clue, because the surface area is pretty much the same between the two. It's like a difference of 1 square millimeter. It's basically the exact same surface area presented to the wind. However, probably with some CFD, you would be able to notice the actual differences of air separation and all that. Alrighty, so let's move on to simulations. So, how did we do it? KSP. It was easy and it worked. I got that in the back, let's go. So, for simulating spaceflight, especially at our level, KSP is quite simple. So, let's keep going about the simulation. So, in that photo there, you can notice it is a mock payload, and it has 2 grid fins attached to it. Here we go. So what we did was we created quasi-realistic conditions by implementing different mods that are able to more accurately represent the Earth's gravity, because in Kerbal Space Program, it's not anywhere near the real gravity. So we had that go down, and we could then test our different algorithms and programs with this simulation. Alrighty, so you have grid fins now, but now you have to control them. This fucking mouse. Where is it? Oh. Yeah, okay, I'm leaving that there. Okay, so what controllers did we consider to use? So there's 2 kinds of controllers. One being hand-designed controllers, which most engineers are used to. So those are like your PIDs. You have to have a pretty intimate knowledge of the actual system, the dynamics, to be able to control the algorithm. And then you have learned controllers, which all of a sudden are a big thing now with all the AI hype. So with learned controllers, you don't need to know anything about the actual system. They are able to kind of make a generalization on the system to be able to control it. So you don't need to know all of the different aerodynamics and all that in our case. So what are the types of controllers we tested? So one of them is called a bang-bang controller. So it's extremely simple. Basically, if it was spinning one way, we turn the grid fins all the way the other way to stop the rotation in that one direction. It's incredibly simple, and if you do it quick enough, it's almost continuous, and it can work quite well. Then we have a linear controller. So this is similar to the PID. You have a proportional constant that, depending on your roll angle and that constant, you're able to then change your grid fin angles to respond to the current roll. And then we have a hover controller. So this is a lot more known in reinforcement learning. So instead of having a simple proportional constant like you would in a linear controller, they have a very different function-based proportional constant. And then finally, the reinforcement learning controller, which we will get into a bit more. So like I said, the Bang Bang controller is incredibly simple. All it does is if you're going one direction of roll, it just completely tries to go the other direction. The problem with this is, besides being very simple, which is good, is it causes overcorrections and oscillations, because if you're going one way and then you try to overcorrect, you're going to overshoot. And then for the linear controller, so it's a lot more proportional to the rate of roll. So if you're not spinning very fast, you don't have to turn the grid fins as much, and that's definitely a good thing. The harder part about linear controllers is having to understand the system, and you need to be able to tune that proportionality constant, because if it's not right, you're not going to have any control. And we also know that aerodynamic forces aren't linear, so using a linear system to describe them is not the best. Now we head off to the hover controller. So what we have here is it's basically a linear controller, but instead of just having a simple constant, it has this piecewise function. It's incredibly simple. It's basically just a quadratic at the root, and otherwise it's pretty linear. So this allows for more finite control, and it's way better than the linear controller. However, you still have to tune another parameter, which is that delta. So right here, we can see different loss functions. So the hover controller, it's really hard to notice, but is the red line. So you can see it's basically a parabola, and then it flattens out at the bottom with very low slope over here. So this is the most common loss function, but there are multiple other different loss functions. So depending on the hover controller is how much actual grid fin orientation you spin. Alrighty, so here are the tests. Well, this shows you what is done in KSP. So the Bang Bang, if you're spinning in a negative roll, right, you turn the grid fins all the way in one direction. And then as soon as you go to the other side, you do the exact same thing, but in the other direction. And then you can see the linear and the hover controller are very similar, the difference being what happens here at the root. So instead of just being a line that passes through, you have those inflection points. So this allows for a lot more fine-tuning of the grid fins at the zero angle or around the zero angle point. So let's move on to the reinforcement learning controller. So it uses reinforcement learning, and it works based off of rewards. So the best way to think of it is the payload itself is an agent. What it's trying to do is make this reward function as happy as possible. So as it's falling, if it's inducing 0 spin, then it gets rewards, and if it's inducing more spin, it gets less rewards. And based on those rewards is how it acts. And then we use Q-learning reinforcement learning, which we'll get into here. So it's a big formula for no reason, but what the Q-learning does is it's an off-policy algorithm. So many people may think it's just easy for a computer to all of a sudden get up and learn because everyone's just looking at AI nowadays and it thinks it's simple. But the problem with computers are they're deterministic. So you can't just go tell the computer, go make some random actions and go learn things. The computer has to start with a certain way it's acting, and through iteration, it can change towards the best behavior. So off policy means the agent or the payload starts with a behavior that isn't advantageous, but with time and with the reward, it can slowly learn what the best way to do it is. And Q-learning, basically all it is this function right here. So your current response to the situation is dependent on what happened last step. So if you're spinning really fast to the left, you're most likely the next time you check also going to be spinning really fast to the left. So we take that into consideration. And then here, this big function, well, this big part over here, all this is the actual Q learning special part. So we have a certain learning rate, which goes between 0 and 1, so that's how fast you want to learn. And then we can take certain guesses based on the reward. And if we think in the future, if we do a certain action, and we're correct, that our function would properly reward us, and we are able to then maximize this function and make the best possible behavior. So Q learning is actually really old. It's like 1980s kind of reinforcement learning. Everyone still uses it because it goes off of the fact of the next thing to do is going to be dependent on the last thing and then a few extra guesses. So that's the gist of Q learning that we use for our reinforcement learning algorithm. So, there we go. Okay, so reinforcement learning versus handwritten. What's really the differences? Why should we even care? If my mouse works, I'll get there eventually. Yeah, okay. So, pros. There's no system knowledge required. So in reinforcement learning, like I said before, it could not care less what the system is. As long as you can give it a way to simulate, it is able to try its way through trial and error and get to the best possible solution. Because in many cases, it's just impossible to understand the whole system, so we just let something go through trial and error and get to the solution. So yeah, it's an iterative process. So the more time you give it up to a certain level, the better it can get. Where if you're just doing handwritten, then whatever equation you come up with in the beginning, that's what you're ending up with. So you can't iterate as much on top of that. And the thing that we've been finding recently is it's able to find unknown optimums. So where we think that we found the best solution to a problem, if you throw a reinforcement learning model at it, it may come up with a solution that we could have never thought of, but is way more optimal. And it's also easier to extend. Since it isn't dependent on the actual system itself, it doesn't care about any of the knowledge of the system, it's a lot easier to throw more variables in and to extend it further. But there are cons. So reinforcement learning is very machine intensive. So if you want to train a proper model very well, you need to have a good computer, lots of time, and not a lot of people have that kind of machine. And then also it makes really, really large code bases. So this leads to the black box problem. We make all these reinforcement learning algorithms, but we have no clue why they work. They just work. And they're so massive that we can't ever look into why they're working. And the reinforcement learning has some dependency on the simulation. Okay, so if we throw the reinforcement learning algorithm at our system, but it's only able to do bang bang, so it's only able to go left or right, with time, it just converges to either going fully left or fully right. But there's nothing really there that we care about. What we care about is giving it access to the full range of motion. So it can choose any degree it wants to turn to for the grid fins. And surprisingly, it basically chooses to become a Huber controller. So why does that happen? Again, we don't really know, because the Huber controller seems as if it has its pros, but we think there may be better controllers. So it would be good to look into more why the reinforcement learning or Q learning enjoys the Huber controller so much. So big graph, but basically it's just showing you your oscillations. So they're all starting at a certain negative rate of roll, and they're all trying to reach zero roll. So with bang bang in blue, you can see it's just oscillating back and forth between the 0 point. It's not really doing anything stable. But with the linear one and with the Huber one, with time, we are able to actually reach equilibrium and hit near zero rate of roll. But you'll notice that the Huber controller does it a little bit more efficiently and a little bit quicker. And then you'll notice on here, we didn't put the reinforcement learning model because, as I said, it just converges to be a Huber model. So what is the general conclusion of this? Computers definitely win at choosing the algorithms here. All of our linear controllers where we were messing around with all the different PIDs, all the different constants, the time it took to do that in comparison to just going, all right, here's the sim, try your best, through trial and error, find the best solution. Even though it converged to a model that we could have easily done before, we didn't know it was going to converge to that, so it found that solution for us. And then further work. So as I said before, we need to figure out why the hexagon grid fins are so much better. They're able to almost sometimes double the decrease in roll angle compared to square, which does not be explained with the small surface area difference, so we need to look into that. And then also, if we give the RL model even more finer control and even shorter time steps, because we only told the model every second you could decide where the grid fins go 10 times. If we instead said every second you can do it 60 times, 60 hertz, or 120 hertz, does it converge to a different kind of model, or does it just prefer the Hubert controller? And then the question is, does it work? And the answer to that is, I guess we will find out when it is launched. Because in KSP, it sure works great, but it's KSP. So, does it work? I guess we'll see. Alrighty. And then I guess that's reinforcement learning and grid fins.
Beautiful presentation. Thank you so much. So we have about 6 minutes for questions. If anyone in the audience has questions, I can come directly to you. Yes, all right. Here we go.
Hi, thanks for the great presentation. I was wondering, was the RL model trained within KSP, or was it trained something else?
Yeah, so KSP, we had a plugin that you could access and basically ask for the roll angle. You could ask for all the different orientation, and you could set your roll angle. You could set your altitude. So through that, the RL model was then trained based off of a bunch of different iterations or epochs on the KSP simulation. So it was on KSP.
Hi, so just wondering, how did you experiment with the effect of role reversal in your simulations, and how you're going to combat that if that so arises in the actual flight?
Sorry, could you repeat that? I didn't hear you too well.
Yes, so how does your system deals with the effect of role reversal if that happens during the flight?
If it starts rolling too fast, or?
No, do you want to?
Just from some of our preliminary research, because we were also interested in potentially looking at this into the future, we noticed that some teams had issues with the aerodynamic phenomenon called roll reversal.
Yes, okay. Roll reversal. Okay, yeah. So we have looked into it, and KSP does not do it justice. So currently, our solution is throw the model at it in the real world and see how far it iterates from the actual KSP simulation. So there's a lot of fail-safes, of course, to the actual mechanical system, but the current way, because it is really hard to actually properly estimate that roll reversal, is we just want to get data on it, because it's pretty easy once you have that data to do some kind of interpolation to then be able to account for that, which is easy in the RL model because you just tell it, here's something else you have to account for, where you can't do that as much in the other ones.
Okay, thanks.
I'm curious how you actually actuate the grid fins on the device, and I would guess that your KSP simulations probably don't take into account things like control delay through the whole system. But I'm curious how you get like the actual response in the physical system.
Okay, so that's a good point. That's a good question. So we, through our testing of the electrical system, we can slightly accurately tell what our delay to our servo motors are. And then with KSP, it's pretty simple since we're just plugging into it for our model, we're not running it on KSP, we're just asking KSP for data, is we can induce a certain delay to that data receiving or data sent. So if we receive data, we can go, okay, this is the orientation, the model takes its time to do its response, and then the model thinks it gave an answer, but KSP only gets it a certain few microseconds later. So that was accounted for by forcing a delay into the actual response to KSP.
Great questions and great answers. Do we have any other questions? Okay.
Sorry, I was just wondering, has the team experimented with any other kinds of simulation? Because I'm just curious how KSP compares, if you have kind of baseline or anything like that to compare it to?
Yeah, so that was part of the preliminary research looking into different simulations. So the problem with many open source simulations of this kind is if they're targeted towards things with grid fins, they're almost always high atmosphere space. So we found a lot of NASA sims that would have been perfect, a lot of different sims that would have been amazing, but as soon as they go lower atmosphere like we are, all of the actual aerodynamic forces that you are experiencing at that level and at our small scale basically get thrown out of the window. So to combat that in KSP, we're able to scale the payload properly, that the forces are pretty close to what we expect because you can do some napkin math and see. But there are most likely better sims out there. They're either A, too expensive, or B, would require a lot of work to actually get lower aerodynamics to work, since in KSP, you can throw plugins in of people's theses and they go, here's the best actual simulation of wind shear and all of that in KSP. So there's a big research community in making it as accurate as possible.
Great. Do we have one more question? We have time for one more question. If not, I'm going to ask mine. So long-term, long vision for this project is to replicate the Dragonfly mission. If I were to bring your project in a different atmosphere in terms of gradient and density and nominal density, how could you adapt your current approach to that?
Yeah, so the nice thing about this is if you are aware of the actual environment you're going to, which we are on Titan, we have a general gist of the density and the composition of the atmosphere and all that, you're able to simply just change the values in KSP to better simulate that. And then since it already learnt on Earth's values, it would learn a lot quicker getting over to these new values, because in reality, for most of them, it's this mostly linear relationship. So it just realizes, okay, I have to turn a bit quicker, I have to turn a bit slower, or there's more oscillations. So you just have to run the same model, but with some different variables to allow it to just quickly change itself up.
Amazing. Thank you very much. Everybody, a round of applause for Christian.
Thank you so much. Yeah, thank you.
Okay.
Very nice. Very nice.
All right, so in a few minutes, we're going to have another amazing presentation on the Launch Canada Turbo Pump. So to repeat, we'll have Adam Trumpor presenting the Launch Canada Turbo Pump project in a few minutes, right on this stage. So I'll give 1 minute.
So how are we doing this? Should I use my computer?
Do you have slides on your computer?
I do.
And they already have them?
I gave them the slides, but I guess I can only view them if I follow along on my
You
machine.
have the TV there on the left,
Yeah.
so you can kind of refer to that. If the text is small, I can turn it a little bit more. Otherwise, I will get the clicker for you. So, okay, everyone, welcome to the second part of the conference. This is an in-person presentation by our very own Adam Trumpor. Let's be honest, Adam doesn't need an intro or a bio, but here we go. Adam is a rocket and gas turbine professional with broad involvement in the industry. He is a turbine engine concept designer at Pratt and Whitney, Canada, and the founder and president of Launch Canada, which you might have heard of. It's an organization created to support and advance experimental rocketry in Canada. In his spare time, Adam is heavily involved in liquid propellant rocketry activities, mentors many students' rocketry teams, and works tirelessly to advance the cause of entrepreneurial space and rocketry in Canada. Please welcome our very own Adam Trumpor.
Okay, thank you, Cyril. Back again for a look at another aspect to what we do at Launch Canada, and that's our special projects. And this is something that we started doing initially in 2021, but it's evolved over the years. And our current featured special project is a long-term rocket turbopump development that is now called Project Maelstrom. So we'll take a look at the project, what we're trying to do with it, and where this all came from and where it's going. Next slide, please. Okay, so obviously the rocket competition itself is a big part of what Launch Canada is all about, but really we try to take a broader perspective in how to create the most cutting-edge learning experiences possible for Canadian students. And we've found that on top of the competitive aspect, there is a place for collaborative learning opportunities as well that bring together students from multiple different schools to work together on big shared projects that teach real-world skills and kind of make that theory come alive. And we do this by pairing students with knowledgeable industry people like myself to take on these really complex projects. And we like to use this as a way to display real systems engineering, technical, and management practices that would be typical in the industry, while making sure that we've got these active partnerships to do this. And this has actually been a really fruitful way to develop a real cutting-edge technology and demonstrate new capabilities at the lowest possible cost. Next slide. So this really all came out of an event that we did back in the summer of 2021, where coming out of the pandemic, a lot of teams had really lost their ability to work on their own projects for an extended period of time. So we decided to step in and get students working directly with myself and several other volunteers to fire this 1,000-pound thrust liquid oxygen kerosene rocket engine that I happen to have lying around, as one does. And over about 4 months, we went through everything from how to handle liquid oxygen safely, to how to write procedures, to the basics of high pressure and cryogenic plumbing systems, how to bend tubing, all of this, and we kind of took everybody through familiarization and onboarding, through cold flow testing, and all of this culminated with an absolutely flawless 35-second hot fire of this 1,000-pound thrust liquid oxygen kerosene engine, which you can see right here. Next slide. So building on that experience, one of the things we heard from everybody who took part was that they loved the experience, they loved the chance to work with us and see what actual professional approaches you would take if you were doing this kind of thing for real, and people were interested in more of it. So when I was thinking about what more of this would look like, as a turbomachinery designer myself, one of my own holy grail projects had always been to try to do a rocket turbopump. These are the most challenging aspect of any large professional liquid rocket propulsion system. It is incredibly uncommon for amateurs or students to successfully develop one. It's rare enough for anybody to even attempt it. And they involve a whole lot of very specialized disciplines, most of which schools really don't teach at all. So we wanted to do this project to change that. And we decided to build on the success of the 2021 engine testing event and develop a pump for this proven engine. Now, this actually had the side effect of also creating what might be the smallest rocket turbo pump ever built. This is much smaller than you would normally use a pump for, but we wanted to see if we could make this work, and there were a number of reasons for wanting to do that. When we set out to do this project, one of the things we really consciously decided on was to focus on the overall systems engineering and the mechanical design of a complete system, as opposed to fixating too much on any one component. And we wanted to create the opportunity for people to build hands-on experience with all of the different aspects that go into this. At the same time, we realized that doing something like this right is usually going to be a multi-year development, even for the professionals. So we wanted to use the vehicle of Launch Canada to create this multi-year learning opportunity. And so this is a project that we're working on in 3 basic phases. We're beginning with an electrically powered fuel pump, followed by an electric liquid oxygen pump, followed finally by a fully integrated gas generator cycle turbo pump. And each one of these is going to build to the next phase and demonstrate concepts that are going to be applicable to the next thing. Next slide. So just the basic rundown for anybody who isn't super familiar with turbo pumps. We're going to take a look at what one is, and they are quite literally the heart of any big liquid rocket engine. So the technical definition is a turbo pump is a rotordynamic pump powered by a turbine consisting of rotating parts inside a stationary housing. But the more practical definition that I've always liked for turbo pumps is they're an integrated, compact, highly loaded, cryogenic cavitating pump coupled to a thermally isolated rotating dynamic disc with multiple blades eating a ball of fire, all contained in a lightweight, leak-proof shell, shaking but not flying apart, going from 0 to 30,000 RPM, 20 to 1200 Kelvin, and 40 PSI to 6,000 PSI in 5 seconds flat, while balancing tons of axial forces so the bearings are not crushed. So that kind of gives a taste of some of the actual problems that go into making a practical turbo pump work. Next slide. Now, why do we want one? They really come down to the most fundamental challenge of any rocket propulsion system, which is how you feed really high flow rates at really high pressures into a rocket engine. And there are basically 2 ways you can do this. One is with very highly pressurized propellant tanks, which is what anybody using nitrous oxide in hybrid or liquid engines is probably going to be doing. And it's what most amateurs and hobbyists who get into liquid rocket propulsion will do as well. But the problem with that is that most of a launch vehicle is tankage. And so if those tanks have to be able to contain very high pressures, then you very quickly reach the point where the rocket is too heavy to achieve any practical mission objective. So if you want to get around that problem, your alternative is to store your propellants at low pressure in lighter weight tanks, and then use some kind of a pump to kick that pressure up to feed it into the engine. So that type of pump that has sort of been the proven standard for liquid rocket engines is a gas turbine-driven turbo pump. Next slide. So we're doing this project for a couple particular reasons, apart from the fact that I really like playing around with turbo machinery. And one of the basic ones is that turbo pumps, as it happens, are really, really hard to make work. These are incredibly complex, highly engineered systems, and unlike most aspects of amateur rocketry, where it's not actually all that difficult to design and build a thrust chamber that works decently, you can't design a functioning turbo pump that way. A poorly designed hybrid or liquid thrust chamber, might still operate just fine, maybe with slightly low ISP or slightly rough combustion. A poorly designed turbo pump will either destroy itself within a couple seconds, or else it just won't produce useful discharge pressure and flow. And there's been a growing number of student teams around the world that have started to get into developing their own turbopumps, but very, very few of them have ever succeeded in producing a practical pump at the end of it. And usually this is because most student teams either lack the time to treat all the elements of a turbopump as thoroughly as is necessary to make it work, or they lack the necessary resources to pull it off, or they simply miss some fundamental understandings of various aspects of practical turbo machinery that are really important to making a functioning machine. So we're wanting to try to address that with our project here. So to do this, we took on this practical, collaborative, multidisciplinary project that is building on what we did with our original LR101 firing, and we really want to use this to create some unparalleled project-based learning experiences for everybody involved that does a deep dive into all of the different aspects of this technology. And there are a whole lot of spin-off benefits to this as well, because turbo machinery like this touches on a whole bunch of other industries. It's obviously got crossover applications to the aircraft industry, to gas turbine engines. When you're working on something like an electrically driven pump, you've got crossovers with UAVs, with electric vehicles as well. And this is also helping to address a fundamental gap in Canada's rocket propulsion experience. As I think most of us know, there is a lot more interest these days in rocketry in Canada on a serious level, but currently the turbo machinery piece is one of those big capability gaps. So we're recognizing that the more people we have in Canada who are interested and who know how to tackle these kinds of developments, the better positioned we're going to be to grow this industry. And as I was saying, schools basically don't teach any of this. Next slide. So the first phase of our project has been what we're calling our electric fuel pump, or EFP, and this was conceived from the very beginning to basically be our workhorse pump. It's the first one that we're working on. It's the non-cryogenic propellant, so in a lot of respects, it's easier. In some respects, it's actually more challenging. This is a very tiny pump, so the manufacturing of something this small poses a whole lot of unique challenges. And you can see right here, this is our first prototype pump impeller. It's about 2 inches in diameter, which is an awful lot smaller than is normally used on any practical turbo machinery. With this particular pump, we wanted to make it modular and testable as far as possible, because this is really the one that we're going to use to prove out a lot of the basic design concepts that are going to apply to our subsequent liquid oxygen pump and to the final turbo pump. So we've been front-loading a lot of the aspects of the design and testing of this particular pump, and we've also been using this as a way to calibrate our various models for both the overall pump performance as well as the internal secondary flows and the overall rotor dynamics of the machine. Next slide. And to help us do this, we've been building up not just a network of partners, but basically an entire supply chain to help us cover all of the critical components that go into something like this. And that includes cutting-edge software tools, and Soft and Way in particular, with their AxStream software platform, have been a tremendously valuable partner for this project. They've really given us some of the cutting-edge design tools we've needed to design and analyze the machine. Flonex as well has been supporting us tremendously with system-level modeling tools. And trying to do a project like this spread across multiple schools across the country has meant that online collaboration has been super important. So we've had Onshape available to us with their online CAD and PLM platform that have really helped support this. We've been building up a network of specialty component suppliers as well, including Carter Bearings, Shunk Carbon Technologies, and Saint-Gobain Seals, who are helping us with some of these critical precision internal components. We have a number of testing partners who provide cutting-edge instrumentation, as well as experience with turbomachinery testing. And that includes SSSOC, CEL, as well as Coolite pressure transducers and Lion Precision for eddy current proximity probes. And finally, the manufacturing aspect for this is absolutely central to everything. And we've been thrilled to have EOS as a partner for additive manufacturing of many of our critical components, as well as cutting-edge machine shops like Daishan and MacFab, plus various specialty manufacturers throughout the entire supply chain. So it's really like with a real turbomachinery development, it takes a really well-established network of key partners, and we've been building that as part of this project. Next slide. So we just wrapped up our second year of the project, and after a while of just calling it the Launch Canada Turbo Pump Project, we realized we really had to come up with a better name. So we went with Project Maelstrom for this one, which both kind of evokes crazy swirling fluids, but also we felt there was a little bit of irony given how tiny this pump is. The big focus of the past year was finalizing the detailed design and several iterations on the complete mechanical arrangement of the pump and all of the major components. So you can see a quick cross-section there of what the internals look like. We are using a bunch of very specialized materials as part of this, so we managed to procure all of those critical materials. We have a number of our major components that have entered or are entering production. We've also been working on manufacturing trials of some of the more challenging manufacturing aspects of the project as well. We've also been doing a lot of work on a pump controller for this that is going to be a platform for controlling not only the electric pumps, but also the future gas gen cycle turbo pump. Design has been one of the biggest focus of the past years. We worked, like I mentioned, collaboratively with the Onshape platform to do the design and CAD for the machine. We completed the detailed design for pretty much all the major pieces and a number of design iterations on many of them. We were thrilled to have Jeff Thornburg, the former head of propulsion at SpaceX and former head of turbomachinery at Aerojet Rocketdyne, go through a design review with us on this project. So he provided some amazing feedback. And these are the kinds of partners we like to be able to connect our students with to have those learning experiences. We worked through the instrumentation design and selection for the pump with a really big focus on instrumenting the heck out of the machine. And we completed the design of the electrical drivetrain and procured pretty much all of the major components for it. Next slide. There were a number of major analytical activities that were supporting the design work. Tolerance, stack up, and steps and gaps analysis for the machine is really central to any turbo machinery, but particularly something this small. So that has been a really big focus, as well as detailed design and modeling of the secondary flow systems and the sealing systems and the cooling flows through bearings and motor cooling jackets. We also put a lot of focus on the rotor dynamics modeling of the pump in order to validate the design, and all of these models are going to be further calibrated through the initial testing of the machine. We completed manufacturing reviews for all of the major components with a number of our specialty machinists. We've got our set of dynamic carbon seals being manufactured. We completed the production of a number of custom sealing and lock washers. We worked a lot on a customized motor for the project involving a spline shaft and some fairly extensive internal instrumentation to allow us to characterize the heat generation by the pump and the effectiveness of our cooling design. We've begun manufacturing trials of our splines in Inconel 718, which happens to be one of the most painful materials to machine. We've been working on titanium impeller test prints, as well as alternative machined and brazed designs. We've been working on brazing trials as well for the various superalloys that we're going to be using in this machine. Next slide. So for the year ahead, we're really getting into the fun part. This is where we are going to be finally assembling and testing our first complete pump unit. Like I said, this one is really envisioned as being our workhorse. So we're going to get this one into testing, and we've designed it to be as modular as possible so that as we learn through testing, we can change out components and we can iterate very quickly without requiring too much of a tear-up of major sections of the pump. Building on the lessons from that electric fuel pump, we've completed the preliminary design of the liquid oxygen variant, and as we get more into the testing, that is going to feed into the detailed design and refinement for the LOX pump as well. And we're generally taking a task-based approach with this, so we invite students from all the participating Launch Canada teams to take part. We have dedicated subsystem leads with responsibility for the various technical disciplines, and students can get involved in as many of these aspects as they're interested in and take on design jobs that kind of feed into the various aspects of the project. We really want to maximize the opportunity for everybody to learn by trying new things and building this experience, so that hopefully when you all enter the workforce, you will do so with a level of experience that is almost unheard of for new graduates. Next slide. So for the electric fuel pump in particular, we are completing the manufacturing of all the remaining pump components. That should be done over the next roughly 3 months. We're finishing the final integration of the electric drive system. So for the electrical engineers in the crowd, this gives some really interesting projects to get involved with. We will be doing the final assembly of the first pump and its initial testing as well. The LOX pump is transitioning into the detailed design phase now. So a lot of the design process that we used for the electric fuel pump is going to get adapted and fine-tuned as we go into this more challenging liquid oxygen pump. We're hoping to get into the manufacturing and testing of that pump by probably towards next summer if everything goes really well. We're also working on the design of the hot end for the turbo pump version in parallel, which includes preliminary design of the actual turbine and gas generator and the control systems for these. We'll be looking at getting the initial gas gen built and tested over the next year, and we'll be starting manufacturing trials of the turbine as well. And to kick off the new year of the project, we're going to be starting with a student onboarding process to welcome new participants, get them up to speed in the different aspects of the project, and we're working on some cool learning activities as well. Next slide. So for anybody who's interested in getting involved with the project, we'll be kicking off signups for it starting in September. So we're always happy to welcome new participants to join us and be part of some pretty cool real-world rocket propulsion and turbo machinery design, build, and test activities. And we're hoping that this will give everybody the chance to actually learn from industry professionals how you develop these kinds of machines, and hopefully we'll create a really valuable learning experience for everybody involved. So if you're interested in joining, shoot me an email, pay attention to the Launch Canada Discord and emails, and we'll have more details coming soon on how to take part in this latest crazy rocket project of ours. So if anybody has any questions, I'll be happy to take those now.
Amazing presentation. So here's the first question.
Hey Adam, I gotta say this is really impressive stuff. It's awesome to see student turbo machinery projects in Canada.
Thank you.
I have 2 questions. The first one is, you mentioned a couple times a test rig, and it sounds like you are going full steam ahead straight to the fuel pump. So I'm wondering if there are any sort of critical things that you like, are you planning to still do the test rig first, or are you just going to kind of test in situ with the fuel pump and see what needs iteration from there?
So yeah, we kind of went back and forth on that a little bit, but with the modular approach we took to the pump itself, we are going to be mostly working on in situ testing. And so we've designed the different elements of it to be fairly easy to isolate. So if we need to do deeper dives into seals testing, bearing preloading, cooling, all those things, it's fairly easy to do that. And if, to the extent necessary, we can do a deeper dive into these things as well. We have also been working on some kind of companion projects to this, because honestly, turbopumps are so multidisciplinary. You've got a million possible sub-projects that you can go into, almost an arbitrary level of depth, right? So we've been working with some cool partners on novel bearing concepts as well, and we're going to be probably doing some focus tests on those ones too.
Cool. Yeah. Awesome. And my second question is, you mentioned that this blind shaft is made out of Inconel 718.
Yeah.
But I'm not aware of any hot gas components of that system, and usually you're using Inconel for strength and temperature. So
yeah.
what was the motivation for that choice?
So for the fuel pump, we're not making extensive use out of Inco. It's, like you say, not necessary. For the liquid oxygen pump, and certainly for the turbo pump, it is going to be much more important. So kind of in keeping with the goal to front load a lot of this, we don't want to go through a preliminary design that has these massive manufacturing risk items, right? So we're focusing on a much easier to machine material for the fuel pump shaft. But in parallel with that, we know what this is going to have to look like for the turbo pump, and so we want to retire that risk early. So that's kind of where that's coming from.
Cool. Thanks so much.
No problem.
Once again, great question. So we have time for one more question. Such a great presentation. We have representatives from Kronos that flew from interplanetary space.
Hi, Adam. So is there a particular performance benefit to using a gas generator engine? A gas cycle turbopump versus an electric cycle on such a tiny scale?
So, because of the tiny scale, I mean, we're kind of in uncharted territory in a lot of ways. Turbopumps themselves don't necessarily make a lot of sense for super small vehicles. Usually it's around the 5,000 to 6,000 pound thrust class where you start seeing a net benefit from the pumps. In our case, we're doing this partly because it's a small, manageable size, but it's also kind of matched to this existing machine. In general, the drawback with electric pumps is batteries and motors are really heavy ways of packaging and transmitting energy. So normally, rockets work best when you use the energy sources that you naturally have on board the rocket, which normally means propellants, which normally means you're going to get into either a gas generator or staged combustion or expander cycle engine. One of the things we are actually interested in looking at a little bit more is what a design study for a pump in this size would actually look like comparing an electric-driven version to a turbine-driven version. You've got ease of operability when you're doing something with motors, of course, so for initial testing, you really want that. But often gas generators are, again, this more compact way to store energy. So the final machine is probably going to end up a little bit lighter, but it's just, the cost versus benefit that you get into, right?
Awesome, thank you.
No problem.
Okay, it's 11, but what we have after is a break, so we can do one more question, and then I'll head on to the break. Perfect. Nice hoodie.
Hi, Adam. You mentioned earlier there that there's some increased difficulties when operating the liquid oxygen pump.
Yeah.
I'm just wondering if you could talk a little bit more on that and what the challenges you guys are going to face.
Yeah, so I mean, with liquid oxygen, you basically have two major challenges. One is material compatibility because it's an oxidizer, that's why we use it, but it means it really wants to oxidize things. So finding materials and designing the overall pump in a way that you minimize the opportunities for something to start a fire is super important. The other aspect, of course, is it's cryogenic. So now you're dealing with really severe temperature gradients. So compared to room temperature where you're machining your parts and building up the pump, you get it cold, everything is going to shrink down. So you've got to look at what's going to happen when that occurs and make sure that nothing is going to start rubbing, nothing is going to get too tight. So suddenly you're not just focused on room temperature conditions, you've got to look at this complete range and make sure that nothing is going to occur under any corner of the conditions the pump experiences that could lead to a bad day. So that's sort of where that comes in.
Beautiful. Thank you, Adam. One
My
round of
pleasure.
applause for Adam, please.
Thanks, everybody.
If you think it's hard to build a turbo pump, try to do it with a decentralized team of volunteers. Crazy. The project management in this man is very impressive. Thank you, Adam.
Thank you, sir.
Okay, so now we have a 15-minute break, and we'll be back with Cesaroni at 11:15. So if you're interested in talking about commercial solid rockets and engines in Canada, see you at 11:15. Okay, it is 11:16. We will be starting with our next presentation for the day from Cesaroni Technologies, which is a maker of solid fuel engines in Canada. So if you're interested by that, please come back to the conference area for a presentation by Cesaroni Technologies, or CTI as they're known in our rocket family. Do we have our speaker, William Peary? Okay, so as we wait for our speaker, I'll introduce Cesaroni Technologies. Cesaroni Technologies is a leading manufacturer of rocket propulsion systems and related aerospace components, known for its innovative solutions in the field of solid rocket motors. I know there's a lot of teams here competing in the basic category. They're essentially all firing Cesaroni Technology motors. With a strong emphasis on research and development, the company serves a diverse range of clients, including aerospace organizations, defense contractors, and commercial space ventures. Their products are recognized for their reliability and performance, making them a trusted partner in the advancement of space exploration and defense technologies. And with a beautiful smile, we have William Peary coming to the stage representing CTI. So your slides are there, and you can say next slide.
Thank you very much. That was definitely a very good introduction, better than I could have planned myself. So thank you very much. It's a pleasure to be here, and today I'll just be going over our broad range of solid rocket propulsion products, so you can get a sense of what we do and how it relates to the aerospace industry in Canada, and the other aspects of integrating rocket motors in anything other than just a launch vehicle. So, okay, the mouse, click, come on, slide. Hey, there's me. So about me, I have been working at CTI for the last year and a half. I started on my internship, and I'm back again for this summer. I started out working with Adam on his liquid rocket project, and eventually and with Mach on their liquid rocket, and eventually I was persuaded to go over to the dark side and work on solid rockets, because initially I didn't think they were as fascinating due to their relative simplicity, but I soon learned that it's a fake simplicity, and the real complexity lies within the motors themselves and the propellant. So what we do, we were founded in 1985 as an automotive R&D company manufacturing heat exchangers. And after that, we began producing ammunition products and that use a composite blend of polymer and copper to make a lead-free round of ammunition. And we've then subsequently started solid rocket production with the ProX line, and then quickly devolved into working on professional rocket solutions for a variety of customers. So here again, we have our heat transfer unit, the bullets unit, the test equipment unit, and aerospace, which are our 4 production units. I work in the aerospace, believe it or not. So we start off with our line of ProX motors. I'm sure you're all familiar with them. So they're a low-cost, consumer-grade line of rocket motors of various shapes and sizes, and they're meant to fill the need for hobby rocket people in both Canada and the United States. And we have a global dealer network, and they're recognized as the largest hobby rockets that are commercially available. So now we move on to the interesting stuff, commercial rocket propulsion products. This is our current lineup of propulsion products with a human for scale. Thank you, Daniel, for making this last year. And you can see on the left, we have the smallest motor we make, which is a parachute extraction motor. And on the other side is the largest one we make, which is a 16-inch, the Spider Stage 1, which is going to be used for a small launch vehicle with NASA and the DoD on the coming years down in New Mexico. So you see one of our most famous customers is Up Aerospace. You can see here's the Spaceloft XL rocket, which was used for the NASA Flight Opportunities missions back in the 2000s and currently to today. So we've had over, I think, 13 successful launches with a variety of customers. And yeah, here's a video that won the GoPro Awards for the rocket launch. Let's see if I can click it with this remotely. Okay, there we go. Maybe the audio will work. What on earth? An ad? Why? Why? It's not skippable. Daniel. Well, now we got oh, GoPro. Okay, let's skip ahead a little bit. Okay, there we go. This is launched in our spaceport facility in New Mexico. I believe that facility was originally owned by SpaceX when they were working on their early Merlin 1 engine. And we bought it up, and now we use it for testing our solid motors. And if you ever go to Spaceport America Cup, please don't launch your rockets into our facility, because that happens often. Very close. So you can see here, it's a 10-second burn duration, single stage. It's suborbital, as all Canadian rockets are. And as you can see, there it goes. So I actually just stuck a GoPro to the end of it. And you can see it's spin stabilized, which means that it doesn't have any active TVC control, which is what you want in a low-cost sounding rocket. Now what you'll see subsequently is the de-spin operation, where similar to the way that a skater extends their arms, it retracts cables, which then slow the spin of the vehicle down, allowing it to perform data acquisition on its payload. So you can see here, it's steadily accelerating, well, decelerating above the, and now above the carbon line. And we have stage separation, so the payload can now perform data acquisition in space. Those are the cables that were initially doing the de-spin. And there goes the nose cone. And now here comes a 1 in a million shot. That's why they, where the separation of the main stage from the booster. So they use a pyrotechnic charge here to separate them, and you'll see it right now. So then the rocket motor plummets back to Earth and embeds itself in the ground like a big long dart, and the top stage has a parachute system that will allow it to appropriately land. Slightly softer to preserve data. So that's pretty much all there is to it. Okay, let's see, can we move slides? Oh, there we go. Yeah, so with this Up Aerospace Space Loft XL motor, we developed it in Toronto. And here's the initial, I believe this is the static fire video. No, another one. Let's skip ahead this. I don't feel like watching another one. Come on. Okay. So in the commercial aerospace division, we have multiple phases, starting from the design, propellant manufacturing, component and hardware manufacturing, and subsequently testing. We also work on a variety of hybrid propulsion systems and gas generator systems, although currently we're doing less of that, more and more. With solid propulsion compared to liquid propulsion, you'll note that it's very much an act of production and having a long-term sustainable goal of testing a single batch and extrapolating that in the future. Whereas with liquid propulsion, you test every individual component indefinitely, and you run the final article. Whereas with solid propulsion, it's much less that, and more determining a long-term design that you know will work even though you can't physically test it. So you can see here are some examples of our design. You have to see CFD on, or FAA on a grain, because when you're traveling at Mach 2 and you're accelerating, you need to make sure that the propellant grain itself can withstand the acceleration and the shear force that it exerts on the grain. You see also propellant characterization here. And then we have a variety of propellant manufacturing facilities. The one in Toronto is the top right, and we're fully licensed for class 1.1 and 1.3 explosives, which is the most important thing to developing solid propulsion, is the regulatory and the licensing. Because in Canada, you have to be following all of the explosive regulatory division of Transport Canada and making sure that you're in check with all of their stuff. Otherwise, you will be in a lot of trouble. And this is what I spent most of my time doing, which is case manufacturing. So you see here, we have a 4-axis filament winder, And the cases that are made of composite, we've got basically just CFRP, and you wind it on, it creates a case for the rocket motor, a component that withstands the pressure and the axial and hoop stress of the motor while it's under pressure, and allows it to be used as not only the pressure vessel for the motor as the propellant's expanding, but also as the structure of the vehicle sometimes. Again, in order to categorize the propellant and the motor when you finish designing it, you have to do multiple static fire tests. In fact, the main thing that you do with solids compared to liquids, well, you do both technically, but a lot of static fire tests in order to extrapolate and then determine how it'll work in the future. Because you can't test everything single use, and so you have to figure out how to make it multiple, understand the future behavior given the present. And so we have mechanical testing, we have environmental condition, accelerated aging, beyond just the aerospace engineering degree, which has done that already to me, and then hydrostatic testing for the propellant, for the case design, as well as vibration and mechanical testing. So here is a static fire of a 6.5-inch sled motor taken down in New Mexico. As you can see, there you go, rocket motor. Very short. The idea for a sled motor is you maximize thrust and minimize the burn duration, because in a steady or in a horizontal flight, horizontal condition, you want to maximize thrust, reduce weight, but it's less important than when you're flying because your ISP doesn't make much of a difference. So yeah, again, very shiny. However, it's steel, so it's a slightly lower performing than our phenolic nozzles, which don't look as good, but are much lighter and better performing. So yeah, onto this topic, rocket sleds. So sounds very Canadian, but it's a lot more interesting than what it sounds. So typically what you do with a rocket sled is you have a 4-kilometer test track, just a random length, and you have a series of rocket motors that are put on the sled and fly it down. Now, why would you want to do something like that? Well, the main reason is to do dynamic testing of various test articles. So in the case of one of these rocket sleds, you could test anything from a ejection seat to a nuclear warhead for structural testing. So again, these are very common in the defense industry and something that's in a lot of need right now. And you can see the economic benefits of doing something like this because it's much cheaper to test an F-35 on the ground than it is to test it in the air and lose $500,000 testing it, right? So anything that needs acceleration or high-speed tests, you can use these for. So we also have a series of military training missiles. So these are for low-cost supersonic missile targets. So they're fired at like an aircraft carrier or a naval ship, and they're shot down and they give you a score. Very straightforward, but very difficult to do in terms of the optimization of something so small. Because the smaller you get, the more your rocket case weighs with respect to your propellant. So with something like this, you really need to pare down the weight of the case and maximize the performance of the propellant. So that's a very challenging design problem. And also you have to do that while making it low cost and very repeatable. So an older thing that we did back in the 90s or early 2000s was the AWS. It was an affordable weapons system. And so we developed it was a low-cost cruise missile development project. And we manufactured the boost motor for that. So as you can see, as it's flying there on one of the pictures, you'll see that initial rocket firing is launching the cruise missile out of its launch rail, allowing it to go on its planned flight. Now it's just for tests. Okay, the other thing that we did was deep Crowley boosters. So typically when you're on an aircraft carrier or a ship, you don't want to be shot at with missiles. So one of the ways to avoid them hitting you is by firing a secondary missile off of the ship and using it to trick the heat-seeking the head of the missile so that it will miss your ship altogether. So we designed the boost motor for Thales in UK for this one. Very interesting. So another interesting thing we worked on was the Instanize program. Now this was, again, you can see it's a little dated, just 5 megapixels photographs, but back in the day that was pretty interesting. So the idea was that you could have a hand-launched rocket that would essentially fly off the ground take 5-megapixel photographs in all directions and give you immediate situational awareness on the ground. So as you can see nowadays, you'll be probably replacing that with UAVs, but back in the day, you'd had very limited means of doing that. So a solid rocket motor would be a very good way of testing something like that. You can see there, it's on our static fire stand where we're characterizing the thrust. This is with a load cell and a pressure transducer and everything you might expect. Another thing is parachute extraction, and you'll probably see a lot more of this in the future. A UAV flying unattended can potentially encounter some issues. So if you're going to crash and you're above people, what you want is something to prevent you from hitting the ground hard. So a parachute extraction motor works very well. The idea being, instead of a drogue chute, you have a parachute that is yanked out by a rocket motor, and it will prevent your vehicle from hitting the ground. So we developed this parachute motor, and we made it for the Finnish and Swiss Air Forces, and we supplied it for a number of years. And I have one on display over there if you want to look at it. Another thing that we did, we worked with NASA in the past on a couple of projects. We did the only ever flown aerospike nozzle. It's basically a Pro 150 with a custom-built aerospike. And we also did tests on upper stage launch vehicle components. So you can see the case there. I have a version over in the display area later if you want to see. It was a long burn, so about 14 seconds burn time. Very, very thin, very light. The idea being that you could have improved insulation with higher erosion capabilities. So it was testing that insulation, which is very similar to the ones that they're using on the 5-segment SRBs now for the Artemis program. So here's a test fire of the upper stage. Now, we're dealing with usually 2 seconds or up to 10 seconds of burning. And typically you'll encounter combustion instability with something this long. So you can see here's the demonstration test back in our Toronto facility. And that's a very long burn duration. Now you see a little flutter, some very low frequency combustion instability, but nothing catastrophic. So it was a fairly successful technology demonstration. And there it goes. Yeah. So all of that beautiful gas is just going into Gormley, venting it out. And nobody ever calls the fire department for some reason. I don't know why. Yeah, so that's that. Let's see. So the one I spent most of my time working on was the Viper program. So I actually brought one in on the floor over there. So this is the largest rocket sled manufactured in Canada. It's a 17,000 pound thrust rocket motor. In my time at the company, I started back on case 3, and we're now on like 75 or something like that. So we make a lot of them and we sell them. And so that's 2 things you don't hear typically in Canadian rocketry, which makes me very happy. And I've been involved in a lot of the filament winding of the cases and also testing. I was there for all 6 static fires. And the one that we have over there was static fired on the 4th one. So here's the static fire of this. Again, 17,000 pounds of thrust. That's all very hot. You don't typically see that in anything other than commercial rocketry. Again, only 2 seconds of burn duration though, because it's meant to go from 0 to 60 0 to Mach 3 in 2 seconds. Which is a little faster than most sports cars. And that was just north of Toronto, so there is stuff happening in the city. And if you know where to look, you can get a job working on it. Yeah, it's much louder in person. Right now you can't hear anything. But there's a difference between a small motor and a big motor. When you're listening to an actual rocket launch, as opposed to a sounding rocket, you get the feeling like pushing through your chest. You definitely get that with this. So yeah, that was the 5th one. We did, I think, 6 static fires of this. The other thing we work on is gas generators. If you're familiar with turbo machinery, you'll realize that they have to start spinning somehow. And having a gas generator is one of the ways you can do it. Basically just expanding gases through a propellant. Typically you use phase-stabilized ammonium nitrate. And again, we've made it for certain things. We've made it for the AM-9 Sidewinder missile system, a couple of refurbishment programs for the, where we've replaced old gas generators for steering missile subsystems. So you see the missile on the left is a Trident II ICBM. Those, for instance, use gas generators as part of their thrust vector control system and also for their launching system as well. Yeah, and now onto some hybrid motors. This is something we haven't done as much lately. However, in the past, we've done them quite a bit. So we designed classical hybrid motors with gas generator and nitrous oxide systems. The one on the left, bottom left is the Hyperion sounding rocket. We did that flew that in NASA Wallops in the late 90s, and worked with a couple of other companies on other large-scale ones. So we developed the Hyperion 1 and the Hyperion 2, and they were all just conventional hybrid motors with propellant grain and nitrous oxide. So a more interesting hybrid we designed is a staged combustion aft-injected hybrid. This one was originally a development project for the Canadian space, or for small Canadian launch vehicle. And the idea being that you had a solid propellant gas generator operating just on the cusp of being on and off, and you would allow that to have a very throttable, very efficient hybrid without the need of any complex turbo machinery, and that really lowered the cost and raised the efficiency, making a hybrid something that was actually potentially feasible for a full-scale launch vehicle. And you could also gimbal it much easier than without any need for any flex sealing or anything complicated like that. Okay, now we just go on to the other reason you might want to be listening to this, is we have internship opportunities and sponsorship opportunities. So we have a ProX Motor Reload Kit we give out as a sponsorship, and also, more importantly, the internship opportunity. So every year we hire one intern between their third and fourth year. That's how I started out here. I was working as an intern, and you get really, really hands-on testing and manufacturing experiences. So if you want to apply for an internship, please apply to Daniel Tetman or dtetman at Cesaroni.net, and he'll be around December and January is when we start choosing people. Really interesting opportunity, and you'll get to do some pretty hands-on experience with a rocket company that not only designs and manufactures rockets, but sells them as well. And so you can see the difference between a commercially viable rocket company and something that's more just experimental. So you get a bit of both. So a lot of realism and some pessimism thrown in with the excitement of developing something new.
Thank you so much. Beautiful presentation.
Thank you. So does anyone have any questions?
So we have about 6 minutes for questions. If we have any questions in the audience, and maybe I can start with one. I honestly was very surprised at every year at the breadth of products that you sell and you work on, from hybrid engines to parachute ejection motors to gas generators. It's huge,
yeah.
And it's amazing that a lot of that is being done in Canada. And a lot of those engines require one same component, which is the nozzle.
Yes.
And a lot of students here are working on their own nozzle concepts, and I know this is a challenge in student rocketry because nozzles are hard with erosion and materials. Could you speak a little bit more about the approach that Cesaroni takes with regards to their nozzle and their development?
Yeah, well, I can't speak on it to a fully technical perspective. Yeah. However, I can somewhat go into it. So with certain low-cost motors, again, with nozzle design, it's all based on really on economics and what the customer is willing to pay for. So something like a stainless, or it's just a steel nozzle. The simplest you can get. It's steel that's been machined in a lathe, and you install it into your rocket motor. And because it's steel, it has a fairly good heat capacity, and for your short burn durations, it'll withstand it. Now the downside is it weighs a lot, and so as a result, your performance is limited. Then you move to something where it's like a phenolic resin, and those are higher performance and lower weight, but they cost more. And so you'll see in the ProX motors, they use typically a lot of the phenolic materials because we manufacture them on a fairly large scale. But when you're dealing with higher performance ones, you need higher pressure capabilities, which means you need to do a little bit more than just manufacturing the phenolic piece itself. And you might need to install like aluminum fixtures as well. So if you look at the one that I have on display, you'll see that it's got an aluminum pressure backing as well as the phenolic embedded internally. So we have a proprietary method for manufacturing that on a fairly large scale.
Amazing. Thank you. Very good answer.
Any other questions?
Any other questions from the audience? We have 3-4 more minutes. So if I can have a follow-up question then.
Yeah.
we saw a few test sites. We saw one with a Canadian flag and a few with American flags.
Yeah.
What products are developed and made in Canada and tested in Canada?
Well, yeah, I'm not sure how much I can go into it, but typically we manufacture, like, I'd say 80% of our components in Canada, and the United States is typically I'd say it's a smaller group of people, and they're working on more high-level development projects. And again, they're not allowed to tell me anything about it because of ITAR. So I don't know I don't know exactly what they're doing. They're doing some stuff. It's pretty cool. I've seen videos, but beyond that, I mean, not too much that I've worked on down there. But a lot of the rocket sled production, like on the Viper, for instance, we manufacture that in Canada. So all of those I was working on, or we were working on them, and they're all made in Toronto.
Makes me very patriotic. Thank you.
Yeah, thank you.
So if you have no other questions, then a round of applause for William. Thank you very much.
Thank you. Hey, guys.
All right. So it is 11:45 approximately. It's 11:42. We need a few minutes just to prepare our next speaker, which will be Joe Cassidy from L3 Harris. He will explain the Artemis Moon to Mars campaign and how it will prepare us to go to Mars. So an amazing speaker that we're very lucky to have in about 3 minutes. He will also join us virtually. So for those that don't know, Aerojet Rocketdyne was acquired by L3 Harris. So when I say that Joe Cassidy is from L3 Harris, he is also stemming from Aerojet Rocketdyne, which you probably all know very well as a very famous and known rocket company. So we'll be starting in a few minutes. I just want to take the occasion to also say hello to our live stream audience online. I know we have a couple of dozen people on there, so hello and thank you for attending virtually but still being there. And hopefully we'll see you in person next year. So I'll do it or you do it? I do it or you do it? Okay, good. Okay, so it is 11:46
I will start with a brief introduction while people are walking in for the presentation of Joe Cassidy from Aerojet Rocketdyne, accompanied by L3 Harris Technologies. All right, welcome everyone. So, a little introduction, but first, do we do the sound check now, or?
Can you say something?
Yes.
Okay.
Okay. We can hear you as well.
Okay. I'll just try to talk normally. How does that sound?
That's okay. We get a little bit of feedback. A lot of feedback. Maybe I can cut the mic in the front. Oh.
The feedback's coming from me. I'll turn my mic off.
Okay. How's that now?
That's pretty good. Awesome.
Oh, great. All right. Thanks.
I can't. Oh, okay, perfect. All right, so welcome everyone. We are welcoming today Joe Cassidy. He is an executive director for space propulsion and power systems at Aerojet Rocketdyne and L3 Harris Technologies company. His role includes working with NASA and other customers on emerging technology and space exploration programs, so very relevant to today. Most notably, the Artemis program to return humans to the moon and prepare humans to Mars. Interestingly, we have a Canadian going on the Artemis mission, so he is directly contributing to Canada having some space in deep space. He is an avowed Martian and wants to see the first humans land on the surface of the red planet before 2040, and the clock every year is ticking. He is a corresponding member of the International Academy of Astronautics, an associate fellow of the AIAA, vice president of the Electric Rocket Propulsion Society, and executive vice president of Explore Mars, Inc. We are extremely lucky, and I insist on that, to have him here presenting his talk, the Artemis Moon to Mars campaign, and how it will prepare us to go to Mars. Everybody, please give a warm welcome to Joe Cassidy. The floor is yours.
All right. Thank you. Thank you very much, Cyril. And thanks to Adam and the organizers for inviting me back to have a chance to share with you some of the progress that we are making on the Artemis program. I'm sorry I can't be there in person this year, but hopefully next year again. So let's start off recap. When I was up in Timmins last year, I showed you some of the video from the Artemis 1 flight. So we've now had a chance over the past year or so to review all the data we got back from that flight, that test flight. You can see some of that here on this slide. I won't go through any of the details, but suffice to say, we met all of our test milestones and objectives. We had a very good test flight, and we feel very confident that we're ready to support a flight of humans on Artemis 2 that's going to take us back to the vicinity of the moon for the first time in over 50 years and go farther than we've ever gone before. And as noted, that will include a Canadian. And so we're super excited about that too, and the role that Canada is playing in all this. So I'm just going to show a video now, and I'll talk over it a little bit. I hope it comes through. It might be a little choppy. When we did the test run, it was coming through a little choppy, but hopefully you can see some of the evidence of what we're up to. Oh dear, I touched it twice. Let me go back. That's operator error. There we go. All right. So we'll play the video. So what you're seeing now is booster stacking that's going on down at the DAB in Florida. And then over in Michoud, we're building the core stage for Artemis 2, and that's now been completed. Those are our RS-25 engines. There's a great shot of an RS-25 being put on. We're putting all this hardware together now for Artemis 2. That core stage has already shipped to Kennedy on the Pegasus barge. It's now there now at the DAB. This is the stage adapter. Here's now Artemis 3 hardware. This is the interim cryogenic propulsion stage for Artemis 3. And this is the CubeSat nest on Artemis 4. When we go to the Block 1B, we're going to fly a lot of secondary payloads and CubeSats. This is the exploration upper stage being put together down at Michoud, as well as the core stage for Artemis 3. So I guess the point of all this is just to say we're not sitting around while we're getting ready for Artemis 2. We're building a lot of hardware that's going to support the Artemis 3, 4, and even 5 missions. So we're moving forward all the time. There's a lot of work going on. So what are those future missions? Obviously, the goal of this is to prepare us to go back and land and put humans on the surface of Mars again. At the same time, we have plans to do some things we never did before with Apollo, which is we're going to build a deep space station called the Gateway. Canada plays a big role in that too with the Canadarm. I believe CSA now has the contract in place and work has started. And so that is another exciting contribution coming from Canada for the Gateway. And the thing I really love about the Gateway is it's an orbiting space station around the moon. It's a jumping off point for getting us down to the surface of the moon in a sustainable way, so we won't be just, you know, throwing away all the pieces of the lander that we used to go down to the surface. We can actually use it to refuel elements, and it gives us the ability to test systems like environmental control and life support systems in deep space that are going to be the precursors for what we use to go to Mars. And that's really where I see a beautiful tie-in between what we're doing going back to the moon and what we're doing getting ready for Mars. So go on to the next slide here. There we go. So there's our crew for Artemis 2. We talked a little bit about that. First time we're going to have humans out of low Earth orbit in a long, long time. And this crew is just so representative of humanity. I think it's wonderful to see the crew they picked, and they're a great bunch of folks. We get to go around now as they're training and doing a lot of work to prepare for their mission, which is going to launch next year. They get to go and visit a lot of places. And one of the most, fun things that I get to do is go sometimes with them to visit suppliers, people that are making all the components and pieces of this to make it a reality. And it's just so neat to see the reaction that they have. And I know Jeremy Hansen is definitely a rock star up there in Canada. So we're so excited to be getting these guys ready to go back out and visit the vicinity of the moon again. I think I'm going to another video now. So I'm going to let this play. This is our kind of exciting, get everybody's pulse pumping for Artemis 2. Obviously, we've flown the test flight here. That was the launch of Artemis 1. Pretty powerful rocket. Orion proved itself out marvelously on that first test flight. And we're looking forward to having the crew go out there and then come home safely through that re-entry corridor at 30 times the speed of sound. So every time we watch that, I don't know, I've watched it probably a few dozen times. My pulse rate always goes up every time I watch it. So let's talk a little bit then about where are we going beyond Artemis 1 and 2. So obviously 2 we'll fly around the moon, demonstrate that we've got all the things working the way we want them to work. Everything worked well on Artemis 1. The real proof in the pudding is when you have the people on board. And so that's what we're going to do with Artemis 2. Artemis 3, we developed the lander element as well and go out, rendezvous in lunar orbit with the lander and go down and do that first human surface landing in, as again, I said earlier, over 50 years. It's been a long time. Artemis 4 is when we start to build the gateway. And that's the one, as I said, we're really starting to do things there that get us ready to go to Mars. Building this capability and having the ability to have a space station in deep space, not just down in low Earth orbit, allows us to prove so many of the things we're going to need for a transit to Mars. So that's really exciting. There's a lot of science that we're going to do, even on the gateway, with things like radiation monitoring, looking at stuff like the viability of food supplies for long trips to Mars, and drugs, all of those kinds of things. We've got to know those are going to be good before we send people off on that 2 to 3 year journey out to Mars. And that's what we're going to be able to do with Gateway. So that starts with Artemis 4. Artemis 5, we get even more capability out there, including surface mobility. So we're going to develop a couple of different rovers to allow the astronauts to move around and explore even further from the landing site. And that begins the actual process of building up capability down in the lunar South Polar region, where we can, eventually have a base of operations, and we'll be able to start to understand better what those resources are that we can take advantage of for future missions. And we're hoping, for instance, that there's, evidence of water, ice there. We'll be able to use that to break it into hydrogen and oxygen, and obviously hydrogen, very useful as a rocket propellant. Oxygen, a good oxidizer for rockets, but also breathable air for astronauts. So that whole ISRU, or in situ resource utilization, is one of the big things we're hoping to prove out with these first sets of missions and building into the latter part of the decade, Artemis 6, 7, and 8, as we start to build up that outpost on the surface of the moon. As well as each one of those Artemis flights after Artemis 4 has a 10 metric ton payload capability in addition to Orion. So we're going to be taking pieces of the Gateway up that are coming from our international partners. So we have an international habitat that will be built by ESA, and that'll ride up along with Orion on Artemis 4. Artemis 5, I believe, delivers the Canadarm to Gateway. So we have a plan for each of those missions to take not only Orion and a crew out to do a landing mission, but also to take more hardware up to build out the Gateway. So it's a very exciting time. And I believe I'm done with that presentation. I'm going to try to share with you one more here, and bear with me. I've got to pull up a different video. I just wanted to show you a little bit of the Gateway video. Are you seeing that okay on your end?
Yes, it's perfect. Thank you.
Okay, great. So I've kind of cut to the chase here. I start right here because, look, there's the Canadarm. But I'm going to play it and see. It might make you a little dizzy. They've done this in a way where it wouldn't be good if the Gateway was actually spinning this fast. Our reaction control system wouldn't be doing its job, but it's for effect. So let me see if I can get this to play. Maybe not. It might have locked up on me. There we go. Let's see. Try one more time here. Shucks. Well, at any rate, there's the Canadarm. I think this video doesn't want to cooperate. So I'll stop there and be happy to take any questions that you might have there from the audience.
Amazing. Thank you so much for this beautiful presentation. Everybody, please applause. So we now have an opportunity a very unique opportunity to ask questions to Mr. Cassidy here. Anyone here interested?
Hi. Are you worried about budget expenses like what happened with the Viper rover?
Oh, good question. Yeah, so I'll start with the short answer. No. And I'll caveat that. I am worried overall that, you know, it's a tough time for budgets, obviously, with, you know, just overall government budget is always under pressure. What I would say is we're lucky. We've been through 2 presidential administrations. We're getting ready to have another election, you may have heard. So we're all watching that really carefully. But we have tremendous support on both of our houses of Congress for Artemis. If you look at the NASA budget and what happened there with Viper, the parts of the NASA budget that are, you know, getting hit the hardest are not the exploration parts. And that's due to the tremendous support we have in both the House and the Senate, the U.S. Congress. And I think we can count on that. I see that both the presidential campaigns have come out with statements that say they're supportive as well. So obviously, it's always a concern. It's a nervous time when we have a change of administrations like this. But I don't see any evidence right now that people are backing away. And I'll say one more thing. I think one of the great things about having international partnerships that we have, and Gateway is really representative of that because we have so many international partners participating, including Canada. Those are commitments that it's hard to back out of, you know. And so as a country, you know, I think we want to honor those commitments. So that's another reason why I feel pretty confident.
Great question, great answer. Do you have any other takers? Yes.
Thank you. I just wanted to ask, what role would you say that L3Harris's participation in the Draco program and nuclear thermal propulsion would have for the Artemis program going forward and that transition from the moon to Mars?
Thank you. Good question. So directly with Artemis, Draco and nuclear thermal don't exactly play into the Artemis program, but when I said what I said about Gateway getting us ready to go to Mars, one of the things we're really starting to look at is that transition from what we've done in the past, which is we build all the hardware on the ground and we launch it, and you know, like we go to the space station, it's 200 miles up, and so we can take everything, transfer it onto the station, do everything we need to do, come home in another vehicle, a Dragon, Starliner will come home eventually, hopefully soon. But you know, those kinds of things got to be pretty routine. What we're not ready to do yet is make that bigger jump for transferring large amounts of mass over greater distances, and that's where things like nuclear thermal really do come in. And I think Draco is the first step in that process. It's going to demonstrate that we can build that kind of system and launch it and actually use it in space. And then beyond that, I think we'll build an operational system probably in the 2030s. I think, you know, mid-2030s timeframe that would be capable of transporting astronauts from some starting point. And it might not be from low Earth orbit. That's the other thing that's great about Gateway is it's going to teach us how to do operations in an orbit around the moon that could be a very useful point for departures from the Earth-Moon system to places like Mars.
Great insight into the future here. Do you have any other questions? So I know, Joe, you work with a lot of international members, like you mentioned, and a lot of different companies and contractors, and this is a very, very complex task that requires a lot of moving parts. Do you have any advice on teams that are working here with multiple sub-teams, sometimes hundreds of students, different contractors, supply chains, etc., on how to lead a successful space project?
Yeah, oh wow. I would say one thing that we learned very early on is you can't over-communicate. Never assume that somebody understands something that you put out. It's always another thing. I think I learned this a long time ago. Read back things. This is almost like an aviation military pilot kind of thing. But when you give an instruction to somebody, it's always good to have them repeat it back and kind of make sure that they got everything in there. And the other thing is, it's always good to. I kind of have developed a systems engineering mentality over the years, but by managing a lot of projects and working in teams that were kind of distributed around the country. And one of the things that I think it's always good to do is define the requirements in a way that is completely understood on both sides, and then do what I just said. Check that. Go back and say, okay, here's what I think I told you. Now, and on the receiving end of that, say, here's what I think you just told me, and make sure that the two pieces are really coming together in a way that meshes, because that's where the interfaces are always where the problems crop up. And that's true whether it's an international partnership or just two parts of our company trying to work together.
Excellent, very good way to see things. And I love the you can't communicate enough. We're here to build together, so let's talk together. Any other questions? Yes.
Is there an expected time frame for the future Artemis missions?
Yeah, it wasn't on the chart, was it? So Artemis 2 is next year. I believe the date is no earlier than September of 25. I'd have to go back and double check, but I think that's the latest published date. Artemis 3 is about a year later, so in 26. And then Artemis 4, because there's a lot of pieces coming together and some of the gateway hardware and things like that, I believe now is early 28. And then beyond that, it should go to a cadence of one mission a year. That's really what we want to get to, is flying one Artemis mission a year, getting a crew out there to either gateway or the surface on an annual basis. So and that'll go right on through the early 2030s.
Beautiful. So it looks like the people here in this room will be a big part of that, right? 2030s,
absolutely.
2040s. This is going to be like the apogee of your careers, if you allow me the joke there. Well, thank you everyone for coming. If we don't have any more questions, one more round of applause for Joe.
Thank you, guys. And good luck in the launch.
Thank you so much.
Bye.
Okay, everyone. Thank you so much for coming. This was the last speaker for the morning. Now it is lunch. We'll be back at 11:45, so in approximately 30 minutes. We do have some options for lunch, so if I could welcome to the stage Shirley. If Shirley could come to the stage to explain our lunch options. So 12:45, please come back. We'll have a presentation on the human side of space exploration with Alath McIntyre. Okay, we have Shirley coming up stage to talk about lunch options for those that are hungry, and I am one of them.
Oh, yeah, so food should be pretty straightforward for today. We have two food options. One is a concession stand inside the Sportsplex, and we also have a very delicious food truck outside of the Sportsplex. Just to the right as you exit, you'll see them. And they have a lot of stuff available, from burgers, brisket, to wraps, and we'll be able to accommodate pretty much most dietary restrictions as well. So yeah, head on over to the food if you're hungry. Thank you.
Okay, everyone. So it is 12:46, 1 minute behind schedule. Apologies. The fries were something to put in my mouth. We are going to continue this now first day of the conference. So if those interested to hear the next side, the human side of space exploration by Dr. Lath McIntyre, please come to the conference area. At the same time, I'd like to acknowledge and welcome people on our live streaming channel. I can see that we have a couple of people there, so thank you for attending and thank you for your interest. So we're going to start in 1 minute or 2 minutes, so that's time for people to come on this side, and otherwise, hello to people on the live streaming, and thank you for sticking around. I will start by giving a short introduction to our speaker, in 1 minute. Okay, so I'll start with a short introduction to our speaker. So Dr. Lath McIntyre was among the final 72, that's my French coming out, 7012, 72 astronaut candidates out of the 3,772 applicants with the Canadian Space Agency in 2017, which was the last application campaign. After a Bachelor of Science in Biology at Dalhousie University and 2 years as an onboard marine biologist in Alaska, she completed her Master's in Space Science at the International Space University in France. At the Controlled Environment Systems Research Facility at the University of Guelph, she completed a PhD in Environmental Sciences on the implication of low-pressure conditions for plant-microbe interaction in a lunar or Martian greenhouse. She has participated in 2 microgravity flight campaigns and 2 analog Mars missions at the Mars Desert Research Station in Utah. Dr. McIntyre is currently a staff scientist with Science North, which many in Timmins know, inspiring the next generation of scientists with space exploration. And Science North is a group that comes every year and installs sometimes that planetarium that we get to see. So they have a lot of impact, and we're very, very thankful for them to be represented today. And so I'd like to welcome her to the stage, everybody. A round of applause for Dr. McIntyre.
All right, looks like we need to work on our signal. Reconnect. Yeah? All right. Ani, hello, bonjour. I just have to say, was really super exciting walking around and seeing all of these amazing university teams and the hard work, the results of your hard work, the rockets that you've built. It's super impressive, and I really appreciate you carrying on this work of increasing our capacity to go to space. It's awesome. So, I'm not here to talk about rockets. My talk's not technical. I'm here to talk about the human side of things, the soft, squishy part of space exploration. I went into sciences because I wanted to solve problems, and I wanted to help. We just had a launch back there. That's awesome. I wanted to help improve the quality of life for everyone on Earth. And I'm really, really interested in our long-term survival on this planet. But I also studied science because I wanted to leave Earth. I know not many of you are over here yet, but how many of you would leave Earth if you had the opportunity? Show hands. Yeah, there's a few of you. Awesome. Me too, totally. How many of you, though, already really feel it kind of deep in your bones that you're already in space? Yes, Zach. Because, yeah, for sure we are, right? This ball of rock is our spaceship, and we are all crew. There are no passengers, right? We're all crew on this spaceship Earth. And really, we do most of our space exploration from here on Earth, right? From satellites as well, from probes, from things in orbit around Earth, and now with the James Webb Space Telescope, things in orbit around the sun with us. But really, we're exploring the universe through the electromagnetic spectrum, right? It's hard to get our soft squishy selves very far away. The furthest we've been is the moon, and we're going back, which is super exciting. Yes, woo! But here in our spaceship, we are facing some major challenges. Things are not perfect. I would say some of those challenges are colonialism, capitalism, the military-industrial complex. Those things are leading to some really awful stuff, like the ongoing genocide in Palestine and what's happening in the Congo and the Sudan. And our spaceship is not running tickety-boo. We have a lot of work to do. And our long-term survival as humans on planet Earth depends on our ability to recognize these problems, to imagine the solutions, and to work to make those solutions real. And I know all of you out there, mostly on the other side of the curtain, have been working on that. You have been finding problems, encountering problems, imagining the solution, implementing it, making it work, and you haven't been doing it by yourself. You've been doing it as part of a team, which is another critical element in our survival, is working together. And not just working together in little teams with people who you share, the same culture with, but really recognizing that we're all humans, we're all on the same ship, we're all in this together, and we need to work together as like a planetary team, especially if we want to do space exploration. And I would say, for sure, rocketry is part of the solution. So you guys you're doing it, it's awesome, thank you. So you can't see him because my slides aren't up. Darn skipping the tech test. I was like, no, it's cool, it's gonna work. But I'm going to share a quote with you. It's by Buckminster Fuller. And what he said was, "It is now highly feasible to take care of everybody on Earth at a higher standard of living than any have ever known. It no longer has to be you or me. Selfishness is unnecessary. War is obsolete. It is a matter of converting the high technology from weaponry to livingry." I believe this with my whole being, and it is what I am dedicating my life to. But let me start back at the beginning, how I got here. So I was born in Stillwater, Oklahoma, but I immigrated to Canada before the age of 1. I had an unconventional childhood. I grew up on a commune, and it was wonderful. It was awesome. I had a good childhood, but I did have adverse childhood experiences, mostly off the commune. And to this day, I carry scars. I carry emotional scars, like intellectual scars, even physical scars. I've got crazy physical scars. But none of us have a perfect childhood. None of us grow up unscathed, but that doesn't mean we don't have something to contribute. We're all crew. We all have something to contribute. You don't have to be perfect to make a really important difference in this world. So I encourage you to find support. I know you have it because you're here, but to find people who believe in you, who support you, who tell you you can be and do whatever it is you want to do. Because if you believe that, you're going to go far. So I grew up in Lake St. Peter, Ontario. I went out to the East Coast to do a bachelor's in biology. And then after I graduated, I went to work in Alaska and the Bering Sea as an onboard marine biologist for a couple years. And I did that to test myself, to see if I would enjoy doing science in a harsh environment, in isolation with a crew, and I really did enjoy that. So I went from there, halfway around the world, to the International Space University in France. And they have an amazing degree. It's a really excellent program. I highly recommend it. They have scholarships for Canadians, so if you're interested in studying space, this whole big space industry, that's a heck of a lot more than astronauts, I highly recommend it. And what we really learned to do there is to work in international, interdisciplinary, and intercultural teams. And one thing that experience really brought home to me was that our differences, it's not really about like the color of our skin or the texture of our hair or what planet we're from. It's more about our cultural differences. Because I worked with Canadians who looked really different from me, but they were Canadians, and we totally got along. There were no issues, right? And then the challenges came from bridging the cultural gaps. And so I encourage you that, you will find people that share your values in other cultures, and to bridge those cultural gaps, and to try to work with people from around the world. We had cool experiences. As a team, we got to make a plan for terraforming Mars and colonizing Mars, which was cool. We did an intensive habitat design workshop with the European Space Agency. Ton of fun. We also got to visit Moscow, Russia, and we got to go to Star City, where they train astronauts. I have cool pictures of it, too. I wish I could share them with you. Amazing pictures. The last 3 months of that degree, so that's like a year-long degree, the last 3 months I got to do an internship at the Controlled Environment Systems Research Facility back in Ontario. They happen to be a world leader in life support systems. And I studied a breadboard system, so like a test system, like you guys are working on here with the rockets, that would take carbon dioxide out of the human habitation chamber, capture it, and release it into the plant growth chamber, so that we could create a closed-loop system. That internship, during it, I got to do a parabolic flight campaign, so I got to go to France. On a parabolic flight, your experiment and you get to experience zero gravity as you come over parabolas, so you're double gravity, over the top, zero gravity, and you do that 30 times. It's very fun. It's only like 30 seconds of zero gravity, but that was like a check experience I really wanted to have. And as a student, I got to do that. I also went on to start a PhD in that lab. So I studied plant-microbe interactions under conditions that you would expect to encounter in a greenhouse on the moon or on Mars. So big hypobaric chambers. And during that time, I got to do 2 Mars analog missions. Also amazing photos, I swear. But I went from Ontario to Utah. Utah does look like Mars. There's a habitat there. There's a greenhouse. And that greenhouse is taking the wastewater from the showers and dishes and stuff and using them to grow plants. So, I was out in the field. I was searching for microbes. I was growing salads and serving them to my crew. And I was basically living my dream. Like, that's what I wanted to do. I don't think I mentioned that at the beginning, but I set out to be a farmer on Mars. I grew up as a small-scale farmer on Earth. Small-scale farmers on Earth don't get paid to do what they do, really, not really. So I was like, well, I'll go do this on Mars, and that'll be fun. So I got to kind of live it, and that's the cool thing. Like, as a student, if you keep pursuing opportunities, if you keep looking for things, there are a lot of people who are encouraging it, and you're going to have cool experiences. So yeah, earned a couple more mission patches there. Going through my pictures. And then I did hit a few more major life milestones. Like, I got married, I had 2 kids, and Canada made the first call for astronauts. And I applied, but I didn't make it past the final 1,000. And then I did a postdoc. So I worked with the engineers at the University of Guelph looking at appropriate wastewater treatment for First Nations. And finally, I applied for a job at Science North. So if you haven't heard of Science North, it's a science center in Sudbury, Ontario. We might actually be the largest in Canada now. They're going to reopen the Ontario Science Center. It's going to happen. We're the second largest. And when I was doing the job interview, they were like, okay, so we've described the position, you've toured the center. Do you think you would enjoy being the staff scientist of Space Place in the planetarium? And I was like, yeah. Absolutely. Like, the only job I would take over this job is being an astronaut. And then we all laughed because, that's like wanting to be a rock star, right? And then that summer, the next call came. And this time I had a whole organization behind me who was like, yes, please do this. This would be great for our reputation. Like, get out there. Yeah, you can go to the gym 3 days a week. No problem. Like, do this. So I had support, and that was awesome. Nearly 8,000 people started that application to be the next Canadian astronaut. Less than 4,000 people finished it because it was a really long application. So that was in August. By September, 1,706 of us had passed the entrance exam, the government entrance exam, to qualify as an astronaut. By November, 163 of us had been selected to go to the next step. And to my incredible shock and surprise, I was still in. So there were 100 of us who were invited to go for medical exams. I went to the military base in North Bay for mine and passed it. I have heard, though, that, you only don't have a medical issue if you haven't been, examined by enough doctors. I'm not sure it is. Anyway, okay, so after the medical exams, there were 72 of us left. And we were divided into 3 groups of 24. We were invited to another military base in Quebec near the Canadian Space Agency to go through aptitude testing. So we were there for 4 days of just aptitude testing. So of those who made it there, we had 68% men, 32% women, all physically fit, highly educated, mostly, this is something for you guys out there, mostly engineers. So you're pursuing the right things. But also scientists like myself, doctors, and a lot of them were actually pilots on top of that. My beautiful mosaic of all our faces with me there for photographic evidence. You can find me on the Canadian Space Agency website. Okay, so what they were looking for, the sort of the skills and the qualities needed to be an astronaut are judgment, integrity, reasoning, teamwork, the ability to synthesize and communicate using plain language, public speaking, motivation, and resourcefulness. And I know these are all skills that you guys here, and also you back there who are working on your rockets, have all been really practicing, and especially the teamwork component. So throughout each of those 4 days, we didn't know if we were going into a mental challenge or if we were going into a physical challenge. And my most comfortable spot, my happy place, was the swimming pool. We spent a day in the swimming pool, and I love swimming, I'm good at it, and I was really having a lot of fun, and I realized it's because I felt like I was making good contributions to my team. I felt useful. I think we all enjoy that feeling a lot. So the assessments culminated in this grueling circuit that made us solve mental challenges while physically exhausted, emotionally exhausted, and of course working as a team. We had to work together. I have a beautiful image of Josh Kutrick and Jenny Gibbons, who were selected. Luckily, they were both in my little group of 24, and we had to have buddies, and Jenny and I actually buddied up. And by the end of the 4 days, I was honestly hoping that she would be selected. She is an amazing human being, and I'm so excited to follow her career in space, especially because she is the backup for the next Artemis mission, which is scheduled to fly no earlier than September 2025, but hopefully September 2025 we'll see that Artemis 2 mission launch and go around the moon. And Jeremy Hansen is first up for it, but Jenny's his backup, which is just super exciting. And they're doing a lot of really fun stuff right now. They're doing geology field training in Canada and having a good time. So I'm not going to space. But I do get to share my enthusiasm for space, communicate space science, and also climate action. That's a big part of my job now, too, which is very near and dear to my heart. And I get to hang out with astronauts sometimes. I have a picture of me and Jeremy Hansen that you can't see. That's okay. But really, most importantly, is I have a great crew, right? I'm working with other people, we call ourselves Blue Coats, who are dedicated to inspiring the next generation of scientists, engineers, mathematicians, people working on technology, even artists, And that's really what makes the day-to-day worth it, is part of being part of that great crew. So finally, I just want to encourage you to keep doing what you're doing. It's amazing. Rocketry is part of the solution. We do need Earth observation, for sure, to understand what we're doing here and to run this ship. And so you're all doing great work, and we need the scientists, the engineers, the mathematicians to run this ship, and really, eventually, to take us to new worlds, because Earth does have a limited existence, for sure. So keep looking up. Miigwech, thank you. Merci, and I'm very happy to answer any questions you might have.
Thank you a lot. So you left us on a little cliffhanger there. So if I can ask the first question there, you mentioned that Earth had not a lot of time left. Can you indicate to us what is that tied to and how much time we have left here?
Yeah, what am I referring to there? So what I'm referring to is the lifespan of our star. Stars are born, they die. Our star is like a yellow dwarf, kind of like middle regular star, and it's in its midlife right now. It's halfway through its life. So in about 5 billion years, we expect it to sort of use up its hydrogen, collapse, and then start nuclear fusion again and expand into a red giant and engulf the planet. So we're not going to survive that unless we figure out interstellar travel, hopefully.
You said 5 billion, 5 million?
Yeah, we've got time.
Okay.
We've got time.
We've got a few gray hairs by then.
There's some other like more immediate threats to deal with.
Fantastic. So I'll take any questions from the crowd. If we have, I'll come to you. And I just want to thank you for your patience with our AV system. Of course, we're having some difficulty. And I know you had some beautiful pictures. This is on the fly. We're still learning.
Yeah, sorry I kept bringing them up, but they are amazing. You can come see me after. I'll show them to you.
Hey, good talk. Thank you. You said, "Oh, I'm not going into space. Why is it? It's never too late. Why is it just this time? Couldn't you try again in 3 years or?"
Yeah, that's a great question. Well, I am 45, so it's a bit late to start the training. Like the investment is, it doesn't really. But I guess I haven't completely given up the dream. I'm kind of excited that Timmins has a stratospheric balloon facility. I don't know how many of you are aware of this, but there are 2 companies right now that are taking people to space with balloons. And I'm thinking maybe it'd be cool if like Timmins could kind of upgrade to humans to space in balloons. I didn't want to talk about it because we're doing rockets, but I would take a balloon to the edge of space, given the opportunity.
And I think that if you were to put any of us, even the Klingons, in the rockets that we have here, there wouldn't be much human left. So the balloon makes a lot of sense. Absolutely. I remember that. Absolutely. Do you have any other questions? I do have here.
I got just this quick question. In your speech, you mentioned about your enthusiasm for the environmental science and environmental conservation. I was just wondering if you could tell us a little bit more about maybe your more recent work in this field. Because personally, I'm really interested in the topic of the environmental science.
Cool. Yeah. So my recent work towards like environmental conservation. Through Science North, I was able to help develop we call them object theaters. So it's like a 20-minute experience that visitors come into. And we've actually had a climate change object theater at Science North for the last 20 years. And I got to work on the newest version of it. And we set it up as like a training. So you go in and you're like in a barn and sheep are training you to be a change agent. So like someone that sees the change that needs to happen in the world and goes out and makes it happen. So we have, and there's like a pledge you can take and a website. So we've had hundreds of thousands of kids have been through that experience now, and we've shown them the graphs and we've shown them what's happening. And then that led to us actually getting funding from the government to do a traveling tour that's been traveling across Canada and going to different towns and stuff, and it's all about climate action. So that's been kind of the recent work, and then I am hoping eventually to transition into actually building a life support system on the land that I grew up on. So that's like my long-term dream is to kind of have a facility that people, like an analog facility like the one in Utah, where people kind of come through and they try to push the system to its limits, and we see if we can really create a sort of closed system that can provide, clean water, food, even clean air, right? As the forest fires get really intense, we might need these shelters where the air is getting purified. So that's the direction I'm going.
And you're going to be building this around the Timmins area, this life support system?
I'm hoping it's more southern Ontario, the land I grew up on 250 acres and had a good view of the night sky. I think that's sort of what shaped me, and I hope to get back there.
Beautiful. And this life support system will be able to simulate which types of conditions? Will we be able to do pre-breathe? Will this put us in situations where astronauts can actually get training in such facilities?
I would love for it to be like that, yeah. So it could kind of replicate a scenario you might, not replicate, but be analogous to a scenario you might encounter on the moon or on Mars, and where we could study the crew dynamics or just the emotional response, right? Like, food is at the center of our cultures and our sort of identities, and so how do we transition to living off of food that we can produce in a closed loop system? What does that look like?
Wonderful idea. I love it. Yes.
Once again, congratulations on doing that tour with that and the number of people. I was curious about, is there a sweet point in regards to the number of members of a crew travelling a distance to, say, Mars?
Yeah.
That was next, if you were doing it direct Earth, not via the stage, via the moon, in terms of the amount of fuel required for that length of journey and then to survive X period.
Yeah, so I mean, we keep hearing about cruises of 6. 6 seems to be kind of what we're landing on. But when you think about a life support system, like once you want to start develop running a system, is 6 people enough, right? Because there is we're on Earth. Earth is our life support system, and basically what we're trying to do, like they did at Biosphere 2 in Arizona, is shrink that life support system down. And it's what is the minimum viable size? Probably more than 6 people. So our early 6-person missions are probably going to be very dependent on mechanical life support and packed food. But I'm hoping that biological element will be there, even just for our mental health and well-being, right? Because we do see astronauts, keeping pet onions that have grown and stuff on the space station. Plants are really a key element to our mental health in space. So I think we'll want them.
It's a very good point that you're mentioning there, where plants play a big role not only in our physical well-being but our mental health well-being. I was speaking to some crew that went on the ISS, and one of the interesting tidbits of information that I heard was their favorite place was the garden, and they would actually not only go to the garden but put their head into it to smell the earth, because that's the smell that they miss. So that plays a big role in mental health. Thank you for bringing that up.
Absolutely, thank you.
Do we have any other questions from the audience? Well, in that case, thank you very much. One more round of applause, please. So we're going to wait a few minutes to try to see if we can still resolve this AV issue. We're currently troubleshooting it, so we do have a break after our next speaker. So I'll see if we can take that break, maybe to push it a little bit off and see if we can have more time to resolve this issue.
Okay, it is 1:20. So we're gonna start in about 10 minutes for our next speaker at 1:30, which is Rahul Goel from North Space. Company started in 23, planning to launch orbital rockets. I will go into a detailed bio in a few minutes, but if you're interested to talk about Canadian orbital rockets and possibly opportunities in Canadian rocket companies, please come to the conference area. So I'm repeating myself, but at 1:30 we'll have the presentation by Rahul Goel for North Space. Okay, so in 3 minutes, we'll be starting with North Space. 3 minutes of the conference part. For free beer. On you? What I say is legally binding though, so if you're offering it. It's gonna show your slides there, and then you can. So you have your own reference. Okay, so 129. I'll start with an introduction of our next speaker. We're very lucky here at Launch Canada. We have a range of companies that support us. Not only support us in sponsoring this event like North Space is doing, but supporting us by giving opportunities to students after they graduate from Launch Canada and graduate from the rocket teams. And so we're very lucky in Canada to have companies that provide this pathway in working in rocketry post-university, post-high school, and post-rocketry teams. And if you're interested with what you're doing today, there are ways to do it professionally, and our next speaker is one of those options. So I'll present our speaker, Rahul Goel from North Space. Rahul is a proud Canadian serial entrepreneur and aerospace engineer with a passion for economic development and helping aerospace engineers commercialize their research. Very fitting. Rahul currently works at North Space as the CEO, a Canadian space company building an end-to-end orbital launch vehicle for Canada. Rahul holds a bachelor's degree in aerospace engineering from U of T's engineering science program, where he also founded the Robotics for Space Exploration team, and is now pursuing a PhD part-time at the UTIS in space robotics, which is also U of T, with the goal to develop a Canadian lunar rover. He also proudly serves as a board member for Launch Canada and a strong advocate for supporting student design and engineering teams. So we have an all-around rock star and in Canada. Everybody please welcome Rahul Goel.
All right. Well, thank you so much, everybody, for making time for this talk and for being here. Congratulations to all the teams, and congratulations to Launch Canada. Tremendous. I'm very lucky to be here for the first time. I wish I could have been here in prior years, but you know, with the work that we're doing, head's always just barely above water. So this year we were kind of finally able to squeeze it out and make it here. So really honored and really excited to tell you a little bit about Nord Space, but also share a little bit about the student experience. Because a lot of us at Nord Space are fairly young. A lot of us are students. We were working on rocketry teams only a couple of years ago, so I think there's a lot to relate to here, and hopefully it might have an impact on your journey as well, post-graduation and even in internships. So if I could have the next slide, please, I'd appreciate it. So as we all know, we have a really rich history in space in Canada, and there's a lot to be proud of. Everything from our contributions on the ISS to our astronaut program and all that other stuff. But as a kid and as I got a little bit older, I always wondered, where are our launch vehicles? Where are the rockets? What's going on here? And as I got even older and became an engineer and started playing a bigger role in the space industry and learning about all this kind of great stuff, it really struck me that we're missing a critical piece of infrastructure here in Canada. And especially over the last 10, 15 years, it's become very apparent that having a launch program is a critical capability for really any nation that's wanting to be a spacefaring nation. Now, we don't need to launch astronauts necessarily, but just having that minimum capability to get small assets into orbit is something that I think and a lot of us think is a critical capability, and I'm sure a big reason why you all are here today. So I personally define sovereign launch in Canada as launching a Canadian payload from a Canadian rocket from a Canadian spaceport. And that's exactly what we're trying to accomplish here at Nordspace. Next slide, please. Obviously something very wrong with this map. We clearly have a great concentration of student and amateur rocketeers, but not being on this map is not an option for Canada. We're probably one of only 20 nations at this point that are close to getting launch or already obviously have it. And we estimate by 2040 there are probably about 40 nations that will have launch, and we're pretty far from that. We're behind the 8 ball. We're going to fix it, but there's a lot of work to be done, and we need people like you to make it happen. Next slide, please. We're facing an Avro moment in Canada. I fundamentally believe this along with many members of our team. We cannot let this happen on our watch. When I learned about the Avro Aero, and I was very inspired by Canada and space and all of that from like say the age of 5 to 10, where I sort of started understanding some of this stuff. But then when I went to a local museum and got to touch, a model of an Avro Aero, full-scale one, I was shocked. I was blown away. I couldn't believe that something like this exists in Canada, only to realize that it doesn't, and it never really ended up panning out the way we all hoped it would have. Obviously, a little bit before our time, but imagine we had this capability and we lost it. We lost thousands of jobs and a future in aerospace that Canadians could have been exceptionally proud of. We can't let that happen again, and I fear that that's happening with launch in Canada. We cannot let that happen again, not on our watch. Next slide, please. So, I'm preaching to the choir here. Of course, sovereign launch is so critical for all sorts of reasons. Environmental protection and disaster management, for our economy. It's a brand new industry that promises thousands of jobs and billions of dollars over the decades in economic growth. All the technological innovation that comes from this. And, if you rewind the clock 10, 15 years ago, we were able to keep a lot of our aerospace engineers, talented folks like you, in Canada because, ITAR, you can't really go to the United States, which is one of the main places you could work, but now you could go to, Germany or Spain or the UK or Australia or New Zealand or anywhere, and you will. You're leaving Canada, and we can't have this. We're losing our talent. We cannot have this. So from a national security standpoint, environmental protection, defense, all of that, it's critical, but I also think there's something even bigger. I think when we have launch in Canada, we're going to inspire a nation to dream bigger, to work on hard things, to solve hard problems. There's something so beautiful about seeing a rocket launch that obviously all of you know, perhaps better than I, that it just awakens something. And I think when we do that for the whole nation, it's going to be a whole new chapter for Canada. And I'm so excited to make that happen with all of you. Next slide, please. So, average age during Apollo for most of the engineers and in mission control, 28. Pretty young. There's no reason you all are too young, we are too young to do this for Canada. We can do it. We're the right age. I think it's the perfect age, in fact. I've long held a belief that between graduation and entering industry, there's about a 1 to 3 year window where you're so talented, but you still believe what's traditionally thought was impossible. You still think it's possible. You still think you can do it. You haven't been jaded by the intensity of, writing requirements and building things to a certain spec, and all of that is so important, of course. And just the practicalities of finance and all this kind of stuff that really throws a wrench into a lot of your biggest dreams. But you still believe it's possible, and I think that that's what's required. We need people who believe that this is possible to actually make it possible, no matter how hard it is. And I think that's where all of you fit in. So we can do this. We're the right age. Next slide, please. So, here's an example of some of our team members. Again, we lean pretty young, but age is just a number. At the end of the day, it's going to take an entire nation to make this happen. But I'm really proud of just a few of our folks here. And if you go to the next slide, we've come a pretty long way in a very short amount of time. So February 2023, that was on my porch where we were running goofy propulsion experiments, and I permanently stained my porch as a result of it. But, a year later, we acquired our own facility, we set up our own in-house manufacturing, we designed from literal napkins to 3D printing in-house metal engines, fired it, flight ready, and 3 or 4 days ago, we just went vertical with our rocket. Now, I know it pales in comparison to some of the things that you all have been doing as students, But it goes to show how fast you can actually accomplish things if you have the right team and if you have the right resources, and I think you really have the right philosophy for engineering and making things happen. Now, we have a very long way to go, but I think this is a pretty promising start for us. If you could just play that video, we have a lot of videos and we post a lot and try to be as transparent as possible. But in the last 2 or 3 days, we went to our new test site, we stood up our rocket vertically for the first time, and it was quite the spectacle. So if the video works, that'd be great. If not, that's all right. Fantastic. Got some epic music on that as well. You can watch it later. An ecosystem where students like yourselves can test and build in a safe environment and support the community that way too. One of the biggest challenges I had as a student was just finding resources, finding space, finding people with know-how to actually do this. We really want to try to make that happen. In addition to providing funding, it's really important to provide guidance and resources. Next slide, please. So I'll talk a little bit about NordSpace. The goal of this presentation really isn't to talk about NordSpace as much, but I think it helps contextualize a couple of things, and I think it'll also help illustrate our approach as a company. We have a couple of key divisions, so we try really hard not to hang our hat on being a launch company, but for marketing and PR and growth purposes, it works really well, but under the hood, we're working very hard on several other key pieces of technology. Our satellite tech is really important, and we're excited to be working on that. We're building our own spaceport in Canada, and we're excited to share the location publicly later this year, but it's the most beautiful place I've ever seen. And we're working on, of course, launch. So I'll keep telling you a little bit about some of these things. Next slide, please. So we have 3 classes of launch vehicles, Taiga, Boreal, and Tundra. And one of the things that we often get asked is, hey, is it hard to do what we're doing in Canada? And the answer is yes. But one of the things is that we've realized is the challenges have actually led to us coming up with some pretty innovative and attractive technologies. So our launch vehicles, because there's no spaceport in Canada really, or there's no launch or test facility for us to test at, we had to make things highly portable, as I'm sure all of you have. We've had to rely on conventional fuels because we don't have access to, RP1, for example. What we thought were challenges actually have caught the attention of some really important stakeholders. We're in the U.S. Next week, working with the Defense Department on some really exciting projects, and they can't believe that what we're able to do with the limited resources that we have to build a portable launch system using conventional fuels. It's necessity is the mother of invention, and it's turned out people care, and it's really great. So for reasons beyond our own consumption of our launch capabilities, we're really excited to be putting this innovation out there. So Tundra is our goal. Please, yeah, that was perfect actually. Tundra is our launch vehicle that we're working towards, which is, from in terms of scale and size, very close to Rocket Lab's Electron. Liquid rocket engine, of course, and we're working exceptionally hard to bring the cost down. One of the things that's really important to us is cost. We're working extremely hard to make sure that we have an extremely low-cost launch vehicle, and I'll talk a little bit more about how we're doing that, relying heavily on 3D printing, of course, and things of that nature. Next slide, please. So Spaceport Canada, and I'm just giving you a little teaser here of the location that we're setting up at, or one of 2, but our primary site. And it's going to make Canadian history, and we're very, very excited about this, to own and operate our own spaceport, and also, as you can probably tell, we care a lot about students, a lot, and we're making sure that we're setting this up as a facility that also helps amateur rocketry, helps students, and also helps new companies. What we're really trying to do is pave the way for other companies in Canada to not have to face the same headwinds that we have to. So, tremendous potential, and we're really excited to be building this to our spec. Next slide, please. It doesn't look the pictures don't do it justice, but we're working very hard, again, on vertical integration. So in-house, we do everything from our own, laser welding and robotic welding to additive composites, and all kinds of, CNCing, of course, and all of that. And this is just in the last year and change that we've been able to set all of this up. So we're very excited, and that's a shot of our test site that you just saw recently. Next slide, please. So the Hatfield engine is sort of the crown jewel of what we're doing. You see a shot of how it's printed and manufactured in-house. Shot of one of our early test fires as well, which are always extremely exciting. It's being designed in a way where it's extremely easy to manufacture, extremely easy to integrate, and extremely easy to operate, and also scalable. So we're working on a couple of variants of this engine. Our current engine is about 15 kilonewtons for our upcoming launch, but obviously it's going to scale up significantly from there. Next slide, please. As I mentioned, we're also working on various spacecraft components. This is really important for us to not just be a launch company, but also to be a payload company and build the entire supply chain within Canada and within Nord Space, where we're able to go from mission concept to orbit all within Canada. So we're working on our own in-space propulsion thrusters, our own hyperspectral camera, and a couple of other components as well. And we're trying to package our engine as well to be able to be sold. Next slide, please. So I want to pivot a little bit and talk about my personal journey and how we sort of come to this point. As you can see there, a little shorter, a little chubbier, but that was me back in grade 4, I think. Starting off with Lego robotics, and that was a pivotal moment for me. But since then, I've been a part of countless engineering teams and built them and led them, windmills, rovers, satellites, rockets, drones, you name it. And I cannot emphasize how important the student design team experience is. So I'm really grateful and happy to see all of you guys doing what you're doing. It makes a big difference. Next slide, please. I often get asked, I don't consider us anything really special, but how did we land on the path? How did I land on the path that I have? It's pretty average upbringing, honestly, for me. So there's nothing really, no reason anyone else can't follow or exceed what we're doing here. But born and raised in Toronto, very proud Canadian, very proud Torontonian. Initially went to business school, in fact, which was a mistake, obviously. I love those guys. But ended up in U of T engineering, aerospace engineering, and that's where I'm now back to do my PhD part-time as well. Spent a lot of time doing what you guys are doing. Now, I really wish I spent more time in class. I basically didn't. I just show up for exams. I don't recommend this at all. But I was able to slide through, and I basically spent like 18 hours a day doing the kind of stuff that you all are doing. I'm sure some of you can relate. I wanted to start Nord Space when I graduated. So I graduated in 2016. Obviously very hard, trying to raise $20 million as a fresh grad in Canada, trying to build a rocket, pretty tough about 8 years or so ago. That was a pretty crushing moment for me when I started, that reality started to hit, and that what I thought was possible started seeming a little impossible. But undeterred, I spent the next 10 years or so as an entrepreneur, and my only goal was to earn enough money that I could spend it all on building rockets for Canada. And I was very lucky to get to that point. Thanks to an amazing team at my other companies that I manage, we got to a point in 2022 where I was able to start the company, and I'm deeply personally invested in this, and I think that's the only way to actually make this happen. I was very specific about making sure we don't start a company that's on government life support for funding or anything like that. It has to move fast, and it has to be extremely nimble. Next slide, please. So the impact of private capital in Nord Space, and I highly recommend this is a path that you all take. If you're planning on doing something like this, is I contributed our Series A, and continuing to invest. We went from our first napkin sketches, as you saw, to our hot fire, and we're looking forward to our first launch later this year. So in less than 2 years, we're hoping to get to a point where we can go from 0 to our first flight. And the reason it's so important to go so fast is the success rate, from probability standpoint for launch companies, at least for that division, is how fast they can actually launch something. It doesn't matter what it is, just get off the pad, learn how to launch, develop your ConOps, understand the process, figure out infrastructure, logistics, and all of that. The rocket science is hard, but it's honestly, from my personal experience, it's the easy part. The hard part is everything else. I'll talk more about that in a second. Next slide, please. So our philosophy at Nordspace is to just keep launching. Our goal is to get to a point where we're just launching constantly. Every couple of weeks, down to every couple of days, we're just launching, and building that cadence where we're just flying and testing and taking that approach. You know, the reality for launch in Canada is it's going to be very difficult, it's going to be very expensive. It's a treacherous path, but it has to be done, in our humble opinion. And, you know, we don't want to make rocket science harder than it has to be. That's why we chose liquid propulsion. That's why we're going with conventional approaches in every way possible. And I've always just said that, hey, I don't care. We just got to get to orbit. I don't care if we limp into orbit. Just get there. And that's our goal. We're nothing fancy. Our goal is to get to orbit. So we're minimizing the rocket science, trying constantly design for manufacturing, design for assembly, design for cost, and then invest in vertical integration. So in-house manufacturing, our own test facilities, our own launch pad, all of that, so we can just manage and cut down on all the steps required, and then just fly fast, fly often. Next slide, please. So I think personally, as a student in a sense myself again, but also in general, I think you all have really the ability to make launch possible. It's incredibly inspiring to see what you all are doing. Like, honestly, I'm so blown away and so in awe and deeply humbled. But I think we have to really work hard in Canada to make sure commercialization and policy and all of those elements, really, the business, the logistics, the strategy, regulatory, those are all prioritized. I know it's fun, you know, I'm sure there's people who want to work on RDEs or want to work on the next, you know, incredible hybrid propulsion. Do all of that, please. But don't start, in my opinion, the next launch company in Canada and make it an RDE, you know, for example. Just do the thing to get us to orbit, please, you know, and I'll be really happy. And I think that's what we need. So focus on the basics, and I think that's something that we struggle with in Canada. We're always chasing innovation, and I don't want to discourage that, but really focus on the practicality as well. Raise your voice as students. They're very loud and very important. Attend events, attend industry events, stand up during Q&As, and even though there's much more senior people in the room, and talk about launch, ask about launch, make sure that you're that annoying person that cannot be ignored. Write, research, share on social media, all of that, it all goes a very long way. And just be very clear with your asks. Happy to help with this. Next slide, please. Last couple of slides, I want to really focus on commercialization. Some of you might be pursuing higher education, which is great. Some of you guys might have some incredible ideas for aerospace products. Please focus on commercialization. Now, I think fundamental research and all of that is really important, but I just think in our country right now we're lacking this. And I think if you try to become entrepreneurs, it'll just be great for the whole country, for the whole economy, for us, and we really need this. Next slide, please. So to that end, you know, one of the things that we're next slide, please. Thank you so much. We're starting Northspace Ventures next year, which has the express intent to provide seed capital for new aerospace companies. And not just seed capital, but try to bring them in-house and help them with manufacturing, help them with design, share our lessons, and help them just get started really quickly. So this is something I'm very excited about. If you're one of those individuals who has a brilliant idea or wants to commercialize your work, please talk to me. I really care about this. I care about creating more entrepreneurs and more economic development and more jobs and keeping our aerospace talent here in Canada. So we're putting $2 million starting next year into this, and with the hope to invest in about 6 to 8 companies over the next little while as our first round. So exciting. Next slide, please. I really believe students are the bedrock, you guys, of Canada's space industry, so please keep doing what you're doing. It is so important. We're extremely humbled and grateful by the number of people that apply to work at Nordspace. I'm working as hard as I can along with our team to get to a point where we can hire as many people as possible. We have people, you know, waiting outside our office in the mornings with their resumes. I've never seen this before. And I've been a part of several companies, run companies. Nobody cares about them. Nobody cares about a software company or anything like that. Helps pay the bills, but this is what people care about, and it's so exciting. So please keep doing what you're doing. It's so important. Next slide, please. Last slide or two. Outreach is really important to us. As you all know, we're very proud to be sponsors of Launch Canada. One of the things I struggled with when I was a student was just sponsorship. I thought it was I found it very disappointing and very difficult that some prominent, you know, aerospace companies in our neighborhood wouldn't even throw like $500 at us. So it was really important to me that, you know, upon graduation, we get to a point where we're able to contribute back to student design teams. We're proud to say we're sponsoring about 15 student teams now between satellites, rovers, and rockets, sponsoring Launch Canada, the CIRC. And the only reason I say this is if there's others in the room who have more capital than us, you know, larger companies and all of that, please support our students. If a small company can do it, you can too. But we're trying in all kinds of other ways, as you saw, with infrastructure and mentorship and all of that, scholarships to see if we can help Canadians and especially help students. Next slide, please. So that's it. You know, I think Canada will become a spacefaring nation once we unlock access to space. It's so important for us to get launch going for the future of this country. It's going to be hard. It's going to be competitive. We got to focus on first principles, but we'll get there. And we need everyone's help. So thank you everybody for your time. I really appreciate it.
Wow, a lot to unpack there. I'm sure there's going to be many questions from the audience. At least I have a lot. There's a lot of information that I didn't know. I didn't know you had a venture program, which is very interesting for teams here that are focusing on commercialization. I love your patriotism. I really felt it through the presentation, so thank you a lot. Any questions in the audience for our speaker? I think a lot of us are still processing what you said, and I can see a lot of students nodding at your mentions of commercialization and flying fast, failing fast, focusing on what works. And I worked on RDs and I worked on hybrid engines, and I completely agree with you. You know, there's one thing about the science at school, but it's another thing of making Canada a spacefaring nation. And your vision as a CEO of seeing forward and seeing beyond and seeing what we need to do for our country is fantastic.
Yeah,
so,
for sure.
Thank you so much. Yes.
Yes, hi. I was just wondering, what are your methods of cutting costs for manufacturing, developing the rocket engine designs and stuff like that? Because are you starting from scratch, or are you building up on something that already exists?
Yeah, that's a great question. I can get into this in a lot of detail over time. I love economics and unit economics and things like that. But high level, you know, one of the things that we try to do is use a lot of components that aren't necessarily space rated, but qualifying them for our purposes. Oftentimes we find that they are the exact same components rebranded as a space rated component, and you know, 1/20th of the price. So that helps. Another thing that I really care about, and I think that's really important, is one of our team members has a really great saying that was passed down. You either pay for something now or you pay for something later. I think one of the things that we're really trying to do is pay for some of the things that might cost a lot later now. So we're investing a lot in in-house manufacturing. We're buying our own land for a test site. We're buying our own land for a spaceport. These are large capital expenditures, but they fundamentally will reduce the variable cost over time. I'm not a fan of variable cost. I hate spending on subscriptions and leases and things like that. I know that's difficult for new companies and new teams, but that was really important to me when starting Nordspace, that we have the capital to invest in core infrastructure so that we can amortize that and just put that on one side and not have to spend $200,000 to some spaceport company to launch, or $500,000, some of the quotes we got, just to launch a rocket when we could just do the thing ourselves. So, you know, things like that add up a lot. And then there's all kinds of other things as well. One of the biggest challenges, if you look into financials for a lot of rocket companies, is they spend so much money on R&D, and they have to charge a lot for their rocket per launch just to cover the R&D expenses. It takes them 10 years just to break even. We're doing everything we can to minimize our R&D costs. Easier said than done, but we're trying.
Looking even further down the road, I know it may not be on the cards right now, but do you see any point in the future where you may be interested in doing human-rated spaceflight?
I would so love that, but that's one thing that I have a tremendous amount of respect for any company that attempts anything with humans on board. I would love to do that, but that is one element of spaceflight that strikes fear into my heart. I think maybe after realistically 15, 20 years of success, you know, we can reach that. But it also falls into the same category where I don't want us to get distracted as Canadians. As much as I would love for us to do human spaceflight, it's just not necessary. What we need is basic access to orbit, focus on that, do that well for a decade or so, and then we can aim higher and do greater things. So I would so love that, but that is a level of responsibility and difficulty that I admire greatly, and maybe someday we do it, but not in the near future.
I just had a question about the location of your business and where you're planning to spread in Canada.
Sure.
Are you trying to keep this in Ontario, Toronto area, and then kind of move over into Nova Scotia, or are you trying to make this like a Canada-wide sort of business, make it more accessible to more of Canada?
Yeah, any opportunity we can get to make this a Canada-wide endeavor, we take. So our spaceport is on the East Coast. Our test site is not necessarily in the Toronto area, but it's east of Toronto, 2 hours. And the way our company is structured, where we're not just working on launch vehicles, I mean, that's the cool thing, we can talk about that, but under the hood, we are working on other things as well. They might not all make sense to be in the same facility, so very likely over the next couple of years, we'll have at least 2 more locations working on different aspects of space missions.
I have a trick question, if you don't mind. You just mentioned do not get distracted and focus on the mission. You've shown North Space work being in many different areas, in space propulsion, spectrometry, cameras, sensors, in space data. How do you maintain the focus in your company while addressing all these different ventures and the venture part of North Space?
Yeah, it's a great question. I mean, we don't allocate an equal amount of resources necessarily to each division right now. Our focus definitely is on our launch program. That's the one that has the highest, our greatest time requirement to get up and running. But over time, I'd say 80% of our resources are on launch, so it is our focus. But hoping that over the next year or two, it becomes 50% and less. It's also sort of a necessary evil. You look at Rocket Lab, for example, a company that I admire greatly. They've had 50 launches, fantastic, but still their greatest revenue driver is their payload business, not launch. They still haven't made money off of launch. Lots of lessons to be learned there, but one of the key lessons is it might be a bit of a delusion to think that you can build a launch company and succeed as a launch company right out of the gate. Very difficult. It's critical capability that we need, but to make it happen, we might have to go on a couple of side quests to build some business lines that generate cash flow sooner than launch.
Great answer, thank you.
Hey, Rule. Thank you for addressing the brain drain part of the problem and the talent. With so many different options for bright Canadian aerospace engineers to go to, like Rocket Lab, RFA, and SpaceX, for those of us who are dual citizens, why should people stay in Canada and work on North Space when they have opportunities elsewhere with companies that are maybe like further along or more well capitalized, paying higher wages? So just want to get your thoughts on that.
Yeah, for sure. Just on the last point, we try very hard to be very much wage competitive. I think that's really important. This is not, I don't believe in endeavors where you underpay people and just ask them to believe. It's really important. So we try hard on that front, but I'm sure I'm sure it's still not at that same level. We'll get there. But I think there's a unique opportunity. I mean, of course, if you're patriotic and you care about Canada, then that's great. Not everybody is to the same extent, and that's totally fair. But one of the things that's really, really exciting and cool is we're making history. We're doing something for the first time, and that has its own charm and that has its own benefit that comes with it. You go to a Rocket Lab, great company again, but they've sort of already developed some of their core technology. You're going to be playing an absolute mission-critical role. You're going to be playing a fundamental role in building something that's really great. And at the same time, you end up learning tremendous leadership skills. You end up learning about technologies and making key design decisions that will affect things years down the line. Very hard to be able to do that at a company that's already fairly well established. So we probably only have a couple years left of that even under our belt before we become too constrained from a design standpoint that some of that isn't even possible in North Space. So I think it's a particularly cool time to join a company like North Space. I think about the brain drain problem pretty often, and one of the things that gives me hope as well is that there are more opportunities. That means that generally I think it's a good thing for the global space economy. There's going to be more people going into rocketry because they see a path there, even if it's not in Canada. And my hope is that Nord Space and other companies grow enough that you bring back all that knowledge and experience and come back home. And previously very hard to do. You can't go to the United States easily, so you stay in Canada, you don't really learn about rockets, but if you're able to go to Rocket Lab, RFA, all those other great places and come back to Canada, that's a great benefit for us. Hopefully that's a satisfactory answer.
Thank you.
So I'm sure many more questions in the audience, but unfortunately we ran out of time. Will you be around today?
Yeah, for a few more hours, yeah.
Amazing. So please feel free to go talk to Harold, and thank you again for this talk.
Thank you so much. Appreciate it.
Okay, so we're going to continue right away with a presentation by Ontario Tech Space and Rocketry, FLAIR. A presentation titled Coding to the Stars, the technical backbone of the FLAIR project. So, I have a small introduction. Ontario Tech Space and Rocketry is a student design team based out of the design studio and machine shop at Ontario Tech University in Oshawa, Ontario. This is their second year in existence and second year participating at the Launch Canada competition. OTSR, so 2 and 2, that's pretty good. Not a lot of teams can say that. OTSR will be performing ionizing radiation research with a supersonic 11 feet high powered rocket flying to 20,000 feet. I also want to say OTSR has been one of the most responsive and one of the most helpful teams in terms of building outreach this year. So I'm personally very thankful. And presenting today the presentation Coding to the Stars, the technical backbone of the FLAIR project, we have Israel Ogunmola, a team manager, third year mechanical engineering, Chris Rowdy, a team member, third year mathematics and computer science, and Logan Geiger, recovery lead, second year mechanical engineering. So everybody please, a warm round of welcome. And hello to everybody on the live stream. We're very happy to have you, and thank you for your comments in the chat.
Hello? Hey, as Cyril said, my name is Christopher Girardi. I'm a team member on Ontario Tech Space and Rocketry. I'm proud to be the only non-engineer of the team, kind of the IT guy, and that always comes with its kinks. People think, oh, you're in computer science, you must be really good at Photoshop, and I get sent all this different tasks all the time. But with me here, unfortunately, Logan wasn't able to make it. He was an excellent help throughout the entire project. But we do have our team manager, our team lead, right here, so take it away.
Hey everyone, my name is Israel. I'm one of the co-founders of the team, and I'm currently my third year mechanical engineering. This year I'm the team manager for Ontario Tech Space and Rocketry, and yeah, it's great to be here to talk about FLAIR.
Hello, I'm Logan Geiger, and I am the current recovery lead for the team. I'm in mechanical engineering, and I'm in second year going into third year.
Okay, next slide, please. Oh, perfect. So, straight into the presentation, right? Coding to the Stars, the technical backbone of Project FLAIR. Now, FLAIR, I'll explain a little bit later, but it's a recovery tool for our team. So, a few of us may be familiar with what happened to our team last year. Well, I can show you this video. This is how our launch went. Well, not exactly that, but the conclusions were the same. We were able to launch up into the atmosphere. However, we weren't able to exactly recover a rocket. Now, there's a very famous Facebook post of a woodchucker. Yeah, that was us. So someone found a rocket next to a highway. We were just casually chopping down trees. And a funny story about that was we actually reached out to them on Facebook, and he went back there the next day, but unfortunately did not find the rocket. Ever since then, we've been searching places like eBay for all our missing parts. No luck, but we do have plans to return out to the forest to searched for at this Launch Canada competition. And so this failure led to a lot of lessons learned, and it helped highlight the importance of good recovery systems, right? And so it led to the development of our team's recovery software, as we call FLIR version 1.
So there were a variety of reasons why we weren't able to recover the rocket in the first year, but mainly it was due to the telemetry. So first of all, we weren't able to recover on the same day due to constraints with time because we were the last people to launch that day of launching. That actually wouldn't have been too much of a problem if it wasn't for the second issue, which was the fact that our batteries could not survive the night. So, because we were planning on recovering the same day, we didn't put enough batteries in that could survive for long enough. So we ended up losing our GPS tracking the next day. And as part of that, our GPSs weren't very high quality. So they had some issues and we weren't able to properly track the rocket on its descent, so we had a very hard time figuring out where it would be after it landed. And we lost sight of it high in the air and below the tree line. All these issues compounded together made it so that we couldn't recover our rocket. So we needed to develop something to be able to recover it, and that is going to be FLIR.
And so, as part of engineering, you have to make sure we take lessons learned and provide corrective actions to make sure these things don't happen again. So some of the lessons we learned was through our unreliable telemetry data, we're able to find it very difficult to track the rocket because of our invisibility ranges, right? So we have the radio range and we have the visibility below the tree lines. So we only knew a small fraction of what actually happened through the entire flight plan. And so this software known as FLIR, which stands for Flight Launch Analysis and Recovery Estimator, aims to mitigate these risks by trying to piece together these small pieces, these small fractions of data that we can get from the rocket in order to be able to predict and provide a heat map of where we expect it to be. So over here I have a really simple flowchart of what we can have FLIR to do. It's divided into three main sections, right? So we have the pre-flight, we have the duration of the flight, and we have the post-flight portion. So pre-flight, we will be measuring all the weather conditions, making sure it's what we expect it to be, and we'll be using this to update our pre-characteristics of the launch pad. So changing things like the launch angle and making sure we can remeasure weights and CG and all these parts that will affect the trajectory immensely. And then during flight is where all the magic actually happens. Our flight stage records GPS data and transmits it down back to the ground station. And through this, we're able to run our kinematic solver to be able to predict the position based on a certain time interval. The final part will be to produce an output. It's sort of like a heat map of where we expect the rocket to be. So based on the probability of sort of the confidence that the system has, right, we will be able to provide our recovery team with coordinates, and that would help them path plan where exactly to go into the forest or wherever to look for the rocket, hence making it a lot more efficient over time.
Thank you very much, Israel and Logan. As always, they have a buttload of work to do. So you could always find us at our booth towards the back in the center and come check us out. I know tomorrow we're going to be having some old test simulations of FLIR, just looking at the data we're going to look at for pre-flight at least. Of course not post-flight, but yeah. So FLIR, the core process was to gather data from our altimeters, our GPS trackers on it. We get latitude, longitude, and altitude. And we also want to compare it with environmental factors, wind speed. Because for the pre-flight simulation, we'd want a perfect copy, but of course, everything's changing. So the best we could do, or at the very least, is make sure that the conditions are as close on the day of. We implement this, we map out the data that we get on the rocket during the flight, and then we also, using a kinematic solver, figure out what the velocity would look like, the thrust, various different variables, tons and tons of graphs for our flight based on the day of. And then we transmit this data, always keep a backup so we could use it for the post-flight testing, so we could figure out what we could do in future versions. And we're going to simulate it and use it as predictions. As you can see, a lot of the data comes in. I'm sure you're all familiar with NMEA. Quite fun to use, at the very least. And of course, last year, one of the big problems was our NMEA data was a little screwy. We were mapping from China all the way to Nigeria. Absolute impossible values that could never work. And there's been many problems with it. So the script we've developed allows us to filter out bad data, allows us to create subsets so we can just time it so our computers aren't really the best, so we don't crash them with too much information at once in like 20 lines a millisecond. And basically make sure we optimize it so everything's safe and working without crashing. And I can tell you there's always bugs. I remember we spent weeks testing data that wouldn't map, just to realize that every single line had a little V symbol. I forget what it was, the GPRMC V symbol for warning on every line, and no one noticed it, so we spent hours and hours optimizing for weeks just to realize bad receiver. I'm sure it's happened for measuring and all the sorts of stuff. But as said before, our receivers do lose a connection at a certain invincibility altitude, upper and lower invincibility. The script we developed for mapping also stops gathering data at those points, just so we don't gather unnecessary data that could screw up the simulation later on. The other side is the pre-flight simulation. Here you'll find various graphs. We could use motor representation, graphs for thrust, mass flow rate, altitude graphs, just about everything. But as you can see, probably the most important part is our flight trajectory, which is the main premise. We do use, for the environmental factors, we use RocketPi's documentation, but we've done all the kinematics ourselves, and you'll see soon how that can apply to future versions of Flare. But first, I would love to thank the avionics department. They gathered it, and they've been really big help with the telemetry monitoring, data logging. It allows us to do everything part of it. And the big benefit is because everyone has to do this for the rocket, Flare is zero cost. And the goal is to keep it near zero cost always. Or at very least with stuff used from avionics departments. And as you can see some of the stuff we're using here. We have the onboard telemetry, combination altimeter and GPSs, all of the different wiring. Our parachute is launching instead of like a system chip built in. We're using pressure holes so it can tell at a certain altitude when the pressure exceeds too much. It just automatically launches. Doesn't need a connection for it. But yeah, it was a great thing. The scalability of this is with this kinematic solver we built. We want to be able to have a prediction when we do lose signal in bad cases. So instead of a simulation that starts on the ground, we'll take the very last data right before crashing and then make a new simulation based on accelerometers that are on the rocket and future telemetry data that we could get to be able to create as close to accurate even in worst conditions. Parachute doesn't launch anything really. That's the idea. But of course, the scalability doesn't just apply to this. It applies to various other things. We'd love to be able to do control descent. Because right now, all this is tracking. It's tracking, predicting. Next year, we also hope to have actuated fin systems allow us to guide the rotational inertia of the rocket, as well as control parachutes, allow us to land at certain spots. The idea is to have it all in one system, so that just so that's super easy to work with and that everyone can use it. And, of course, we'd love to have better components. As you can see on the left, that's about the setup you're going to see this year. We have our little handheld receiver on our rocket. We originally were using some software, but we just decided to implement it into our own script for receiving everything live. And then at the bottom right, you can see the GPS tracker they'll be implementing. We'd love to have something like a pellet case that we're working towards, something with its own battery to prevent battery limitations, and something that can actually receive data from the rocket without needing an invincibility altitude, of course. And really, it would just be great to have these things next year. As Flare, I personally came in about 2 months ago, and that's about when Flare started. So we've really hoped that the scalability of the future, and I'm personally very eager the moment Launch Canada ends to work on all this stuff to show that we're going to be innovating every year, as we want to stress that this is Flare Mark 1. We weren't able to recover it last year, and this is the basics we need to recover it this year, and we hope to exceed that and be able to compete with other teams for control descent that I see looking around in booths is a bit of a fight between teams. Thank you so much. We'd love to see you come back next year. And if you want to talk to me later, I'm very eager to learn more about really anything. We also have other software stuff I'd love to talk about. But yeah, I'm really open to new ideas, anything you'd love to see from us. We're here to learn. Thank you very much.
Thank you for this amazing presentation. You know, I've personally witnessed the very quick rise of your team. Only 2 years, and you know, already your first year launching at Launch Canada, the second year back again, doing some advanced avionics research. I'm very impressed, and I wanted to ask as a first question, if you allow me, what do you think is the secret sauce at Ontario Tech that allows you guys to go so fast?
We hire some very peculiar people, myself included. We sometimes don't know how to stop working, but most importantly, especially with Flare, a lot of stuff just becomes a pipe dream that we believe is near impossible given time restraints and budget restraints until we figure it out. By Launch Canada every year, we just try our best to achieve something we don't think we could achieve at the start. And we always find something to improve on and some way we've showed to improve ourselves.
Fantastic. And I think this is very fitting with our previous presentation where you want to get in the sky fast.
Yeah.
Fly fast, fly forward. Any questions from the audience for our speaker today? I do have a follow-up question, if you allow me. So often the difficulty with going fast is that knowledge transfer and documentation is something that takes a sidestep. How will you ensure that as you graduate and other members of your team also do, that this knowledge will stay in your team? And we've seen meteor rise of certain teams, and then the team lead leaves, and then you kind of lose that momentum. So
I'm very excited to talk about this. My main focus with the rocketry team is the idea of an AI ran database. We want to have a database that organizes all of the information, stores projects, team leads, completely accessible to every team member, and uses database agents so that we don't have to teach every single guy SQL and all these different languages. People can look up exactly what they need from a project and exactly what they need from previous projects using keywords. And that is the other goal that I just love to work on.
Thank you. Amazing. Any questions from the audience? Well, thank you very much for your time. I don't know if you...
Christopher.
Oh, no, you were about to say something.
I just want to say, I know there might not be too many questions this year. It's pretty basic because other teams, I'm sure, have all done it. But I promise you next year there will be loads of questions to be had.
Beautiful. On a cliffhanger like that. I love it. Thank you so much. And up next on Season 2 of Ontario Tech City Rocketry. Okay. All right, so at 2:30, in about 9 minutes, we'll have the presentation from one of our lead sponsors. Actually, our largest sponsor, Pratt and Whitney Canada, represented by Nina Joshi. So please come back in about 10 minutes in the conference section, where we'll have the Pratt and Whitney presentation. Once again, when we're talking about rocketry and we're talking about aerospace, there's a few companies that allow you to continue post-graduation, and this is one of them. So looking forward to seeing all of you there.
warm-ups. Hey, Zach, please come to Production Central.
Okay, we are right on time. So we have a presentation from our lead sponsor, Pratt and Whitney Canada, presenting their work on powering careers, upcoming internships, career opportunities, and hiring process. So for all the combustion specialists, the combustion interested and minded people, we'll have a presentation for you right now. So if you could please come to the conference area, we're going to be presenting our lead sponsor, Pratt and Whitney Canada, represented by Ninad Joshi. So as a small introduction to our speaker, Ninad is an associate director of enterprise research and
exactly 30 years apart. Okay, so sorry, I was just taking notes on one of our speakers, which is honestly amazing. We're very, very lucky to have the people that we have today. So we have first Ninad Joshi, who is an Associate Director, Enterprise Research and Technology. Ninad has been with Pratt and Whitney Canada for more than 20 years with extensive experience in business jets, helicopters, and regionals. He was involved in strategic patenting and innovation for current and future product and processes. And his interests are propulsion technology evolution, hybrid and electrics, competitor movement, new manufacturing techniques like additive manufacturing, MIM, and ultrasonics. And then we have Harish Shafiq with us. He's a director at Pratt and Whitney Canada. He oversees around 7 engineers and works on all types of components related to this aircraft systems on the engine, so that's the fuel system, thermal management, control systems, propeller systems, you name it. So we have a very well-equipped team here. And Harris has 24 US patents and has published, 45 conference papers over the years, so we're very lucky to have them today. And I don't think I need to introduce Pratt and Whitney Canada. It's a name that rings a lot of bells for us, especially related to our president from Launch Canada, Adam Trumpor. So everybody, please welcome the Pratt and Whitney Canada team to the stage, and hello everybody on the live stream.
So I'll take the podium, and Ninad will take the handheld mic, and we're going to tag team it. Perfect. Thank you very much. All right. You got the clicker? All right.
Hello, everybody.
We'll get started. Good afternoon, everyone. It's a great honor to be here. Pratt and Whitney Canada is headquartered in Longueuil, Quebec. Great Canadian company. One of the largest companies in Canada in the aerospace sector. We're in the business of designing and manufacturing gas turbine engines. We're going to get, over the next 45 minutes, 1 hour, we're going to be talking about a little bit of what the company does. And we're going to talk a little bit about opportunities at the company for young, energetic, hardworking engineers. So to start with, Pratt & Whitney, it's part of Raytheon Technologies. Raytheon is a big American conglomerate. Raytheon basically has 3 businesses. One business is Raytheon. Raytheon is a big US defense contractor. So you've heard about things like Patriot missiles and Sidewinder missiles, and that kind of military equipment is designed, manufactured by Raytheon. Some of the equipment that the US government is supplying to Ukraine, for example, in their effort. The second company within the RTX family is Collins. So Collins, a lot of different aircraft components and aircraft systems that they design and develop. Their biggest business is really avionics. So the old Rockwell Collins was merged with Collins Aerospace, and you'll see in a lot of the airliners that Boeing, Airbus, Embraer, Bombardier, they manufacture. The cockpit, the glass cockpit, is typically a Collins cockpit. The third big business in RTX is, of course, Pratt & Whitney, and what I'll be focusing in on is Pratt & Whitney. So I think we're having some technical difficulties. The next slide is coming. I can't see that screen, so. So we're gonna have a video for you, and it'll tell you a little bit about the products we design, develop, and are in service. And it'll give you a really good preview about what the company does, and then we'll get into more details. Thank you. I spoke to slide 3. Slide 4.
All right, guys. So apologies for the technical difficulties. So what you saw here, most of them were Pratt Canada engines, and some of the cool ones that you saw, they were the PT-6Cs, that was the blue airplane flying over the Rockies. You saw the Gulfstreams, you saw the Citation Latitudes, you saw the PW-150s, the ATR 72-600 with the PW-127. So you kind of visited most of the portfolio, okay? Now moving on, what is Pratt and Whitney? So I'm talking about Pratt and Whitney Group in general. We are the world's greatest manufacturer of gas turbine engines. If you look at the picture on the top left, that's the so-called Bombardier C series, which has become the Airbus 220 now. So this is the first airplane designed with all composite fuselage, all composite, all engine technology, and it is exceeding all the customer expectations, okay? Beyond that, we have the fighters, we have the helicopters, then we have the next geared fan implementation on the Embraer E2, then we have the Pilatus PC-12 NGX, and so on. So we cover everything in the turbo shaft, turbo fan, and the turboprop world, and the APUs. And what do we do with that? We also have a comprehensive suite of predictive maintenance, which is our DPHM or fast technologies that help us stay on the wing more, okay, and build more reliable engines.
So truly, we have a global footprint. The engineering offices are located in Longueuil, Quebec, Mississauga, Ontario, and we also have an engineering office in Rzeszów, Poland. Manufacturing facilities across Canada, from Halifax to Lethbridge, and then we have support centers, product support centers across the world in South America, Asia, the Middle East, and Singapore.
Moving on, if we talk about Pratt and Whitney Canada, we are dominant in the market that we deal with. So we have about 16,500 operators dealing with. There are about 1,000 airlines that are using our products. We are servicing about 42,000 aircraft that are still in service. Together we have about 67,000 engines that are still in service, and we have accumulated more than 1 billion flying hours as a fleet average, okay? So to summarize, build on the previous slide, we are there in every country and every territory of the world.
So just, a bit of an overview of the Pratt & Whitney Canada portfolio. And really, there's no other gas turbine company in the world that has the portfolio, the small engine portfolio, that Pratt & Whitney Canada has. A strong presence in business aviation, regional aviation with ATR and de Havilland. We supply to the biggest helicopter manufacturers, Leonardo, Airbus Helicopters, Bell, Sikorsky, general aviation, the skydivers, the crop sprayers, many different kinds of applications in the general aviation market. And Pratt Canada also does APUs. So the auxiliary power unit that you find typically in the tail cone of the aircraft, also done by Pratt & Whitney Canada. So a tremendously diverse product portfolio, all within one company and competing with many different companies. You have a company like Williams that does small turbofans, and all they do is small turbofans. We compete with them. You have a company like Turbomeca that does helicopter engines, and all they do is helicopter engines, and we compete with them. And we have a company like Honeywell, and all they do is APUs, so we can compete with them. So, a tremendous portfolio of product, developed by great Canadian engineers, and a portfolio of product that has evolved over the last 30, 40 years to what it is now.
Okay, going a bit more into the engine portfolio. So I have the data in 4 columns. So what you see is the first column is all turbofan engines. We start with the smallest one, which is the PW600 now, which the lowest one is about 900 pound thrust. JT15D is an older product, it's a legacy product which is still in the market. Then we have the 500s, which basically cover about 3,000 to 5,000. Then PW300, which is a bit bigger than that. And PW800 is the newest product from our stable. It takes us all the way to 18,000 pound thrust. One good news on the 800 as of yesterday is that our PW812GA engine has flown on the Gulfstream 400 and took its first flight yesterday. So it was a great achievement for all of us at Pratt Canada. Okay. Yeah. Moving on to the second column is general aviation. So that's all the PT6E, PT6As, and different ranges of PT6. So that gives us a very dominant stake in the small engine market. The regional aviations is PW100 and PW150s. The newest product in the stable is PW127XT. Air Corsica has gone online and given an official statement where they record twice the time between overhauls, and they're recording a 25% reduction in fuel consumption because of that. So that's a public statement. I invite you to go up online. Okay. And within the APUs, we have a broad portfolio of products. Although you just see one, it in turn is a family of products: APS 2300, 2600, 3000, APS 5000, which goes on the 787. So we have a dominant stake there. And also in the helicopter market, we have the small range covered by the PW200 and the PW210, followed by the larger ones by the PT6E.
So, the 800, for me personally, it represents the last 10, 12 years of my life. This is the biggest fan engine that Pratt Canada has ever developed. Collaboration with Pratt and Whitney US. The core of the engine, when we say the core, the high pressure spool, is shared between us and the PW1500 engine that goes on the A220 former C-Series aircraft, and the LP spool, low pressure spool, fan, externals, accessories, and the whole engine integration all done at Pratt & Whitney Canada. The engine's been a tremendous success. The engine has already found 4 homes. The 800 engine is, like Ninad just mentioned, on the G400 that just had its first flight a couple of days ago, and is in service on the G500, the G600, and also on the Dassault 6X. The G500, G600, probably already 250 aircraft in service?
Yes, absolutely.
Probably already close to 500,000 hours flown. The aircraft itself, with the engine, very popular with corporate America. Companies like Coca-Cola have a couple of these planes. Companies like Honeywell have a couple of these planes. Their CEOs are flying around to important meetings, and we're Pratt Canada is powering all these aircraft.
This is the next big story that happened last year. This product went into service around November last year with Air Corsica, and now we have several of them. The order book is really, really strong. So as I mentioned earlier, it has a 40% increased time on wing. So basically it stays on the wing longer, so that assures you of a greater dispatch reliability. It has 20% lower fuel cost and a 3% better fuel consumption. So it is exceeding all the customer demands that were imposed on it, and we are over-delivering on that. So it's a big seller for Pratt.
And then, we'll talk a little bit about the venerable PT6. The PT6 that was initially launched, I believe, in the 1960s.
Yeah.
I believe we recently had a 50th anniversary for the PT6. We've made over 50,000 engines. Companies, aircraft manufacturers have designed their entire aircraft around the PT6 engine. I believe the PT6 engine is, per the slide, on 100 different aircraft. What else can I say about the PT6? It's continued to evolve. It started around 500 shaft horsepower. We're all the way up to 1,700 shaft horsepower on the latest PT6s. So on that same diameter, same barrel of engine, getting more and more power out of this turbo machine. So, you know, the latest development on PT6 is the E-Series. The E-Series we worked, started around 2016, 2017, certified 2019, 2020. In service, we've already made 500 engines of this variant. And the special thing about the E-Series is full electronic control on the engine now. So the gas generator and the propeller, all electronically controlled, and basically getting to a single lever in the cockpit. So reduced pilot workload, and really that cockpit now with a PT6 engine isn't that different than what you see on the big aircraft.
Just to build on this, many of you guys stopped by to understand career opportunities. So there's a gold mine I want to tell you about. So PT6 engine, as Harris mentioned, that we've sold more than 50,000 of them. Now the key point is half of them haven't come back to the company for their first overhaul as yet. So there's more and more revenue to be accrued from those engines that are still in service, okay? So when would they come in? By the time you guys start joining Pratt, you know, by the time new workforce joins, this would be a gold mine for you guys to capitalize on. Moving on, this has been the product evolution. If you see, we have gone across all the setup. My intent is not to bother you with all the little details, but if you look at all the major business segments, general aviation, helicopters, business aviation, regionals, commercials, and if you look on the time scale, we have been very, very busy on all up fronts, and we have had 125 certifications in the last 30 years and 200 in the last 60 years. So can somebody just do a math? You know, if we have been working on 200 certifications since 1960s, how many engines do we certify per year? Any guess? Anybody doing the math? Anybody pulling the phone? So in the last 60 years, we have produced 200 certifications. So it's almost 5 a year. All right?
You know, and that's been Pratt's success story. And that's how we've been able to attract the best engineers, retain the best engineers, is really this continuous cycle of product development. This continuous cycle of looking at the product portfolio, this continuous attention to where are the holes in the product portfolio. If we got a 5,000 pound thrust engine, we got a 10,000 pound thrust engine, how about a 15,000 pound thrust fan? You know, and along came the 800. You know, if we got a 2,000 shaft horsepower turbo shaft, why not a 1,000 shaft horsepower turbo shaft? Is there a helicopter application that can use that engine? Expanding the APU product line. Like Ninad was saying, you fly on a 787, you fly on a Dreamliner, that engine in the tail cone is a Pratt and Whitney Canada engine. So we've continued to be a leading investor. We've continued to develop product. We've continued to certify product. We've continued to improve our product, improve the fuel efficiency of our product. We've continued to, where needed, replace ourselves on existing aircraft applications with even better engines, blocking out competition. And that combination of stuff, we're investing in the business, we're growing the business, and the business is very different than it was 60 years ago when we were just designing and making PT6 engines. After that came the PW100 product line, the PW200 product line, the PW300 product line, and like we talked about, the PW800 product line.
So now going forward, what's the path ahead? Okay, so we are very heavily working towards making our product sustainable. So first and foremost is we are trying to derive more performance or more sustainability out of our existing products. So that improves removing the not so advisable materials from our products, redesigning the products for a lower weight, better efficiency, so on and so forth. Next step is we are also working on SAF compatibility. SAF compatibility, we have flown several of our products on 100% SAF, but we are certified to run on 50% SAF. So this is what our revenue products are doing, and we are progressing to build more portfolio on different kinds of SAF. We are also working on a hybrid electric demonstrator. You guys would have seen this in the newspapers and so on. Okay, and then we are also active in the hydrogen space. Watch out for more excitement from Pratt in the coming weeks. Okay, so that's the teaser.
So it's not only about developing new gas turbines. It's not only about thinking about making aviation more sustainable, and whether that sustainability is achieved through sustainable aviation fuels, bio-derived fuels, whether it's hybrid electric, where it's a combination of a thermal engine with batteries and a motor, or whether that's future fuels like hydrogen, but it's also the factory. And you've seen, other companies in other industries also focusing on the factory, focusing on automation, focusing on lean manufacturing, making sure the factory itself is optimized for throughput, optimized for sustainability, optimized for reduction of waste. And this is, some people have a passion for designing the product, some people have a passion for making the product, and the manufacturing engineering side of this is a big part of the overall equation.
Now, we always pride ourselves on dependable engines. So have you tried to quantify what a dependable engine is? So here, just to put things into perspective, let's assume when you start your career, okay, you would be buying your first car because you got your first great job, okay? So you drive 50 kilometers to work one way. So you do 4 engine starts a year. One when you leave for work, when you come back from work, and maybe one in between when you go to your nearest cafeteria, whatever, or nearest restaurant to pick up your favorite food, okay? You work 5 days a week, absolutely no vacations, and then you work 50 weeks a year, okay? So if this is your typical usage pattern, okay, and your career lifespan is 40 years, okay? So what would you do with so in 1 quarter, you would have 240 engine starts, 6,000 kilometers of your car running, and you would be running the car for 90 hours. Does that make sense? So now 6,000 kilometers is a typical mission for our PW300, PW800 business jets. So once they get out of the hangar, they just go hover around and come back, just a casual, I'm just going around the block kind of thing, okay? What happens in 1 year, okay? In 1 year, you have accumulated 960 starts, done about 24,000 kilometers on your car, so you may have had 5 oil changes by now. You've done 360 hours of engine running, okay? So we are talking about reasonable numbers, okay? So let's move on. In 10 years, you've done 9,600 engine starts, you've covered 240,000 kilometers on your car, and you have 3,600 hours on your car. What do you do at this stage? What do you do with your car at this stage? You just dump it away, right? So now, 3,600 hours is typical time between overhaul for our small PT6s, small turbofans, and helicopters. So TBO is, when the engine comes back, kind of say, I missed you, mommy, kind of thing, give it a hug and just send it back. That's it, okay? So this is typically what happens after 3,600 hours, okay? Now, what happens 40 years old? So by the time you finish your career, you've gone through 4 cars, you have done 38,400 engine starts, you've done 960,000 engine kilometers, and you've done 14,000 hours on it, roughly, okay? So this is a typical time between overhaul for our PW300s and the PW100s, okay? And even at this time, you have the product commands sizable value in the recycle market. So, and this is the reliability that we sell on every single engine, okay? Now, between this, there is one magical thing happened, okay? So, do you notice the dotted line after the 10-year mark? Okay, so at the 10-year mark, you did 9,600 engine starts, right? So, let's assume 6 months after that, you have 10,000 engine starts directly, right? So basically at that time, assuming all the starts happen perfectly, you come up to a 99.99% dispatch reliability, okay? That's what we commit to our customers. So through the lifespan of 10 years, nothing's gonna go wrong, no battery discharging, no oil changes, nothing required, and the first excusable failed start that you get is after 10 years and 6 months. So, sir, does that give a feel of, what's the reliability that we build on this engine? Make sense? All right. So, anyway, this is what makes us dependable engines, okay? And how do we do that? That is what makes us the market leader in multiple segments. And we attribute this market dominance to strategic investments and motivated employees, people like you, bright students who are willing to take jobs at Pratt.
So I'll talk a little bit about opportunities at Pratt. But before I do, I'll just build off of, the dependable engines a little bit. We talked a little bit about the PT6, and we talked about, different airframers, how they've designed their aircraft around the engine. One of the beauties of the PT6 is it's built an entire aircraft segment, which is the single engine market. You get onto an airplane, you're used to seeing an engine on the left wing, an engine on the right wing. There's a whole bunch of smaller aircraft out there that just have one engine in the nose. No redundancy. Something happens to that engine and you've lost power. Once you lose power, you stall. And you're hoping to glide, basically. So how have airframers been able to get away with designing aircraft with a single engine is the reliability of the PT6 engine. That the PT6 engine has been able to establish such a benchmark in reliability, in safety, that it's one of the only engines that is being used for single engine applications. Now, talking a little bit about opportunities at Pratt & Whitney Canada. So we're looking for smart people, we're looking for energetic people, we're looking for highly motivated people, and there's different ways to potentially join the company. We're a big employer for interns. I have to say this past summer, across the Pratt & Whitney campuses, I believe there was close to 300 interns hired. It's a huge number. It provides you with an excellent opportunity to get some actual, practical, industrial, professional experience while you're doing your education. The internships they're typically 4 to 8 months. They could go as long as 16 months. The internships could be in various different areas: operations, engineering, customer support. We have interns that come in undergrad, first year, second year. We also have some interns that come in doing their masters. In Quebec, we have an aerospace master's program, and as part of the requirements, if you're doing it at McGill, Concordia, École Polytechnique, is you do an internship, and some of those internships during the master's program are done at Pratt & Whitney Canada. And then, some of the internships, if they're in engineering, cover the various different disciplines: design, aerodynamics, heat transfer, fluid mechanics, vibration, you name it. Gas turbines need that discipline. My friend next to me over here, he's an acoustic specialist. So, we do we do all kinds of engineering. So we hire 3 times a year. We have a fall internship session, we have a winter internship session, and we have a summer session. Summer session is usually the most competitive. Summer session is when we take the largest number of interns. Most young people, like my children, they don't want to go to school in the summer, so they're looking for interns, so that's where we typically get the most applications. Right now, positions are open for winter internships, January 2025. So if you're thinking potentially taking a semester off, getting some industrial practical experience, Ninad will be able to tell you how to apply.
At this point, I want to give a shout out to Shivesh. Come on stage. So Shivesh just finished a 16-month term with Pratt. He's done great work. I'm not privileged to tell you what he did, but I don't know what he did. Whatever he did, his boss is very happy with him, okay? And he ended up talking to me through the right channels as the director of intellectual property organization. So you can understand he must have done something that deserves protection, okay? All right, so go ahead. Yeah, sure.
So back on,
okay, yeah.
So, I talked about the internship program. I also want to talk about the new grad rotation program. The new grad rotation program, myself and a couple of other directors at Pratt and Whitney Canada, we specifically architected this program, implemented this program in 2022. I've been at some of the Quebec universities talking about this program over the last couple of years. I think we've gotten fantastic results with this program. The ones that have stopped by the table, I've talked about this program, a lot of passion about this program. We started in 22, we got the green light from our vice president. We brought in 20 new grads. In 23, we brought in another 30 new grads. In 24, we brought in another 30 new grads. We have 80 new grads in this program. The plan is April of 25 or May of 25, we'll bring in another 20 to 30. So we're getting that approved. But the way the program works is you join the company, you do 3 one-year rotations. We will tag you up with a mentor with someone in the leadership, someone with 20, 30 years experience, and we'll move you around a little bit. The change is a little bit challenging. You work in a department, you get comfortable, you know the people around you, you develop a relationship with your supervisor. The year ends, and you know what we do? We move you. And you change departments. You gotta learn some new tools. You gotta develop a relationship with a new team. You work on some new tasks, some new challenges. The year ends, we move you again. And we cycle you through like that, but there's, it's to develop you. It's to develop you. It's for you to find your passions. It's for you to find what you excel at. It's happened. We hire someone, we bring someone in, and we move them into an aero group, and they're doing CFD day in, day out. And 6 months in, they start ripping out their hair. This is not for me. It's, you've been hired, you're in that group, we need you there. What ends up happening, and this happens in many companies, maybe the person leaves, maybe the person joins a new company, maybe a person looks for a new position. It's sort of a lose-lose for the individual and for the company. The company's invested, the person has moved on, the individual has to start again in a new company. Mechanical engineering is very broad. Mechanical engineering, like I said before, covers many different disciplines. I used to be a combustion guy, did combustion for a long time, and then I moved to controls, and I've been doing controls for some period of time. But you come in, we move you to 3 different areas. You might see different tools, you might see different disciplines, you might see different parts of the engine. At the end of the 3 years, we sit with you, we find out what you like, what you're good at, what you want to do for the next 5 to 10 years, and then we find you a permanent position in that area. Not many other companies do this. And I think it's something that in a world where we're seeing more attrition, where we're seeing more people jump around, it's a solution to that kind of problem. And I think with the 80 we have in the program, our retention is like 99% right now. And we're 3 years in, and we're going to launch a 4th year. So, you know, it gives you a bit of an idea of all the different areas you can work in. We have big combustion and compressor teams in our Plant 22 Mississauga facility. We have an advanced design team that Adam was long part of in our Mississauga facility. Our turbine and transmission teams are mostly in the Quebec facility. The area that I'm responsible for, controls and accessories, externals, split evenly between Montreal and Toronto or Mississauga. So lots of opportunity in the 2 big Canadian facilities, covering all the different parts of the engine, covering all the different disciplines.
In terms of what are we covering, the rotation program covers the 3 facilities as mentioned, the Longueuil, the Mississauga, as well as a facility in Poland. And then that's it. So end of the day, rotation program, it's all about you. So seriously consider this as your opportunity to learn and grow with the company. And just to summarize, cohort 2025, we are launching the initiative in September. Look out for these posts on social media and apply as soon as you can. Okay? Thank you very much, everyone.
Thank you for this amazing presentation. And like I said, there's a lot to do after university, a lot to do after rocketry, and this is one of the excellent options. So thank you for covering those.
It just starts when you finish university.
Finish university,
When
yes,
you finish,
absolutely.
that's when life starts.
When life starts. So we have time for one question, quick question. We're like 15 minutes over time, but we'll take one question because we're very happy to have Pratt and Whitney with us today. Okay, I'll go to the closest. Apologies. Pythagore told me that this is the closest.
Hi, so you mentioned the PET6 engine overhauls being a really good opportunity for like students and new grads to come into the company. What kind of opportunities would that kind of manifest as for new students and grads?
In relation to the PT6?
Yeah, so earlier you had mentioned how like the PT6 engine overhauls would be like a really good gold mine, I guess, or opportunity for new students and interns to kind of come into the company and have a lot of work to do. So what kind of work would that kind of manifest as for students and grads?
Sure. You know, I think when Ninad was talking about, you know, PT6 and the number of engines and, you know, overall on engines, the way our business works, it's a long cycle business. And, you know, the development of an engine can take 3, 4, 5 years, and then it goes into service. Once it goes into service, you know, our engines are out there. The life of an engine or the life of a product could be 40, 50 years. And sometimes to win these platforms with the airframers, when you ship the engine, you're only making so much money. But a lot of the money in our business is made downstream when engines get repaired, overhauled, refurbished, zero-timed, so the engine comes back. There's hot section inspections. There's potentially, you know, repairs that need to be done. It's a huge revenue stream for us. So, you know, the aftermarket provides a lot of the profits, especially for products that have high utilization. So the PT6 utilization could be, you know, 400, 500 hours a year. But in our regional turboprop market, engine utilization could be 3,000, 4,000 hours a year. So when these products come back and they get overhauled, that converts into profits, that converts into return on investment, because developing an engine often can be 8-figure, 9-figure type investments. So based on those returns of investments, that is then the engine for us to reinvest in the business, to develop new product, and to stay competitive. This business that we're in, there's no privilege for us to be working in this business. There's no, like, it's a bad example, but I'll give that example. My friend here is from McGill, and he knows in Quebec, the electricity is provided by Hydro-Quebec. And Hydro-Quebec is more or less like a monopoly. There's not a lot of competition. there's not a lot of, can I go get my electricity from someone else? In the business we're in, there's formidable competitors. I'm on the stage here, I'm only going to talk about Pratt and Whitney, I'm not going to name our competitors. But they are strong competitors, they're American competitors, there's European competitors, and you really got to keep investing in the business, you really got to have the best people, and then you'll get the best results, and then you'll be able to go and hire the talent of the future and develop the products of the future, whether that's more efficient engines, whether that's hybrid electric engines that are thermal engines with motors and batteries, or whether that's engines that can run off of hydrogen.
Thank you so much for a very extensive answer. I really appreciate it. Everybody, a nice round of applause for Pratt and Whitney Canada. Thank you so much. Thank you. And I want to reiterate how impossible this event would have been without Pratt and Whitney Canada, not only in providing the support for being here, the knowledge, the mentorship that we just had in this last presentation, and also the opportunities for you all that they took so long to actually detail and explain so you know where you're heading and your opportunities with PwC. So thank you so much, Pratt and Whitney Canada, for being here today. So going forward, we have one more presentation for the day, and if you look at the schedule, it actually doesn't say who it is, because it was a surprise and we've been working on this for quite a long time. And unfortunately, this person couldn't be with us today. And they did everything they could to be here, but we have a surprise for you all. So I'll say one thing, and I want you to not say the name, but raise your hand if you recognize the phrase, "Fly safe." All right, can we put it on the screen? Everyone, just to give you an idea, we did everything we could to have this man here. Scott Manley is one of the most foremost rocketry YouTubers, and if you zoom in on his shirt, you'll see that he is one of us. And so we're very lucky to have been able to track him down in Montreal when he came for the eclipse. He would post on Twitter, and I would photo search where he was, and then use my electric Bixie to bike there really quickly, and I couldn't catch him. But very lucky to have two Launch Canada teams, TS and Concordia University, that were able to find him, not only find him, but give him a tour and invite him to Launch Canada. So he discovered a mission, he knows who we are, and he decided to be with us today through this video. So he decided to record a 50-minute lecture just for Launch Canada, especially on rocketry. And so I hope you enjoy it. I unfortunately won't be able to stay for the whole length because I will be doing the Stomp Rockets with the outreach team if some of your younger students are interested. But hopefully you get to enjoy it. And correct me if I'm wrong, but we're going to be showing this again tomorrow at another time. So enjoy, and I would like you to appreciate that he didn't do a single take. He did 2 takes for Launch Canada, as you can see when we start playing the video. So thank you, everybody, and fly safe. Oh, last thing, sorry. Please go for your safety inspections as soon as possible. We don't want everybody to come tomorrow. After this 50-minute session, the conference is finished, so you should have time to go back to your teams and try to assemble, integrate, and finish your rocket. Because tomorrow there will be a line, and you don't want to be waiting and have it go on to another day. So Christopher Hobbs is somewhere over here. We have Dave as well. They're both part of the rocket building session that's happening tonight. If you're looking for instruction, and we will find Chris for you. Thank you very much, and enjoy the show.
Here, I'm in California. I am gonna. Okay.
Sound is pending. So you can imagine a very thick Scottish accent and someone roasting Rocket Company for their failures. Sorry? Rotate.
Hello, it's Scott Manley here. I'm in California. I am gonna. Okay. Hello, it's Scott Manley here. Today I want to talk to you about why rockets fail. Why? Because it's a presentation that I've previously given and I have a very limited time to get together a presentation for you guys up at Launch Canada. I was in Montreal earlier this year for the solar eclipse and had some amazing visits with various teams up there. So best of luck to everyone taking part, and just remember, taking part is as important as succeeding. So, yeah, if you fail, try to be spectacular. No, seriously, this is actually going to be, it's going to be a discussion about rockets and failures. Why do we want to talk about failures? Well, this great quote by Wernher von Braun says, "It takes 65,000 errors before you are qualified to make a rocket." And not all of those errors will result in a vehicle exploding, but those are going to be the ones you actually remember, right? People like to hear me talk about rocket failures because they're spectacular events. Rockets are full of flamey, explodey stuff. People like to hear how the explanations of the failures give them clues as to how the rockets actually work in details they've never anticipated. And also, I like to talk about failures because it puts my own failures in perspective. Sure, I may have deleted some code that I shouldn't have, but at least I didn't destroy a multi-million-dollar launch vehicle. So historically, success rates of rockets have been largely going up, but they actually have been going up, but equally as new lower funded, lower cost providers have come into the scene, we've had a sort of continual background of new providers failing rockets. Now, this diagram is from 2017, and some of these rockets may not even fly anymore. Some of these rockets are on their way out, and there's new ones that have come in since then. So anyway, let's rewind and talk about a big explosion. And this is Delta II GPS 2R1 in 1997. So this has 9 solid rocket motors around the outside of a Delta II rocket. Delta II basically came out because it existed because of the GPS contracts. So anyway, yeah, took off successfully. As it was ascending upwards, everything seemed to be mostly going fine. Some of those engines aren't supposed to be lit. That's perfectly normal. But then, a few seconds later, we have an anomaly. And, you might say, that's a giant explosion. That's not an anomaly. But actually, the official statement on the live stream was, "We have had an anomaly." That is one heck of an anomaly. Even better is after it exploded, all the solid rocket propellant starts falling down into the area around the launch site. And there's actually a bunch of people that parked their cars nearby, and their cars were literally destroyed by this. They had to put out all this fire. But yeah, what happened in this case? Well, one of the solid rocket boosters cracked about 6 seconds into the flight. Inside a solid rocket motor, you have a lot of highly energetic propellant burning. They had about 1,000 psi inside that, and you can do your conversion to metric if you want. This failure cascaded, the crack got worse, and after 12 seconds, the entire case ruptured. And about a second later, the flight termination system activated independently, destroying everything. RUD ensued, right? And RUD, of course, is rapid unscheduled disassembly. Now, the root cause, apparently, of this was that the ground handling people had changed some procedures, and the way they had loaded and moved the boosters around, they had moved them on rollers, which put stress points along the edge of this carbon fiber composite, and that caused local damage, which ultimately weakened the casing enough that it failed during the engine firing. So, another fun failure was the Delta III first flight. So Delta III was the successor to Delta II, or at least that's what they thought. So Delta II was getting kind of old and small, and the new owners wanted to make the rocket able to go, to carry large payloads to space. So they changed the design of it, and that meant that it needed more solid rocket motors. And so what they did with this is that to make it more capable, they added a new type of solid rocket booster, right? And these solid rocket boosters were able to perform thrust vectoring to provide steering, so that was incorporated into the control system. But they reused a lot of the guidance and control software from Delta II. So when the vehicle developed a 4 Hertz roll oscillation, it was being excited by the solid rocket boosters. And the solid rocket boosters used open cycle hydraulic system to actuate those motors. So as they were moving, they were basically losing hydraulic pressure, and eventually they ran out of hydraulic fluid. The nozzle stuck in their current orientation, and the vehicle lost control at about 72 seconds into the flight. Okay, another great fun one was the Proton, launched on July 2nd, 2013. This one you've probably seen many, many times. It is like a drunk rocket. You can see right away that the engines are actually moving backwards and forwards. It steers one way, it steers the other, and eventually the thing just goes unstable, heads off downrange, starts to rotate. You can see this orange propellant leaking out, but soon enough the whole thing actually breaks up aerodynamically in flight and becomes a giant fireball on the ground. And the root cause of this, which way is up? So rockets, as you know, have to have sensors to measure how they move. So they have accelerometers and gyroscopes. The guidance system is reading these sensors and it sends commands to control the engines. In this particular rocket, multiple sensors were installed upside down. And you know what? Apparently, these may have been installed somewhat deliberately. It required a fair amount of force because they had these matching key plates that could only allow the sensors to be installed in the correct direction. They had literally been hammered in upside down, so when the rocket launched, it went wrong. And it's amazing that they were able to find this in that giant fireball of a wreck. So for those of you who don't know, and you all know because you're all rocket people, IMUs, you've got accelerometers and gyroscopes, and this is what it looks like on the Apollo equipment, right? They have this like gimbaled sensor platform. Here's a more modern one using like ring laser gyroscopes, and here's a tiny one that sits inside your phone. Yes, you all have those so that you can play Pokemon Go. Actually, I think when I made this video originally, I made this slideshow, Pokemon Go was way more popular. Anyway, it's not the only time that this upside down accelerometer was a problem. We also had this during the return of the Genesis sample return capsule, which was supposed to use the accelerometer to measure when it was slowed down enough that it could deploy its parachute. And because it was upside down, it never actually got enough positive G's. It only saw negative G's, and therefore it was waiting for those positive G's to reach a peak and then fall back. And so the capsule just falls without deploying a parachute until it's smashed into the desert floor. Also, apparently the Galileo atmosphere probe had a similar problem, and I'm not actually sure we've seen a good explanation for why the parachute eventually deployed, but it did deploy and they did get good data. The Schiaparelli is a somewhat related thing. The idea was that this would be a lander which would deploy a parachute, and then at a certain altitude above Mars, it would ditch the parachute, fall down, fire its engines, and perform a soft landing. In reality, it ended up slamming into the surface of Mars at a relatively high speed, and the reason for this is it got dizzy. So the parachute deployment caused the probe to rotate and spin around because there's high forces. And it registered the gyros registered rotation rates, which were above like a hard-coded value, which said these can't be real, so let's ignore them. So its rotation state was not being updated. And so the control software lost track of what way it was facing. And so when it measured the ground as 3.2 kilometers below the probe, the software actually applied its current orientation vector, and it thought it was at negative altitude. So since it was at negative altitude, it cut its parachute and didn't fire its rocket motors and ended up smashing into the ground. This is the Ariane rocket family. You've probably heard about this one. There is now a new one, of course, Ariane 6, that's been added since then. The first flight of Ariane 5 was spectacular. First of all, it was a very big rocket with some very big boosters and some very complicated software. So Ariane, of course, it was a radical change from Ariane 4 to Ariane 5. The original Ariane 4 had been a sort of slow evolution through 1, 2, 3, 4. Ariane 5 inherited these very large multi-segment solid rocket motors on the side. It had a large core with a liquid hydrogen propellant. This was a completely new rocket, but the guidance system, that was one thing that they could actually reuse large parts of. And so they reused a bunch of the software. And that's what happens when you reuse software without doing a complete test. The mission, they did actually recover parts of some of these space probes in the swamps. So yeah, the first flight, it failed in June 1996. It was a successor to Ariane 4 with all new technology, but the software was reused. The software failed 7 seconds in because it was going too fast. So the good news is there was a backup computer. The bad news is the backup computer was running exactly the same software and it crashed. What it was specifically looking at was a value for the horizontal position, I believe, and that was limited to something like a 16-bit register. So when it went too far down range before this particular loop was finished, it overflowed that value, and since it overflowed in both positions, the thing just lost control. And so you needed to understand, the limits of your software. It's possible that this may not have been caught on this particular flight either. But anyway, moving onwards, Superbird B. Superbird B is a satellite which was, I think it's a weather satellite, communication satellite. It's a communication satellite. So it was built in like Sunnyvale, just south of me in the Bay Area. There's a fairly large manufacturing facility down there, and it was in the factory when there was an earthquake, the big 1989 earthquake. So, that satellite, I'm trying to remember exactly what happened, but that satellite didn't end up flying. Instead, another satellite flew, what happened was that satellite got shifted onto a different rocket. And this is what happened. So watch this rocket as it climbs past the top of the tower, right? You'll see that it's slipping sideways, and you can actually see one of those engines hitting the top. One of the booster engines on the side is not performing the way it should. In fact, it's literally running too hot. So this is the Vulcan engine. Now this is a photo from... it's the Viking engine. This is a photo from the STEC Center in the Netherlands I visited, and they have an interesting thing that they use hypergolic propellants. There's, nitrogen tetroxide, and I believe it's UDMH. And of course, those propellants are hypergolic. They burn great together. They create lots of high energy propellant. But to run the gas generator, to run the turbines, you have a gas generator that's run off of these propellants. And because these propellants make very high temperature, and because if you don't have it exactly neutralized stoichiometric, then you want to cool that gas down. So there's a water supply that sprays in there to cool down the exhaust gases so it can run the turbine. This is what the turbine looks like, and this is what one of the cooling vessels looks like in the gas generator. So it turns out that somewhere in the plumbing, somebody made a mistake, and they left a rag inside the pipe. And so the water wasn't flowing to one of the engines, and the engine basically destroyed its turbine very quickly, lost thrust, and that's why the rocket went sideways off the pad and eventually lost things. Now, I believe there's another version of this. I'm just going to skip over this particular one. Okay, so now let's talk about an early Soyuz failure. So Soyuz is, of course, a crew launch vehicle built by the Soviet Union. It flies on top of a rocket which is called Soyuz, but it's based on the R-7 design, which was used for Sputnik and Vostok and everything else. So as they were testing this, they had it set up on the pad. And as they went to launch it, one of the boosters failed to ignite, so they aborted the launch. That's fine. So the ground crew go back to the pad and they start securing the rocket to make sure that it's not going to fall over and that it's all depowered and everything. The vehicle had been switched over to internal power, and the IMU gyroscopes continued to work. As time passed, the Earth spun on its axis. And so if you can imagine, this way is up, but as the Earth rotates, up is staying in the one location, but the Earth is moving. And what happened then is that on board the spacecraft, it thought that it was falling over. So the Soyuz on top thought it was crashing. And so after 30 minutes, the angle of the gyroscope exceeded a predefined 8-degree limit, and that triggered the launch escape system. That in turn damaged the second stage hydraulics, leading to a fire, ultimately an explosion. The rocket was destroyed, the pad was out of use for months. It was not great. This is another example of a Soyuz failure. This one actually has crew on board, and there was a fire at the base of the vehicle, and they were actually having some trouble activating the launch abort system. It did eventually fire, and I love this guy, like, oh, God, that was a close one, right? Apparently, the crew on board were so angry and surprised by the force of this abort that they very quickly turned off the voice recorder because they were swearing too much. More recently, we had Soyuz MS-10, which was a launch to the International Space Station with 2 crew members on board. It was Alexei Ovechinin and Nick Hague. Now, normally Soyuz carries 3, but it's a tight fit. There was an empty seat because Russia was trying to save money. It failed 2 minutes after the launch, and the abort saved the crew. So yeah, this is what the launch looks like. You can see that it has these 4 strap-on boosters and 1 big core engine here. This is actually being streamed by NASA because, of course, there's a NASA astronaut on board. Now, later in the flight, well, they're getting ready to ditch those 4 boosters, and we get glitches. We see the boosters flying off, and what happens is the core just starts to process and loses control, and so they detach the spacecraft and it parachutes back to Earth. So how does this actually work? Well, you have the launch abort system on the Soyuz has this tower at the top, right? And that tower has a solid rocket motor inside it, which will pull the capsule away from the spacecraft like that. But later on in flight, they actually get rid of that tower, and instead they can just abort with engines that are on the fairing itself. The interesting thing, I guess, in this case was that they were at such high altitude they didn't need the tower. This is another example of how the launch abort system looks. The Soyuz is built into 3 parts. There's the orbit module on the front, the descent module in the middle, and the service module at the back. So when the launch abort happens, you leave behind the service module. And yeah, here's just another example of what the Soyuz actually looks like with the 4 strap-on boosters and the core. So yeah, what happened is the first stage booster, they were separating, and one of them failed to separate. This then contacted the core again, causing damage. It shut down the engine and the core, then the abort system fired, and the total flight time, including the fall back to the Earth, was about 20 minutes, and they reached 93 kilometers, so not quite space, unless, of course, you are Virgin Galactic, in which case that's totally acceptable. This is what a normal separation looks like on a Soyuz. One of the beautiful things about this is that as they separate outwards, they open up a valve that depressurizes the tanks through a nozzle at the front. So as it swings out, right, you clear the bottom, and then a pin here triggers, and that opens a valve here, which causes them to flip backwards. It's a really beautiful system, and it doesn't use any extra like special motors or anything. It just uses pressure inside the tanks. This is actually what happened on this flight. So watch it again. The one on the left, right? Watch the one on the left. You'll get to see it happen again, right? On the left in slow motion, right? Here we go. So it starts to go out, and the other ones peel away, but this one doesn't activate its little oxygen jet to escape. So the booster is damaged. And they trace this to a pin. So the boosters mate to the core with a ball socket joint. And in the middle of that ball, there's a little pin, so that as the booster starts to fall out, this pin opens up, and that triggers the jets to release the oxygen to boost the top away. In this case, the pin had been bent due to mishandling, and that meant that the booster never separated correctly. So there's another close-up of the pin. And here's what it looks like when you're actually trying to put these giant boosters on there. These are, of course, there's the actual socket here. They have to be very careful to make sure they don't bend things. So yeah, as I've said, rocket science is hard, but truthfully, rocket engineering is unforgiving. Like, rocket science is actually pretty easy. It's all just math and numbers and stuff. But engineering, that's where the rubber meets the road, or the rocket fuel meets the injector plate. Yeah, so here's another fun one. Apollo. They had a spacecraft called Little Joe 2, and this was supposed to test the launch abort system on Apollo, right? So this is what happened to it. It spun up out of control. It wasn't supposed to do that. And you see how it literally tears itself apart right at the moment where the launch abort triggers. So this was actually a very successful test, despite the fact that it wasn't supposed to have done that. It didn't need to simulate an emergency. It had a real emergency. What had happened was the guidance system had the roll control system, the cables were like swapped, and so it was trying to continually correct for a roll and instead making it worse. Another great launch abort failure was Mercury Redstone 1. This was the first attempt, demonstration of a human-capable vehicle in the US. That was supposed to be the launch. Instead, all you saw was the escape tower shoot off, and then boop, the parachute pops out. This rocket launched about 4 inches before it fell back. So yeah, Mercury Redstone 1, about 1 second after liftoff, the engines cut out. It rose to an altitude of 4 inches, then the escape tower triggered, and it reached an altitude of 4,000 feet. Good job, escape tower. Both parachutes then deployed one after the other. And this left a fully fueled and powered, energized rocket sitting on a pad without any clamps locking it in place. Yeah, there were people in the control room that suggested that maybe what they should do is shoot it with a gun to depressurize the tanks, just in case it blew over in the wind. They were really worried that the wind would catch the parachutes and pull the whole thing over. Now, what happened in this case? Well, there were two cables that were plugged into the bottom of the rocket. There was a power cable and a data cable, and the power cable was supposed to be pulled out before the data cable. Well, sorry, the data cable was supposed to be pulled out before the power cable, but in fact the reverse happened, and so the power cable kept in longer. The data cable. Okay, one of the cables, they got it backwards, and that meant that the electricity was flowing in the wrong direction, and it flew backwards through a relay, which triggered the engine shutdown command. Now, the Mercury Redstone was a very early rocket. It didn't have like a fancy autopilot. It had it was a sequencer, right? It didn't have any software. It was basically a bunch of relays that when this condition happened, the next step in the chain would happen. So first thing that happened was the engine shut down. At that point, they were supposed to trigger the escape tower, so that shot off right away. Now, because the control towers, the escape tower's gone, the capsule is now sitting here and it's waiting for the accelerometer to show 0 acceleration so that it can separate. Well, that never comes because it's sitting on the Earth. Meanwhile, the parachute is controlled by a separate system, and it knows that if the engine is shut down and the air pressure is sufficiently high, then it's inside the atmosphere and falling back, so it should deploy its parachute. So it deployed that. And then a few seconds later, there's no tension on those cables, so it deploys the second parachute. But yeah, ultimately what they had to do was make sure they had the correct length of cables to match the operation. Okay, Mariner 1. This is it was an Atlas LV-3 with Agena B. It was going to be the US's first attempt to launch a spacecraft to another planet, and unfortunately, it lost control and was destroyed just under 5 minutes into the flight. So what happened with Mariner 1? Well, they previously launched the Atlas controlled from the ground and had on-board guidance that was only used for on-orbit insertion. Now, because they use these computers running on the ground, so they can do these complex trajectory calculations, when they lost signal, the booster had to switch to much more limited internal guidance. And due to error in guidance code on the ground, it was getting very rough. It was trying to interpolate between these values. And the instantaneous values, due to the spotty communications, combined with spotty radar tracking, it caused rapid, unnecessary course corrections. So basically, you have smooth data that wasn't, it was supposed to be smooth data, but in fact it wasn't smooth. They were getting instantaneous values, so it was making very hard corrections. And because of the control loss, the range safety orbit officer triggered the flight termination system. And this is sometimes described as the most expensive hyphen in history because of the bar over the position value. It's not really a hyphen, but yeah, it's a good story. Mars Climate Orbiter. Yes, you might have heard about this one. You might have heard this meme, right? There are two kinds of countries. Those who use the metric system and those who have landed on the moon. And I like to say it's also those who used metric to land on the moon, because the Apollo guidance computer software was all using metric, and then later crashed a space probe into Mars because they confused metric and imperial units. And let's just ignore Liberia and Burma, who still use, imperial units. They don't have a space program, right? Anyway, with this case, what happened was Lockheed Martin software for the spacecraft, it used pounds of force. NASA used newtons, and when they were performing with this spacecraft, it was asymmetric, and the light from the sun, the radiation pressure, would cause a rotation. So they would have to occasionally, they would have to use like their control systems to remove that rotation. And when they did the desaturation burn to remove angular momentum, they had to fire the engines. Well, the engines were mounted asymmetrically, so that meant that they picked up a very small velocity every time they fired the engines, and they had to incorporate this into their calculations. Well, they were getting values which they assumed were in newtons when they were in fact in terms of pounds of force, which is about 4.5 times bigger. And that meant that when they got to Mars, they ended up burning up in the atmosphere. Today was indeed not a good day. Polus Energia, yes. So this is a fun one. This is a massive spacecraft mounted on the side of a massive rocket. This is the rocket that would ultimately carry Buran. It was a monster rocket that could carry like 100 tons by some measures. So this satellite was about 80 tons apparently. It was mounted backwards with the engines on the front for some complicated reason, which meant that after the rocket got mostly to orbit, they would separate the payload and then it had to turn 180 degrees and fire its engines. Now instead, due to some confusion, some problem with the software, it turned 180 degrees and then it kept rotating, and so when it did fire its engines, it slowed the spacecraft down and it fell to the ground. Polus was supposed to be a space laser, by the way, so space weapon systems, I don't have a big problem with them burning up. The Soviet N-1 rocket, another even bigger monster rocket. It was Russia's, Soviet Union's answer to the Saturn V. It was intended for their moon program. It was about 2,750 tons, a little less than the Saturn V, but it had more thrust, 4,500 tons, because it had 30 engines on the first stage, and these were amazing engines for the time. They were way more efficient than the engines on America's Saturn V because they were closed cycle, the very first closed cycle kerosene engines. But there were a lot of them because they couldn't make them big. So yeah, this is some footage of the rocket on its giant train tracks. It's like they've got two parallel train tracks with two parallel engines. Look at that ring of engines around the outside and the 6 engines in the middle. Now, to coordinate all these engines, they had to have a computer on board. This computer, I believe, is called CORD, and there were wiring issues, there were software issues, and the launches were, well, all unsuccessful. It launched 4 times, and every single time it was unsuccessful for different reasons. In the final launch, they actually had a problem when they shut one block of engines down too quickly, and the related water hammer effect burst all the propellant lines, and so they had a fire, and that ended. But in the earliest launch, I think it took off, and it detected an engine failure on one side, and it shut down the engines on the wrong side, and that cascaded into a giant fireball that went and destroyed the launch site. As a result, the N1 program was cancelled. But the engines, well, they were actually ordered to scrap the engines, but the engine developer instead kept all the engines in a warehouse. And after the Cold War, there were people in the US and the West looking for things that they could take from the former Soviet Union, and they found that they had these amazing high-performance engines. So the NK-33 engines, which were found in a warehouse, were refurbished by Aerojet Rocketdyne and sold as engines for a rocket called the Antares. This was a commercial cargo vehicle. It was built to carry cargo to the International Space Station by Original Orbital Sciences, which became Orbital ATK, which became Northrop Grumman. Anyway, yes, these engines were from the 1960s. And as I said, they had a spectacular amount of power. Yes, they're so spectacular that they had a problem with one of their turbo pumps. You may remember this. I remember this. I remember looking away for a second and then looking back to watch this fireball falling back in this monster explosion. So this, I believe it was a bearing failure in the turbo pump, and that it's not clear whether that was something that would have been fixed by the refurbishing, but ultimately they moved away from these to another type of engine, which they are no longer able to buy because they're made by Russia, and they're now switching over to another rocket engine. Anyway, for engine failures at launch, this is a fun one. Yeah. This is Astra. It had 5 engines on the first stage. It had almost exactly, it had a thrust-to-weight ratio of 1.25. So when it lost one of its engines, it had a thrust-to-weight ratio of 1. It goes sideways very, very slowly, and then as it burns propellant, it starts to rise up. Yeah, I like to call this the Space Y launch. I mean, okay, normally Y is vertical, but SpaceX is going that already, so they get dibs. I think here's another slow motion example of what's going on here. So there's actually like an explosion at the connector. You see that running up the side there? That's the raceway that carried propellant lines to fuel the rocket. Here's another example up there in the top left. That's where the thing would mate to the pad. So yeah, this ended up failing. Here's another example showing the booster close up there. And yeah, when those leaked out and caught fire, they accumulated debris or the accumulated fuel in the raceway and exploded, and it damaged the engine next to it, so it shut down, leaving them with 4 engines. And with 4 engines, they couldn't really stabilize it. So now, here's another one where we had an engine failure on launch. This is Firefly on their very first Alpha launch. You see that shutting down about 15 seconds in? This was apparently due to a valve that triggered. Now, with only 3 of the 4 engines, it climbed slowly, and eventually it lost control because its control systems were expecting 4 gimbaling engines. This was actually pretty spectacular because a lot of debris ended up falling down. I went and figured out this is me showing like when the engine failed, and this is one of the developers pointing to the valve or the connector that apparently broke, and because it broke, they shut down the engine. Yeah, always check your connectors. And always be vigilant, because failures can happen anywhere. This is a satellite which was dropped because it was on this rig. It was supposed to be bolted to this, and it would be rotated into whatever position was necessary to work on it. And they rotated it without checking that the bolts were still in. So now, we've talked about rocket failures, we've talked about some very spectacular explosions. And I know by this point you're getting a little fatigued. So let's go the other way. Let's ask, has a rocket ever imploded? Well, yes, because the early Atlas rocket relied on balloon tanks that were stabilized by their own internal pressure. And this meant that you could make a very light tank, but you just had to keep it pressurized. But if you lose pressure, the tank will implode. And this did happen in May 1963 at Vandenberg. It was an Atlas Agena D, and as they were loading propellant, they had a break in the LOX line, and yeah, the rocket just starts to fall down and collapse and then explode. So let's just do a few look at SpaceX failures, and I'm going to say this has not got the most recent one in it, but this is their CRS-7 launch. As they're flying upwards, they're getting towards the time when staging is going to happen. Watch the top of the rocket there, just underneath the Dragon capsule. That's where the second stage is. You see that the whole thing just explodes into a pile of cryogens. And if you watch carefully, you might have seen a little shadow float back out of there. So what happened here is in the second stage, there's propellant, right? And that's sitting on top of the rocket. Inside, they need to pressurize these tanks. And so because they're pressurizing the tanks with helium, they want to keep the helium cool to make it have as low pressure as possible. So they put these pressure vessels inside the oxygen tank, the liquid oxygen, right? And if you actually look, you can see this camera view inside the oxygen tank. There is these black cylinders on the side. And by the way, here's another example of what happens after you get to orbit, right? This is when you go into 0G, the liquid oxygen all floats around. It's very cool, right? There's some more examples. So anyway, if we go back to this failure, what happened is these tanks, they are sitting under the oxygen and they want to float up because their density is less than that of the liquid oxygen. And as the G-forces increase, you might think the weight of those things will increase and they'll want to sink, but no, because the oxygen is heavier, so it actually sinks down more and increases the buoyancy from these tanks. So as it accelerates, as it's burning fuel and getting lighter and the G-forces are building up, these tanks are getting more and more buoyant and putting more and more stress on the struts. And as they reached about 3.2 Gs, the force caused one of the struts to break and the oxygen tank slid forwards, right? And of course, as it goes forwards, it breaks the connectors to the rest of the tank. It hits up, strikes the front of the tank. It's now releasing lots of helium, over-pressurizing the tank. And they figured this out because they actually have accelerometers all over the vehicle that were recording vibrations at a very, very high rate. And they were able to actually measure, based upon the speed of sound, where this bump happened. And they could measure when it was released, when it hit, and they correlated to the event within microsecond or milliseconds. So that's how they figured out what went wrong. What went wrong, was that they had a strut which didn't perform as it was supposed to. It was sold to them by a third-party supplier, and SpaceX became even more vertically integrated and built its own struts. This is another one. Footage which was supposed to be a test fire back in 2016, and instead something altogether more spectacular happened here. Yes, this is amazing footage. I watched the top of the rocket fall down, and it explodes as well. It had a bunch of propellant on board. So this was Amos 6. It was a satellite that was, I think it had some SpaceX involvement to provide communications in third world. The explosion happened inside the second stage oxygen tank, right? They had a new fuel loading procedure. What they did was they decided to load liquid helium into these tanks instead so that they could put more in and then it would warm up to the temperature of the liquid oxygen. But they had also developed a new way of improving the performance of the Falcon 9 by using densified propellants. That is, the liquid oxygen was made even colder than normal. It was loaded close to its freezing point rather than close to its boiling point. So now liquid helium goes into these helium tanks. That lowers the temperature, and the pressure vessels are basically like an aluminium like rigid structure, and then there's carbon fiber that's taped all around the outside to give it extra rigidity. And so the oxygen, the liquid oxygen, can permeate through the gaps in these layers and contact the internal tank, and that stuff that did, it froze because it was in contact with the liquid helium. And as it froze, it starts to add stress to the exterior, right? So it's pushing, as the tanks are being pressurized, this oxygen is getting pushed outwards. So yeah, here's a rough example. You've got liquid oxygen near its freezing point. You've got this composite overwrap. You have a thin impermeable layer, and then you have very cold helium in the inside. So now, as the helium is loaded, it actually causes the tank to shrink a little, right? So it sucks in a small amount of liquid oxygen against it, and that oxygen becomes solid. So now that solid oxygen is mixed with carbon fiber, and you know what carbon and oxygen can do under the right conditions, right? As the tank is pressurized, it's now pushing out against the carbon fibers, and the carbon fibers they're pulled tight and they break. And when they break, they release a small amount of energy. It can be like a spark. And when you've got a very, fine, well mixed chemistry where you've got basically carbon fiber and oxygen and a tiny spark, boom, right? That's what happened. This is what they believe happened, and it's such a cool failure, I have to discuss it. Another SpaceX failure was the Dragon 2 abort test. So this is what Dragon 2 is supposed to do during a launch abort. It has these little motors that carry it free, and then it's supposed to deploy parachutes. What happened when they were testing this was that, and this is unfortunately a terrible video, but what happened in this case was that you have a high pressure helium tank and you have the oxidizer and the propellant. And when you're going to use the Super Draco thrusters, they have their own high pressure helium system that's supposed to pressurize this. So they have check valves here that get opened. And unfortunately, what really happened in this case is the one-way check valves are not quite perfect, right? So the idea about a check valve is that it allows propellant to flow in one direction, but not in the other. And the pressure of the propellant flow is supposed to hold it in place. But again, these are not necessarily perfect. And so you had a very tiny amount of oxidizer leak through and fall into a low part of the piping. So now, as this, as they start to fire the engines, they open the helium valve and it starts flowing down these pipes at very high speed. It runs into this tiny slug of the nitrogen tetroxide, and it starts accelerating it down the pipes like a bullet. It then smashes into the check valve, which has components in it which will in fact catch fire, and indeed you have a fire which results in the titanium starts burning, which very quickly turns into an explosion. So instead of firing the rocket engine, we get a giant explosion. Oh yeah, here's the Starship flight test. Yeah, I guess I added this one. We've had a flight test.
Come on, you can do this.
I've never seen in my life.
This is amazing. It's hard.
Billy Flops.
This is it.
Oh my God, this is amazing.
Oh my goodness. Are you kidding?
Attached to it. I don't even remember what to say, but oh yes. So the Starship flight test basically was supposed to demonstrate the belly flop maneuver. And on the very first one, as they're coming down, the rocket engine, the exhaust turns green. And the reason for this is that it went oxidizer rich. So inside the tanks, they have a header tank, which contains the fuel. But due to some valve issues, it actually got crushed and it sprung a leak. And so there was no pressure in the fuel system, which meant they had more oxygen. That's why they had the green flame. We also have some other engine-rich exhaust here as this comes down. This was one of the first big jumps for the Starhopper. It turned yellow because it was also eating its engine alive. And yes, we have some fantastic footage, a compilation of SpaceX going through its various iterations of attempting to land their boosters. As I said, rocket science is hard, but rocket engineering, where the landing legs meet the landing barge, that is not really tolerant of failure. This was a test vehicle which happened in Texas. Yeah, that's Elon. He had just gone for ice cream at Dairy Queen. Ran out of hydraulic fluid, and of course lost control. That's wonderful. Technically it did land, just not in one piece. Sticky throttle valve. Oh, you can see that one thruster trying to keep it standing, but it ran out of pressure and boom. Yeah, so look, this story, there's really just to give you some discussion of various launch failures that have happened over time. There's many more stories which have come out since then. I think my favorite launch failure in the last few years, sure, we've had some very spectacular Starship flights, and there's interesting reasons for each of those failures. But the one that I loved most was Tianlong 3, which wasn't supposed to be a flight. it was supposed to be a static fire. When it came loose, it flew, and it, oh boy, they are lucky that it failed when it did, because if it had kept going, it could have absolutely landed, crash landed over inhabited areas with a very large propellant supply. So anyway, I'm Scott Manley. You guys have a great event. Fly safe, but of course, fly well, but most of all, fly safe. Keep it great. Best of luck.